oso pequeño volvió a casa y el oso grande y el bebé estaban distintos. El oso grande estaba más enfadado y era más malo porque no tenían comida. Juntos.
Hello, wonderful people of the internet. Welcome back to another episode of Leos Labs. Okay, so I've been trying for the past hour to get this stream to go live. It looks like is my face a little bit whited out? Let me fix that really quick. Sorry about that. You're gonna see Infinite Me for a second, and I know it's like a very painful thing to see, but give me just a second to lower the brightness on my side. Maybe something like that's okay. Okay. I think it looks a bit better. Let me see what happens. Yeah, a little bit better, I guess. It looks really dark on my side screen, but it looks pretty good on this screen. Anyway, doesn't matter. Okay, let's talk about what's going on. So for the past hour, I've been trying to stream. I genuinely have no idea why, but for some reason, Twitch over here on my dashboard is basically saying that I'm not live. It's no matter what, it is saying I'm not live. It says I have 0 viewers. However, now it's saying that I have a session that's been lasting for 12 minutes, but I still have no viewers. And then if I go over here, we see we have 9 viewers, and it now says 12 minutes. I don't know what happened. But for some reason, we were not able to load stream, and now we're able to load stream. So I guess it's fine. Let me do one more thing with my video capture really quick. I think the audio and video is slightly out of sync, and that's about as good as we're going to get. Okay, so Shadow Mishia, Emrys, Panaputi, hey, thank you guys so much for coming in. I am really sorry about the issues that we just had. I've genuinely been trying to stream for the past hour, and I've just been running into a bunch of issues. Before even starting stream, I was running into a problem with my camera, which, like, you couldn't tell, when I started, the brightness was off. There were so many issues. I don't know what the deal was, but today, like, the technical gods were like, I'm gonna smite this person in particular, but it's okay. I use Linux, so, figured it out. It has nothing to do with me using Linux. It just has to do with me being, persistent and trying again. Okay, so we're going to start today, as we normally do, with a bit of algorithm archive work. In particular, we're going to read up the last bit of the Metropolis algorithm chapter, which should be, one second, where is it? Here, GitHub repository. Oh, it's going to be a long day today. I'm really struggling. It's okay. So we'll look at the Metropolis chapter. Essentially, we're going to read the last half of the Metropolis chapter today. Hope that it's good. And then there might be a few other PRs I should look at really quickly, but I don't remember what they are. So if anybody in chat wants to update me on what those are, feel free to let me know. There was something in the Algorithm Archive channel on Discord. I think Nick put something up not too long ago. And yeah, there's some other discussion that I want to be updated on. But I don't remember what it is. So we're going to do the Metropolis chapter. That's what I'm going to focus on now. Let me move the microphone just a little bit. Sorry if there was a loud squeak there. Okay, and then we can talk about what we're going to do for the most part today, which is going to be updating the four-dimensional galaxy simulations so that they are instead color quantizing. We'll talk about it in a bit. It's going to be an interesting stream, to say the least. Let's go ahead and do Control-C. Let's go CD into Projects, Algorithm Archives. CD Projects, Algorithm Archive. Then we're going to do Git branch to make sure we're on the right branch. Pull the latest changes from this particular PR. I use Arch, by the way. Yeah, I mean, yeah. I don't know if you've been keeping up, but there was there's a channel on YouTube called Linus Tech Tips. They're reasonably popular, and they have recently done a video series where they tried to use Linux as their like daily driver machines, is what they called it. And man, they struggled a bit, and it's fair. Like, I mean, I understand that Linux is not the like easiest system to use for various people, but I just thought it was kind of funny. It was a good, I think, description of how like desktop Linux is and all this kind of stuff. One of them used Manjaro, which is a type of like, it's an Arch derivative distro. Anyway, let's just go ahead and build this and look at the second half of the chapter. Algorithm Archive npm run serve. Okay, so if you guys are here for the first time, you haven't been here before, first of all, welcome. Second of all, we are working on a project known as the Arcane Algorithm Archive. It is an attempt to basically create an open access textbook for a bunch of different algorithms, with the priority being on good algorithmic descriptions. And what we do is we allow each algorithm to be written in various different languages, as many languages as we can support as a community, in order to teach the algorithms better and also to provide some example code for each of the algorithms. We opted to do that, obviously, instead of pseudocode because, well, a number of different reasons. But I think it just is kind of a little bit nicer to do. So let's go and do localhost here. And so right now what we're doing is we're looking at the second half of a new chapter that was submitted for the Metropolis algorithm, which should be here. Yesterday we read through the first bit here talking about probability distributions, sorry for the yawn, and all that kind of stuff. So today we're going to read the second half of the Metropolis algorithm, go through that, make sure the text is fine. There's still going to be little notational things that we have to fix, but for the most part it should be pretty good. Okay. So let's go ahead and read it. We're starting with a random walk in one direction. Again, if you guys have any questions, comments, concerns, ideas, anything like that, feel free to let me know. I'll address it as soon as I see it in chat. And in addition, if it's specifically about this chapter, I might ask that you go ahead and put those comments also in the pull request, so we can make the chapter as good as possible. Again, usually when I'm writing chapters, I do it in a very open way and all this kind of stuff. But, a lot of times it doesn't get that much review. And I kind of like, I like the fact that it's getting a lot of review. So I think that just makes it better, Okay. As far as stream today, because I spent a full hour trying to get stream started, unfortunately, I probably will not be streaming like longer today. So it'll just be a 5-hour stream instead of a 6-hour stream. You guys are just going to have to deal with that. I'm really sorry. I literally spent like 20 minutes trying to get the camera set up. And then I spent another like 20 minutes just trying to get stream to load. So I'm sorry, I ran into a bunch of problems. I again am really sorry if you got multiple notifications for this stream. It's not that like this stream is any more important than any of the other streams I'm doing. It's just that I ran into a lot of troubles getting it to launch. So if you got like 3 different notifications, that's because I tried and failed to launch stream 3 times. There were a lot of people saying they couldn't see it. There were like 3 people saying they couldn't see it on the Discord. And I myself couldn't see it. It's kind of one of those checks that I do whenever I start stream, just to make sure that it's loaded properly and all this kind of stuff. Okay, let's get through this chapter, and then we're going to hop into, hopefully, color quantization. We'll talk about it in a bit. It's actually really interesting, and I'm hoping you guys enjoy what we're going to do here. There's actually a lot of like cool things to talk about in the stream. So, a random walk in one direction, one dimension. In the rest of this chapter, we will look at a 1D example. We'll look at 1D examples to understand the Metropolis algorithm. Interesting stuff. I'm glad you think that. Six Granny Smith. How are you doing, by the way? Although the algorithm is not particularly efficient in just one dimension, it's much easier to understand and learn how to implement than in higher dimensions. Wait, what? Although the algorithm is not particularly efficient in just one dimension, it's much easier to understand and implement in 1D than in higher dimensions. I think I'm having trouble with the sentence. Let me go to here and let's start the review. Files changed. And let's go to here it is. Go down halfway through the page. And again, guys, if you don't find the chapter reviews to be too particularly interesting, I totally understand that. I put it at the start of stream because I think it's really important to talk about it and do it every day. But at the same time, it is kind of different than the other content that we'll be doing for the rest of today's stream. So if you're more interested in the, 4D galaxy simulations that we were doing yesterday, or some of the GPU computing stuff, we'll cover that in about an hour. But I do think it's really important to get through this and really do some algorithm archive work every day. Otherwise, the project just kind of slowly but surely dwindles into nothing. You know what I mean? So what am I doing here? In most cases, here it is, random walk in one direction. This particular sentence is bothering me somehow. Although the algorithm is not particularly efficient in just one dimension, it's much easier to understand and learn how to implement than in higher dimensions. For some reason, this is bothering me. I think it's because it's much easier to understand. I think I want to change this to say it's much easier to understand with fewer dimensions. Well, with fewer dimensions. My issue is that although the algorithm is not particularly efficient in just one dimension, it's much easier to understand in one dimension than in multiple dimensions. Maybe that's what I'm going to say. Understand in one dimension than in multiple dimensions. Maybe that's okay. Let's go ahead and put a period on that. All right, start a review and let's keep going. Okay, the Metropolis algorithm is very similar to a random walk. So let's first see how we can get a distribution from a random walk. All right, let's go ahead and play this video. Looks good to me. I think the video is fine. I mean, we might argue that, for smaller browsers or whatever, the text is a bit small on the axes here, but I guess it's probably fine. Let's go up here. The dot in the figure above is a walker whose initial position is x equals 0. Leia's not watching a video in x3. Wait, in x3, what is x3? The step size g is a random number in the interval -1 to 1. To get the next position of the walker, we simply generate g and add it to the current position. Sure. Speed times 3. Oh, I wish I could. Genuinely wish I could. Most of the videos I watch are definitely at least speed times 2. I thought X3 was like, a new Windows manager or something. I don't know why. I guess because the X Windows manager. And I was like, oh yeah, definitely talking about a new Windows manager. To get a distribution of X from this walk, we can divide the domain into discrete locations or bins and count how often the walker visits each bin. Each time it visits a bin, sorry for the yawn, the frequency for that bin goes up by 1. Over many iterations, we get a frequency distribution of X. I'm still not entirely comfortable calling it frequency. I don't know why, but it's fine for this. I think it's okay. So a random walk with acceptance criterion. Is that supposed to be singular or plural? The Metropolis algorithm works in a similar way to the random walk, but differs crucially in one way. After choosing a random step for the walker, a decision is made about whether to accept or reject the step based on the function f of x. To understand how this works, let's call x of t the position before the step and x prime the position after it. We then define the probability of accepting the step to be f of x prime over xt 1. The min function above implies that a is equal to 1 if f of x prime is greater than x, f of xt, which means that the move will always be accepted if it is towards a higher probability position. Sure, that makes sense. Otherwise, it will be accepted with a probability of f of x prime over f of xt if we create a histogram of this walk for some arbitrary target function p of x, we can see from the figures below that the frequency starts to look very much like it after many iterations. That seems fine. It blazed me so much to learn that the first one to solve the random walk in 2D was in a paper about a particle, which was a quantum of energy without mass, coming from 1905 and written by Einstein. Wait, really? I didn't know that. Einstein published another paper in 1905, and it was about random walks in 2D? Like, how many papers did he publish that year? Like, genuinely speaking, like, every one of his papers apparently created a new field, including random walks, apparently. But I'm surprised. Random walk in 2D seems like... It seems not like... it seems like normal. Like, it doesn't seem very complicated, I think he published 4. Lev Tall, thank you so much for following. Really appreciate it. All right, let's take a look at the video. Ooh, this is fast. Watching it at 3 times speed now. I think it's fine. So although convergence occurs eventually, not all parts of the distribution achieve convergence quickly. Note from the animation above that the walker very quickly replicates the distribution of the 2 peaks on the left, but it takes quite a while to even reach the 3rd peak on the right. This is because there's a long barrier of low probability region between the 3rd peak and the 2nd peak. Sure. This may not necessarily be a bad thing. Sometimes one might want to estimate how long something takes to transition from one state to another, and often these peaks represent such states. So averaging over many metropolis runs may give some estimation of these transition times. And if global sampling is the goal, the process of exploration could be sped up by choosing larger step sizes for the walker. For example, by choosing step size g from an interval -3 to 3 instead of -1 to 1. Sure. What do you have here? I think you published 4. Can you share a link with us? Let's see. I think the one they are talking about was Brownian motion specifically. Oh, Brownian motion. That is a bit different. Brownian motion is, it is a random walk in 2D in a sense, but also Brownian motion is like, it's super fundamental to like so many different areas of physics. It's kind of like, lots of people know and love Brownian motion. Let me see, where are we? We are random walk with acceptance criterion, and it should be here. Let me just go ahead and remove the and at the start here. There. Wait, what happened here? How did that happen? Okay. Let's just remove this top bit. There we go. That should work. Delete that. Add review comment. Perfect. Okay. Then I think we have the initial setup, and I think the rest of it's just an example, which is good. Okay. Yeah, this is good. So the algorithm for a one-dimensional example, the initial setup. So let our target distribution be the following here, where f of x is a function we know and is given by the following, sure, is a function we know and is given by the following. I don't think the makes sense here because I think a makes more sense. The code for defining this function is given below. I think also there should be just a quick sentence here saying, now we'll show you how to do this with a simple one. Yeah, okay, that's fine. So I think there should be a comment here. Introducing the upcoming sections. All right, keep going. It's a PR. It's not online yet. You can see it here. Oh, wait. I thought Levtal was talking about the chapter or the Brownian motion paper. I didn't think he was talking about the PR. Sorry about that. I completely misunderstood. This is going to change here to be is a function we know. Add a view comment. Slowly but surely getting there. Okay. So what do we do here? Where f of x is the function we know. Okay. The code for defining the function is given below. Okay, sure. Since this is an easy function to integrate and hence get our target distribution p of x directly, we can use it to verify the Metropolis algorithm. The plot of p of x in the figure below shows 3 different peaks of varying width and height with some overlap as well. Oh, it's the same function as above. I see. Now I completely misunderstood. Is the same function as above. We have shown above and is given by the following. There we go. That makes sense to me. Wait, is the same function... Interesting that it changed it like that. Okay, so since this is an easy function to integrate, and hence get our target distribution p of x directly, we can use it to verify the Metropolis algorithm. I think we just talked about that. So next we define our Walker's symmetric step generating function. As in the random walk example, we will use a random number between -1 and 1 in step size. Sure. Okay, however, g can be any function symmetric about 0 for the above algorithm to work. For example, it could be a number chosen randomly from a discrete set, discrete list, such as -3, -1, -1, +1, +1, +3. It can also be a number chosen from a symmetric continuous distribution, like the Gaussian e to the negative x squared, like the Gaussian e to the negative x squared. In higher dimensions, the function should be spherically symmetric, such as multidimensional Gaussian function, such as a multidimension, or the multidimensional Gaussian function. 1 second, where are we? There's that, and then we have this guy. Was this supposed to be -3, -2, -1, +1, +2, +3? Or was it meant to have multiple 1s and 2s? I'm actually not sure. Let me just go ahead and mention that. To be clear, this was meant to have multiple 1s, right? Just double checking, just to make sure, you know. And then here we need to change this. So in higher dimensions, the functionality should be spherically symmetric, such as with the multidimensional Gaussian, such as the a multidimensional Gaussian function, maybe. All right, review comment, perfect. Okay, whatever function you choose, there are at least a couple things to note. One, if the function g is discrete, you will only sample discrete values. For example, if g returns only -1 or +1 and nothing in between, you will sample only integer steps away from the initial x0. The average step size really matters. A small step size means the walker will carefully sample in nearby regions more, but will walk more slowly, so it might not be good at exploring far and wide. On the other hand, a walker with a large step size may not sample nearby regions accurately, and actually has a higher chance of being rejected if the walker is already in a high probability region, since the acceptance ratio is more drastic for larger steps. The effect of step size on the walker's efficiency is far from obvious. Sure, fair enough. Okay, 1 second. How to choose G is in itself a research field, is it actually? And depends on what the goal of the sampling is. Some methods even use an adaptive method where G is trained on the fly using a learning algorithm. Sure, fair enough. Some of these methods and others are discussed in reference A and reference 9. In a lot of cases, people just use trial and error as the algorithm is not too difficult to implement. After choosing G, we are almost always ready to iterate. We're almost ready to iterate. There we go. We just need to choose the domain of x and the initial position for x0, xt at t equals 0, chosen randomly from the domain of x. Sure, okay. So how to iterate? Generate a new position, proposed position x prime is equal to x of t plus g. Calculate the acceptance probability, sure. Accept proposal, x prime with a probability a. If your programming language doesn't have a built-in method for this, generate a random number u between 0 and 1. If u is less than or equal to a, then accept the move and set the new position x of t plus 1 is equal to x prime. Otherwise, reject the move and set the new position as x of t plus 1 is equal to x of t. Increment t is equal to t plus 1 and repeat from step 1. Sure. Okay, fair enough. The following plot shows the result of running the algorithm for different numbers of iterations n with the same initial position. The histograms are normalized so that they integrate to 1. We can see the convergence towards b of x as we increase n. Yeah, I actually really like that plot. Honestly, I think it's quite nice. I mean, maybe other people don't, but I think it's actually a really nice plot. Okay, so example code. The following code puts everything together and runs the Metropolis algorithm for a number of steps given by num steps. Where's the example code? Should be down here. There, change this, runs the Metropolis algorithm, add review comment. All the positions visited by the algorithm are then written to file, which can be later read and fed into a histogram or other density calculating scheme. The code also incorporates a few tests of the algorithm using the test metropolis iterate method. This test will create a normalized density histogram from the generated data and compare it to P of X using the root mean square deviations metric. Wait, does it actually use RMS in here? Okay, fair enough. Overall, I think the text is fine. There is a general question I had while reading this, which was, is the data already output in a histogram form or not? That, I guess, was my question. How do people plot the histogram? Yes, that was my only question. And the answer right now is that... Yeah, that was my question. How do people plot the histogram? So I'll take a look at that probably tomorrow. Let's go here and let's just go ahead and finish the review. Overall, very small changes to text. I'm sorry to keep splitting this up into a bunch of smaller reviews. Let's see, I'll look at the code tomorrow. And then I think the PR will be mostly ready to go. All right, comment on there. Perfect. Submit the review. All right. Good. Happy with that. So we have some small changes meant to that PR. There's probably another algorithm archive PR we'll take a look at later. For now, I think we can go ahead and move on to the bulk of today's stream. So what are we doing? Let's go ahead and Control C here. I did a couple things since last stream because my GPU was consistently chugging every time I was playing a video on stream while also doing a bunch of other things. I made it so I only have one camera instead of two cameras. There was a second camera that I was going to be using specifically for Swoleos workouts. I removed that entirely to see if OBS would maybe use a little bit less processing power. And so let's just go ahead and show the videos that we made yesterday. Oh, it's chugging. It's still a problem. It's okay. I wanted to fix it. All right, so we're going to CD into projects. Then Galilee. Here we are. CD into aux. LS here. And let me just go ahead and play a video for you guys. So we're going to do mpv all.mp4. Okay. So as of yesterday, for the past few days, we've actually been doing a bunch of different things dealing with n-dimensional galaxy calculations. You know, I usually introduce it as 4-dimensional, but n is actually the appropriate term here. We have anywhere ranging from 1 to infinity dimensions. Technically, we can calculate, 1 to, 1,000 or 2,000 dimensions. We can calculate a lot of dimensions here. I'm not saying we should do that, but I'm saying it is possible to do that with our simulator. So here's a 1-dimensional gravity simulation. And you see here, in principle, this is all along a single line. But we've stretched out all the particles, so we just see all their positions here. So you can imagine them all being squished together and then just moving back and forth on a single line. Kinotaru, thank you so much for following. Really appreciate it. So after this, you'll see a 2-dimensional visualization where you can actually start to see the structure. I'll let it play for a little bit longer so people can watch it. But yeah, so this is using a force law, which is F is equal to some sort of gravitational constant times the mass of 1 times the mass of 2. The masses are all going to be equal to 1 here. They're all the same mass over r squared. The r squared here is a distance metric, and it's actually kind of important. So here we have the 2-dimensional simulation. You saw that they all kind of came in and they didn't really explode. They actually just like passed through each other. This is because we don't actually have collisions in this model. So what ends up happening is the particles will just move right past each other and zoom past each other before they eventually clump up into a ball. So when we take a look at the 3D simulations, we are actually expecting to see almost the same thing. And all of these 3 dimensions that we've done so far, or we're doing, which are all like kind of physical dimensions, we used the 1 over r squared force law. And that's because that's the force law that you expect to see in 3D, and we've just kind of extended it to 2D and 1D as well. Okay, so we kind of get the same result here with the 3D simulation. Now, let me kind of talk about what's going to happen in just a second. So soon we're going to move on to the 4D simulation. Now, for the 4-dimensional simulation, I didn't think it was exactly fair to use the same force law 1 over r squared. The reason it's not fair is because if you actually do the math, there is definitely, you got to integrate over another dimension, which means it should be 1 over r cubed instead of 1 over r, it's not a rerun, instead of 1 over r squared. I just wanted to explain something that happened yesterday and explain why we're not doing the galaxy simulation now. So when this switches to 4D, okay, wait, let me go back a second. So here is the start of the 4D simulation. Give it a second. Should be, okay, 1 second. I need to wait just a second. I should have just gone back a couple frames. There we go. So let me go back a couple frames. So right here. So this is the start of the 4D simulation. So what's going to happen in 4 dimensions is that these particles are going to come together and they're going to zoom right past each other like they did before. However, because it's 1 over r cubed, the amount of force that they feel from the individual particles is much, much less when they're very far apart. So what you're going to see is actually these particles kind of move around until they kind of hit this point where like they don't really have the acceleration component from the other particles affecting them anymore. And they kind of form this crystal-y structure. They just kind of stick in place. And that's because each of these particles don't really feel anything around it. Now, for the simulation, it was done in 4 dimensions and we projected it back down to 3D. So you might have noticed, just a second ago, let me just go back a couple frames. I don't think this will chug my computer. But you might have noticed like just right over there. Here, that's not bad. Right here. So like this particle, for example, left the box. Now, look, just to be clear, this particle is not going into the W dimension. It's actually just leaving the bounding domain that we're plotting. All of the particles are here. All of the 4-dimensional particles in all 4 dimensions are here. They're just projected down to 3D. So for that reason, it's not like anything weird is going on in the W dimension. Everything that we can see is here. And it kind of led me to believe that doing the 4-dimensional galaxy simulation is probably not as interesting as I would have hoped it would have been, if that makes sense. So I was hoping that we could do a 4D galaxy simulation. We could see like, these cool disk formations and all that kind of stuff. But the more I look at it, let me just take a look at the 4D .mp4. The more I look at it, oh, what? Oh, what happened to my 4D visualization? 4D R2. Wait, what? Should exist. Wait. Where is what happened? Oh, I see. I'm stupid is what I am. I was putting the MPV command. Okay, let me just take a look at the 4D here. .mp4. Okay, so here's that 4D visualization one more time. And we see they just kind of crystallized. So if we were going to do the simulation again, I'm not seeing it as something that's particularly, I don't know. I don't really see how it's going to work. Doesn't time count as a dimension? Not in our simulations. I mean, sure. Okay, so it's a 5-dimensional simulation then, but we're not counting time as another dimension. So a lot of times when people say time is a 4th dimension, they're specifically talking about space-time. And here we're not considering, we're not dealing with dimensions in that way. We're considering 4 spatial dimensions, and then time is a separate one. Also, when it comes to space-time, a lot of people will consider it Minkowski space, which considers time as this kind of imaginary thing. I think it might actually be the same thing, but yeah, we're not doing that here. Literally 4 spatial dimensions is what we're looking at. It's slightly different, but that was what I was interested in. Okay, so let me go ahead and plot this again with the 1 over r squared. So if we use a different force law, the 1 over r squared force law, then we get kind of what you would expect in 4D. So we get all the particles to come together, and we see that they're kind of moving really fast out here, but they're still kind of creating that clump in the center. So we could do the 4-dimensional simulation with an r squared force law. We could do that. And maybe that's what we want to do, but I haven't really decided if that's what we want to do or not. So at this stage, I kind of want to just put the 4-dimensional visualizations on the back burner a little bit and come back to them in, I don't know, in the near future, in a week or two, when I have time to think about it, read some more papers about it, and just kind of figure out if there's actually anything interesting to come of this, or if it's just going to be completely unphysical type of thing, Okay. So let me just have a video playing in the upper left-hand corner so there's something there, and then we will we'll talk about what I actually want to do today, which is a little bit different. So let's go ahead and do MPV all.mp4 loop. There we go. And we'll just move this up here in the corner. Man, I really need a better GPU. Okay, let's move this here. Move this over here. Okay, come on. I'm lagging a bit. Perfect. Now I have some audio and video desync. Let me go to fix that. My GPU is so bad that even when I like try to fix it, like even when I just all I'm doing is like moving screens around, it's failing on me. Now again, this could be a Linux issue, not a GPU issue. Probably is. Okay, so let's go here. Make this overall desktops over here. Move this down. Okay, perfect. So we've got the visualization just up there in the upper left-hand corner. Now what I want to do next is just open up Zenworld PP and talk about what we're going to do today. So let's move this over here, move that over there. So, and this, perfect. Let me get some water. Okay, so let me explain what the purpose was of the 4D simulations first, and then we can talk about, why I feel what we're going to work on right now is actually worthwhile direction in some sense. Sorry, I was getting thirsty. Okay, so, right, so we just talked about the 4D galaxy simulation. So 4D galaxy simulation, right? And I mentioned I'm really not sure what to do with forces. Right. So that's one thing. In particular, the reason we were interested in the 4-dimensional galaxy simulation is because if you take a 3-dimensional galaxy and you let it evolve with time with some sort of initial angular momentum potentially, it will eventually form a 2-dimensional disk. This is a pretty well-known thing. I mean, it's why the Milky Way is, a spiral galaxy. Most galaxies in the known universe are spiral galaxies. There might have to be a black hole at the center. There might be a bunch of other things that we have to consider. But for the most part, if you let a 3D galaxy simulation run for a while, it'll form a 2D disk. So the reason, I'm sorry, I'm so tired. The reason the 4D galaxy simulation was so interesting was because what happens in that case? Do you get a 2D disk? Probably, right? Because a 2D disk is formed around like an axis of rotation, right? So in 4 dimensions, you have 2 disks that you can rotate over. You have an XY and a ZW plane. So could you get a double rotating galaxy? That was my kind of naive question, and I didn't really have a good answer to that. So that was kind of like the naive physics reason for why the 4-dimensional galaxy simulation was interesting. It's like, what actually can you form here? And to be clear, it's actually not that interesting physically. It's not something that like people will look at and be like, wow, that's groundbreaking research. It's more like, it's there. It's not too uninteresting, right? I think it's one of those things that could be quite clicky, specifically for YouTube and Twitch, and that's kind of why I was thinking about doing it as kind of an easy way to talk about the research that I actually want to do. And the research I actually want to do is to improving n-body simulations. Okay, so this is why this is interesting to me. Hey, Crowbab, how are you? So let me just go ahead and draw this out in blue. Let's imagine we have a whole bunch of points in space, right? Here we go. Lots of little points in space. The way the galaxy simulation works is that you have each of these points affecting all the other points in the simulation, right? So if you have a single particle, it has to look at all other n particles in the simulation before it decides where it's going to move, because each of those particles can influence the acceleration of this particle right here. Now, the way these n-body simulations are typically done is you will split up space along something known as an octree, which essentially allows for us to split up the grid into these octants or quadrants in 2D. Something like this. Forgive me that the grid is kind of askew. Something like this. So this would mean that each individual particle kind of gets its own box, right? And if you want to combine 4 particles together into one macro particle, you just use this box here, the box that combines all of them together, right? By doing this, you can actually make it so that the simulation that you're looking at will see all of the particles nearby, so all of these particles, but then we'll treat all of these particles as one giant glob, which allows for us to basically approximate the physics that we're looking for, so that this particle will see one big old blob over here, and then a bunch of smaller blobs over here, and it can move, to an extent, as physically as we can, with with the constraints that we have, right? Now, there are a bunch of other ways in which you can do these simulations, and I've thought about a bunch of different ways to do them, which are potentially less computationally costly, but every single one of them has some costly thing. Like sometimes it's the parallel summation that's costly. Sometimes it's the histogramming that's costly. Sometimes it's there's all these little problems that pop up that are very difficult to solve, right? And so the question is, which of these bullets do you want to bite? Do you want to bite the tree traversal one, which is what you have to do with the octree? Do you want to bite the bullet that has to do with, an incredibly fast summation routine, which is what you have to do in a pure n body? Do you want to deal with histograms, which is what you have to do if you're just going to add all the forces together to create like some sort of weird force landscape that people move across and stuff like this. So basically all the different ways in which you can solve this system require some weird, unoptimized thing on certain hardware. So this brings me into my next question. So the reason I was interested in this problem is because the act of improving these n-body simulations, the act of finding a way to split up all of these particles in space so that we can, optimally look at them and all this kind of stuff, it comes up in a number of different problems. So not only does it come up in the physics problems, but it also comes up in a lot of computer graphics problems. And in particular, one big computer graphics problem that I just run into all the time, somehow I don't know why, is color quantization. I literally come across this problem a lot. I don't know why, it just pops up all the time. And because it pops up so much, I figured today, since it's basically the same problem, we can try to optimize our color quantization schemes first, and then go back to the n-body simulation and use what we've learned there to improve the n-body simulators. So if you guys don't know what color quantization is, let me go ahead and write that out as well. So you could imagine you have some sort of image that's composed of like green, red maybe over here, mixed with the green, and then perfectly red over here, and then maybe a little bit mixed over here with blue, something like this. So here's our crappy image. Pretend I can draw. I can't. Just please pretend for a second. What color quantization does is it goes through your image, and it basically creates a set of colors that can approximate the image that you're looking at, right? So for this image in here, we have this region in the center. Let me go ahead and color it in white, whereas that's like a mix of red, green, and blue, right? And so what it might do is it might say, okay, well, we don't want to mix colors here. What we're going to do is we're going to say this region over here is primarily blue, this region in here is primarily red, and this region in here is primarily green, and it just casts those colors onto the quantized color that you've created. So for example, if you have like something that's kind of blue, it will cast that onto a pure blue color. So let me show you this in action. We've actually done it a few times before. So we're going to CD to projects, Mosify, I think is the last time I did it. CD projects, Mosify. Go over here, type in ls, and I should have a check.png, mirage, check.png. Okay, here, for example, this will work. Let me go ahead and full screen this guy. So this is a pride flag, and here it is color quantized. So what you can see here is that we have, a whole bunch of different colors, and then we have 8 colors to represent, all the different colors in the scene. So what we're looking to do here is kind of optimize this color quantization scheme. Again, there's a bunch of different ways to do this, and I'm not entirely convinced the best way to do it, but I kind of wanted to take a look at this. Now, I'm actually up for debate here. If you guys want to do other things first, we can. It's just that we're going to have to look at the spatial splitting scheme at some point, and I kind of feel like, hey, maybe now's a good time to do it. But yeah, I'm up to hear what you guys have to say about this. It means that today we're going to have to do a lot of just not GPU hacks, but we're going to have to try to figure out how to put this in parallel. In particular, the problem that I'm going to run into is parallelizing an octree. For this particular code, that's going to be a pain. I'm not entirely sure how to do that. There's also other things that we have to parallelize. We're going to have to go back to the problem of parallelizing a histogram, which we never managed to do properly. Just for the record, I never managed to get that code working. We ended up having 2 to 3 weeks of failing miserably with kernel abstractions. And then at the end of the day, we didn't even get the code working. Oh man, we should go back to that problem. So let me actually go ahead and put a poll up, I think, on Twitch and see what people are mostly interested in. For today's stream, it is currently, 3:30 in the afternoon, which means I'll be streaming for, another 4 hours and 30 minutes or so. So we can make significant progress on something. And I'm interested to see what we do here. So let me think about the things that we could work on today. So I was thinking color quantization would be nice, but there's a bunch of sub-problems here. Did you wrap up the project about fractals? I did not. So in fact, let me explain how this all goes together. So the fractal, in particular, the fractal stuff that we were working on was fractal compression. Okay, so the issue with fractal compression is that it's composed of two different steps here. The first step is fractal generation. Okay, and the next step is we'll say fractal compression itself. I don't know what to call it, but fractal. Let me just re-describe this entire project because I think some people might not know what I'm talking about. So let's imagine we have some sort of image. It doesn't matter what the image is. Maybe your image is this guy up here. Yeah, let's just say our image is this weird thing that we have up here. Perfect. So here's our image, right? It's not a great image, but it is some sort of image. Let's explain what's going on here. There is a way in order to create images via something called an iterated function system, an IFS. So what you can do is you can actually create a bunch of really interesting visualizations. So let's CD to projects, Flamify, ls here, and let's see, let's go into Mirage, save one.png. So this is an example of an iterated function system in practice. So the idea is there's a bunch of underlying equations that will create some sort of structure. So here, for example, is the heart. And so that's one of the equations we used. And then it also has like a swirl effect and a bunch of other effects all rolled into one, each one of which is described by a specific mathematical equation. Then what you do is you send millions of particles into the simulator and they all just kind of diffuse out until you find the actual attractor, which is the structure you see here. You'll see this a lot in like things like the Sierpinski triangle and the Barnsley fern and stuff like that. So the idea with the fractal compression method is that if you start with some sort of image, you can actually decompose this image into a set of arbitrary equations in a very similar way. So, for example, let's say I wanted to draw a heart, right? Well, I already have an equation that can draw a heart pretty well, and so you could imagine manipulating this image with a bunch of different equations and a bunch of different things until eventually we can get that heart shape that you want, right? And so the idea is that you start with an image and you try to find a set of equations that closely approximates the image. And then once you have that set of equations, you just generate the fractal again to recreate the image. So you compress it into equations and you expand it back out into your fractal form. Now, this type of compression was at some point competitive with JPEG for like the compression metric that people use for images and stuff like that, but it didn't win out. And the reason it didn't win out is because even though the decompression step, the step that is generating a fractal, is relatively fast, the part of the process that generates the equations is relatively slow. In fact, incredibly slow, like 50,000 times slower. It's some ridiculous number slower than it is with JPEG. So because of that, people don't usually use fractal compression today. But the fact that we can, like represent any n-dimensional field as a set of fractal equations is actually quite useful, I think, in physics. And I actually want to try to solve some physical systems on a fractally compressed grid. It's something that I'm quite interested in doing. I don't want to go into the details there, but that's one of the projects that I want to look at. And so what Akris is saying is there's definitely artifacts on the top and bottom. And yes, you're completely right. So what people do to solve that problem is, let me see if I can find another image here. So what they'll do is they will often create a, is that right? No, maybe I'm looking at the wrong image here. Let me see if I can scroll. Okay, let me take a look at another one, maybe this one. It doesn't really matter. The point is, what they'll do is if you see like a whole bunch of particles, they'll blur them together, right? Just to make it, so here you can kind of see how it's more blurry here and less blurry here. So like what they do is they use a convolution with a variable sized filter that allows us to kind of blur particles when they're very far apart and not blur them as much when they're close together. So it's kind of a mess to do. In fact, that's kind of the slowest part of the simulation. But here's the thing, right? So if that's one big thing that I want to do, right? And it's called fractal compression, and it's something that I'm really looking into. Fractal compression. Okay, again, there's two steps here. One is the compression. Compression, and the other one's decompression. So a few weeks ago, maybe a month ago, I was going to say, okay, well, let's focus on the easier of the two problems first and focus on the decompression step, right? But in order to do the decompression step, we have to do a very fast histogramming method, histogramming, right? Right? So in order to do a fast histogramming method, we have to anyway, in order to create a fast histogramming method, we need to find some way to basically optimize a lot of these problems on the GPU. And so I was like, oh, to optimize these problems, how about we work on a sub-problem, which is a photomosaic, which is the act, mosaic, which is the act of basically taking an image and replacing it with a bunch of sub-images. And then after we do that, I was thinking, oh, well, if we do a photomosaic, actually another interesting direction here is ASCII art. And the reason ASCII art is interesting is because there's actually a sub-problem in ASCII art called structural ASCII art. I'm sorry, we're like super far now, but there's a sub-problem in ASCII art called structural ASCII art, which is basically the act of taking a circle and representing it perfectly in ASCII code. And to do this, you have to do a form of shape matching and essentially create some sort of affine map, which allows us to take the circle and kind of extend it out a little bit so it better fits the overall shape, or what we're allowed to use with our ASCII glyphs. And then, after all of that was done, I realized to do the fast photomosaic and to do the fast ASCII art, we actually probably want a fast color quantization scheme. But then I realized color quantization is actually a bit hard to do. So then I was like, wait a minute, let's do the n-body first. Because n-body is actually maybe a little bit easier to look at than color quantization. So this is why we ended up going through this huge chain of events, starting with n-body simulations and working our way all the way back up, well, a mixture between n-body simulations and color quantization, and working our way all the way back up to fractal compression, which will eventually be used back in n-body simulations for physics. So that's kind of where we're at. I'm so sorry, but this is by the way, Joshua 4, thank you so much for following. Really appreciate it. This is where we're at. I do 100% realize, that we're in a bit of that we're kind of, again, a bit in a rabbit hole here, but it is something that we need to, I don't know, it's something that we wanted to, or it's all of these projects are interesting in their own right. So I thought it'd be interesting if we do, again, a 4D galaxy simulation here. Then I do the ASCII art and photomosaics. These will both make really good videos. And then we talk about all this together in a fractal compression, which would make another good video. Go back to n-body. These are all good, little side topics to talk about, right? So for color quantization, don't you only need to make the tree once? See, that's the other thing that I wasn't sure exactly how to tackle. So you're right. What I was thinking about doing was color quantization, quantized videos, for example, where you have a set of images put together, and figuring out how to do the adaptive meshing. I'm calling it kind of adaptive mesh refinement, but it's not really. I just don't know the actual term here. But doing a color quantized video, doing a color quantized video would allow me to kind of imagine how this tree could change slowly over the course of the video, which would also kind of allow for me to do time dynamics in the four-dimensional galaxy. That's kind of what I was doing. Honestly, the strands are quite loose here. There's a lot of little things here and there that we have to kind of, figure out. I'm weak. What's up, Shakala Bakala? Are you okay? I hope everything's fine. Let me get some water. But yeah, so this is where we're at with all of that. So this is why I was like, I see, my colors are for the week. Hi, I'm Gawa. Okay, so let's just so that's why I wanted to take a step and look into color quantization. I think you are right in that the color quantization schemes are pretty much always going to be used for a single time step, and then you just kind of use those colors for the whole video. I think that's what most people do. But I could imagine, I could imagine, here, let me just take a look at my old video on color quantization. Let's go here. And let's go to youtube.com. So a while ago, I made a video on color quantization. Let's go here to your channel. Go to videos. Go to Sure, date added oldest. Here it is, color quantization. All right. I'll go ahead and link this in chat for people who don't want to look at it here. Okay, so I'm also going to make it so I don't say anything. So I did this thing where at the start of the video, I was like, talking about color quantization. I was like, oh, there's something wrong with the camera. Oh, come on, why? Maybe I should just play it on my own. Okay, so let's go here. So if you look up here in the corner, right, because of the way in which we were doing the color quantization, you'll note that there's a lot of flickering. It's kind of like right up here. So as I change things, you'll kind of notice we're using different colors, but in particular, wait, just go back a second. There was a lot of flickering right here, right? And then there's a lot of flickering here, but not as much. As you increase the number of colors, it becomes pretty easily, like there's less flickering, but you saw it just there. There was some flickering with my face right there and all this kind of stuff. What we tried to do with that video is, why has the creator advertisements on his own voice? I don't know. Sorry about that. But, man, that's a good image, isn't it? That's a crappy image. Anyway, the point is that I would like to do a color quantization scheme that removes that flickering. In principle, it should be relatively easy to do, but I don't really know the best way to do it. Outside of doing what I was going to do before, which is just have like a single palette that works for the entire video. That's actually probably the best way to do it. I don't know. You're right. Maybe I don't actually have anything crazy going on. That's a quantum noise. Okay. Anyway, so that's way back in the day. We had the color quantization video, and I really like color quantization. It's super nice. I really enjoy it. I recently changed the thumbnail to that video as well. Like I changed that video thumbnail and this video thumbnail just to try to make them a little bit better. And maybe I made them worse. So I changed this thumbnail, and this thumbnail just recently because I was like, these videos aren't doing as well as I would like. Maybe if I change the thumbnail, they'll do better. I don't know. Sometimes that fixes things. Sometimes it doesn't. But anyway, it is what it is. All right, let's go ahead and close this here. No matter the case, I think optimizing the color quantization will, at the very least, allow me to speed up color quantization, which is something that I use all the time. So that's useful as well. Okay, so let's just see how this goes. I'm feeling super tired today, guys. I don't know why. I'm incredibly tired. I'm gonna still try to do the stream for a while, but I might have to switch into something else for a second. Maybe just reading papers, or I don't know exactly what to do, but I might need to switch from the programming stuff in a bit. We'll see. Just because I'm super tired today. I don't know what the deal is. But I will be trying to stream till 8:00 p.m. I'm really trying to make this be my standard stream time. So even if I don't have the stream stamina to keep going, I'm going to kind of push myself to keep going, and we'll see how it goes. On the other hand, I kind of realize how that could be a bad idea, because then people come in and the stream content's not very good. I don't know. I'm kind of 50-50 on that. Anyway, so let's think about it. So for what we could do today, we could actually do a number of different things. I realize I've been rambling a bit, so journal new page before. We could, one, work on color quantization, which is what I've been kind of proposing. Color quantization. Okay, two, we could go back to the fractal flame and improve the fractal flame methods that we had before. Again, the fractal flame method were the ones that were creating these images in here. There's still a lot of work to be done to make it more general and all that kind of stuff. And in particular, fractal flame videos, I want to make some fractal flame videos so I can understand how, for example, a fractal code could change with time. So that's something I'm considering. There's a lot of little things to do with that as well. Three, we could go full GPU engineering, and we could talk about histograms again, or parallel summations. Both of them are equally as useful. Or four, we could do other. I don't know what other means, but something like that. So let me go ahead and create a poll with these in there. Let's do new poll, and we're gonna do what are we doing with our lives? So what should we do today? One is gonna be color quantization. Color quantization, perfect. Fractal flame. The next one is going to be histograms. Parallel summations. Then let's see, what do we have here? Other. And I think we should be able to give the duration 2 minutes. Start poll. Should be fine. All right, so we'll give everyone about 2 minutes to vote in that poll, see what people have to say. Again, the idea is color quantization, which is the act of removing colors from a scene. Quite useful for the n-body simulations. Also, other will probably be more 4D galaxy simulations, I guess. I'm not really sure. So then we could do the fractal flame. We could do histograms or parallel summations, which would be more GPU engineering, or other. Let's see what's going on with the results here. We have so far 2 votes. One is for color quantization. The other is for, okay, we have histograms and sums. People really want some GPU engineering. That's going pretty well. In fact, let me just move this over here. Ooh, that is slow. Hello. All right. I need to change my video again. Let's go here, there, and there. Okay. This is what we got so far. I was like more people voting for the histograms and sums. You guys have about another minute left to vote. It looks like we're 50-50. No one wants to do fractal flame, which is surprising. I was expecting actually more people to want to do fractal flames, but that's fine. I guess here's the thing. Like fractals are one of those things that like I kind of feel are more. We got 1 vote for fractal flame. Sorry. Fractals are one of those things that I feel are like more. Like I don't know. I feel they're quite interesting, but then I think a lot of people are like they don't find them interesting. I don't know. Some people find them really cool, other people don't. See, now we're tied. All 3, which means I'm going to have to break it. So anyone that comes in can break it right now, unless you vote other, in which case you're not going to break it. I don't know. Maybe I even allowed people to vote multiple times. I'm not other. Of course. Because I told everyone to vote other. So for that person that voted other, what, oh no. Why are you voting other? What do you want? Histograms and sums? All right, that's fine as well. Looks like histograms and sums are going to take it. All right, histograms and sums it is. All right, let's do that then. GPU engineering. Oh, okay, I don't know if you can tell, but my computer is incredibly slow right now. Okay, yep. Perfect. Right. There we go. And now I need to modify this so that my video and audio is in sync again. Literally every time I have to move a window. Oh my gosh. Who voted for sums in the end? We could have had a 4-way tie. We definitely could have. Okay, so I'm going to change the stream title to be, I guess, GPU stuff. Let's just do GPU stuff then. So we're going to change the stream title to be GPU chat is what we're going to call it. All right, done. All right, perfect. Thanks, Mint Locust. Okay, so let's talk about some stuff. So there's 2 different problems here that we've talked about simultaneously, but they're actually 2 different things. So one is the histogram and the other is the sum. So what I want to talk about, so there's 2 things in particular I want to focus on. One is the implementation of these actions in kernel abstractions. So basically my question is the sum that we already have in kernel abstraction, so is the kernel abstraction sum already parallel? That's the first question I want to ask, because I actually don't know the answer to that. And 2, we're going to hop into histograms and explain why it's a difficult topic to like cover to any extent, but it's also incredibly useful for a bunch of different areas. So when I say parallel summation, question is, do you guys know what I mean by that? Is this still Julia? How does Julia handle GPU compute? Yeah, so Julia calls the CUDA PTX whatever library just fine. It's basically the same as you're going to get in C or C++. The only big difference between Julia and like C and C++ is that, well, there's a couple of big differences, but the biggest difference is that Julia tries to do garbage collection on the GPU, and it fails miserably at doing garbage collection on the GPU. So for that reason, like, you kind of have to deal with memory in a bit of a different way, but that's the only difference, really, just memory management. If I'm totally and completely honest, I don't like the fact that we have a garbage collector on the GPU at all. I think it's kind of dumb, but hey, it is what it is. So let's introduce the parallel summation problem. Garbage collection on the GPU sounds insane. Yeah, it is insane. It's absolutely insane. I don't know who thought that was a good idea. Does CUDA library also work with Python? There is, I think, like CuPy, CUDA.py or something like this that you can use. There's also, someone in chat constantly mentions there's like a bunch of other libraries that will do the parallelization for you and stuff like that. Yeah, so sum all the values together, but in parallel. Let's talk about why this is actually a hard problem. So let's say you have a bunch of numbers. Here's your numbers. Wonderful. Great. Amazing. Let me change it so it's white. So what you want to do is you want to sum all of these numbers together into one value, right? So you want to add 4 to 6 to 3 to 8 to 1 to 0 to 2 to 4, so on and so forth. On the CPU, this is relatively easy to do, right? Because you can take each individual value and just do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Totally fine. But this doesn't really work very well on a massively parallel device. Now, on a parallel device, you can still kind of work it fine, because you can kind of split it up into, like, let's say you only have 6 threads, then you could do 6 individual sums and add all those together at the end. That's not too bad. But when you're on a massively parallel device and you're trying to ask yourself, okay, how do we have thousands of threads, let's say 1,000 different threads, work on this array? Like, what do we do with it? Well, what you can do is you can split it up into a bunch of different vector additions. So you'll take this and basically say, okay, let's split it into 2. And what we're going to say is these chunks are all dealt with threads, let's say 1 to 100. And this chunk, our threads 1 to 100, which are going to deal with these guys, are basically going to do a single vector addition between this half of the array and this half of the array, right? And then you have half the array left over. And then you say, okay, we're going to do that same thing again. So we split it up into 2 here and also here, and we add those guys together. And then we have half the array again, and we split it up into 2 again. And so the idea is what we're doing here is we're taking the array and splitting it up into a bunch of vector additions. And the reason we want to do this is because vector addition is something you can reasonably do on a massively parallel device. That is to say, you can add all the numbers together, because all you have to do here is have a single thread deal with 1 plus 1, right? In general, when you're talking about GPU computing, there's a bunch of hard problems, and iteration is one of those things that you're almost always going to try to find a way out of iteration. So here we have to iterate through each value in the list of numbers, but if on the GPU you want to avoid that, right? Or at the very least allow yourself the opportunity to do the iterations out of order, right? But with a summation, I don't know, it's hard to do. So anyway, doing the parallel summation is something that you can kind of endlessly optimize. It's one of those problems that's like deceptively difficult to do. In fact, it's one of those things that most people don't recognize even is a problem. Like, for example, if you use TensorFlow, inside of TensorFlow, everyone's doing, obviously summation is such a common thing. It must happen a lot in TensorFlow, right? I was talking to some of my coworkers at MIT, and I mentioned that parallel summation is a difficult problem. I just said that because, naturally, if you do a lot of GPU engineering, like the first thing you learn when you're doing GPU engineering is the parallel summation, and you learn why it's a difficult problem. And, even though these people work with high-performance computing, work with high-performance computers, they deal with parallel stuff all the time, they genuinely thought I was joking. They were like, no way, like summation's super easy. I was like, well, no, I mean, it's not. Sure, okay, people can do it. It is easy in the sense that it takes an afternoon to implement, but like, it's not like you can just like, do 1 plus 2 plus 3 plus 4. It's quite difficult to do. So what I'm interested in looking at right now is seeing if the kernel abstractions library that we're using right now already has a parallel summation implemented, because I think, and I'm not positive about this, but I think that the sum function in a CUDA kernel that you can write on the GPU is already parallelized appropriately. So, but I don't know how they're going to do that. So I just want to see what happens. So I've been thinking about learning Sickle. I don't know what Sickle is. Well, if you have a lot of parallel sums, you can do each one in a separate GPU thread. In principle you could, but the threads are super weak. So this is going to be really slow, which is the case in a deep learning, as I understand. Oh, maybe that is the case. Actually, might be stuff I don't know. I should know a lot more about like machine learning and stuff, but honestly, I've never had the will nor the opportunity to look into it. It's one of those things that like, it's machine learning is the I don't know how to put it. Machine learning is the cosmology of the computer science world. It's this thing that everyone kind of thinks is cool, and it kind of makes me not interested in it. That's my problem. CubeBlocks 404. Hey, thanks for following. I've been working with SIMD on CPU lately a lot. Yeah, so SIMD stuff. So a lot of times when you do, so the GPU is not technically SIMD, but it's essentially the same. It's SIMT, which is like you just exchange the D for a T, which stands for thread, but it's essentially the same programming style. People who are going to be pedantic about it will be like, oh, it's technically SIMT, but it's like, fine, it's the same. It's literally the same. Okay, so let's go ahead and test some stuff on the GPU, see what we can do. James Durr King, hey, thank you so much for the subscription with the Prime. Let's go ahead and put a SimulCow in chat. Let's do SimulCow. Thank you so much. Really appreciate all the support. Isn't it still SimD? I think, I gotta be honest, I don't know the differentiation here. Let me do SimT versus SimD. Oops. SimD versus SimT. I'm so sorry. SimD versus SimT versus SMT. What is the difference? Single instructions, multiple data. Sure. But SimT is single instruction, multiple threads. Is the thread equivalent of SimD. While the latter uses execution units or vector units, SimT expands it to leverage threads. In SimD, multiple threads perform the same instruction on different data sets. I think it's the same. I think you can, calling it SimD, I think is fine. I think the difference here is that I believe GPUs all use the same methods. Yeah, I think GPUs, right. Yeah, I think you're right. Okay. Anyway, I still don't understand either, if I'm being totally completely honest. But I don't think calling a GPU SimD is technically right. But maybe it is. Maybe it depends on who you talk to about it. It's SimT, but with execution branching. SimD is SimT changes. Wait, SimD versus SimT changes whether the threads have to be inline when branching. I don't know. Actually, let's take a look at this. I don't actually know. So when I look at SimT, let me actually go to the GPU programming guide by CUDA. This is a good thing to look into because I always thought there was a thin veil between the two of them that kind of didn't mean anything. But maybe it does. Let me go to the programming guide on CUDA. They have a good website for this. This guy is probably what I'm looking for. And let me just search for SimT. So this is, I usually recommend this to people. When people are asking about GPU computing, I think that this CUDA development toolkit is actually super good at explaining all of the details for GPU engineering and stuff like that. Mention SimT, execute in SimT, programming, asynchronous SimT programming. Let me just look for this guy. Okay. And let's see what we got here. Multiple cores, threads with SimD, vector matrix instructions, and same instruction for multiple threads. Machine learning was coined in 1959. They're using 50-year-old statistics on larger data sets. Yeah, that's probably true. The truth is, by the way, root users, thank you so much for following. I just realized I'm super scattered today. I don't know why, but it's going to be one of those days where I might not be able to finish a coherent sentence. I'm going to do my best, keeping that in mind to stay focused and explain things as deeply as I can, but apparently I'm super scattered today. So asynchronous SimT programming model. Let's actually take a look at this because I'm interested. Okay, that did not, that's maybe a bit, Okay, let's just, let's search for SimT now. Asynchronous SimT programming model. Here we are. In the CUDA programming model, can I just do this? Okay, in the CUDA programming model, a thread is the lowest level of abstraction for doing a computation or memory operation. Starting with devices based on the NVIDIA Ampere GPU architecture, the CUDA programming model provides acceleration to memory operations via asynchronous programming model. The asynchronous programming model defines the behavior of asynchronous operations with respect to CUDA threads. So probably the reason I was so confused about SimT versus SimD is because I think this is what I read, and I was just, I just automatically thought it was different from the SimD, but maybe it's the same thing, literally the same thing. Branching can be done even in parallel by calculating both branches and then nullifying the result that doesn't happen. Same thing kind of happens with CPU for cache fetching. Right, yeah, this is something that we can do with histogramming stuff later. CPU SimD instructions can also do that. Okay, so what I'm going to do is go back, see if I can find a better source for the SimD versus SimT argument. That's not going to work, so let's try it again. Here, let's go SimD versus SimT. Look it up on Google. Okay, SimT and Warp, SimD versus SimT. I was hoping for something let's see what this one does. It's on the NVIDIA developer zone, so in principle, SimT is equal to SimD with multi-threading. Okay, sure. The Tesla is SimD architecture that runs the same kernel at a time. So let's see. CUDA-enabled GPUs are not strictly SimD. It's very similar, but with the SIMT approach, you can completely ignore the SIMT behavior and make branches, what makes developing much easier. Mathematics was invented in BCE. They're using 2,000-year-old techniques with faster calculators. I mean, I'm going to briefly talk about the machine learning stuff just because, look, the truth is I know next to nothing about machine learning. I've mentioned this before, like, I to some extent, I feel like maybe I should dig into it more because it is such a big field, and it's something that will almost certainly get you a job, all this kind of stuff. But it's just, I haven't yet found a problem with machine learning that I actually want to solve with machine learning. Does that make sense? Like, I haven't found a problem that machine learning is the best tool to solve. I haven't found a problem I'm interested in that machine learning is the best problem to solve. That's the actual answer. Now, that might change with fractal compression. We might find that with fractal compression, there's actually a perfectly useful and valid reason to use machine learning. But I just haven't found that yet. So that's where we're at. How to train your data dragon? Yeah, so like this is the thing. Like when it comes to machine learning, I know a lot of people love it, but that's what it is. Aphid1, thank you so much for following, by the way, a few minutes ago. What about generative art? Yeah, so in my mind, here's the thing. If you're doing art, right, I feel like machine learning is kind of cheating, right? Like the fun in doing generative art is creating an algorithm that can make the art for you, right? Flood fill, for example, is kind of in this way, or like doing color quantization tasks, or like all this stuff. It's fun because you create an algorithm to do the thing for you. Doing like stylistic art transfer, like it's cool to start, but it's like, why would you go further than that? Like, sure, it's neat to like turn yourself into anime via stylistic, via whatever, transferring the Ghibli style onto your own face. It's fine, but like it's kind of like, I don't know, it's like you're ruining the fun of doing the art. Like, don't get me wrong, it does create very impressive results, but like, TLDR of machine learning is universal function approximation. I haven't found a good case for machine learning. Well, ML is cheating. I think you're trying to call me out for being a hypocrite, but also I think it's completely right. I mean, like, the problem with machine learning is in almost every case I've seen machine learning used, specifically in high performance computing and physics and stuff like this. You have a better algorithm, or like it's better to have an algorithm do it, because machine learning will inevitably fail at some point. And like for vortex tracking in superfluid systems, you probably don't want to use machine learning for that, because like probably you want an exact result, and machine learning is probably going to give you the best result, but not necessarily. Machine learning is just a tool. You need to use it appropriately to get good results. Right, exactly. We had generative art abilities before AI. Right. I mean, this is the other thing. Like, I was looking into photomosaics and stuff like that, and it's like, oh, hey, photomosaics. There's a lot of really cool photomosaic algorithms. And I would rather look at the algorithms than machine learning, right? Because the algorithms are the fun part, You can do a lot of cool machine learning stuff, but all my research problems, if we had access to training data, we already can solve the problem. Yeah, so this is also kind of part of the issue as well. As far as the machine learning stuff is concerned, I genuinely see it as a useful tool. I 100%, it is a useful tool. Like, people will use it, and it will be useful for those uses, right? But what I wanted to say was that when I'm reading a paper and they claim that they have like 10 times faster results with this particular method or something like that, or like it's a physics result and they're like, oh, this is the first time people have ever been able to do this, I'm incredibly disappointed when in the middle of the paper, they're like, oh, we used a machine learning method. And I'm like, that's, you just took the thing that was super interesting because it was very difficult to do, and you gave me the wrong answer. It's clickbait is the problem, right? I think that's the reason I don't like machine learning. It leaves a sour taste in my mouth because it's like, when I read the paper, I'm really expecting like some new novel approach that I hadn't considered before. And then they're like, we use machine learning. And I'm like, come on, just joined. From what I understand, you can't use machine learning from nothing, right? Yeah. So you have like, different types of reinforcement learning, which are in the machine learning umbrella, you could say, which, mean you don't really need the training data, this kind of stuff. The only real use for machine learning I see is basically to learn from humans. Yeah. So like, you've got a lot of computer vision tasks and stuff like that, which are really, really cool. And like, machine learning definitely aids that, you've got a lot of AI stuff that's really cool. Like all the deep learning stuff, super cool results coming from this. It's just that it's just, it bugs me because it's like, you're right. Machine learning solves hard problems, right? Sure. You're right. It's just that with that comes a lot of like, you can't really rely on it. Okay. I'm also coming from a physical perspective here, but like if you use machine learning to solve a physics problem, like you can't really trust it to extrapolate up into higher dimensions and stuff like this. There's a lot of things that, you can't really, you don't see its internal structure. You don't know what's going on the inside. So you can't really like trust it for like all the results you need for the physics simulation. It doesn't make a good model, The key difference between SIMT and SIMD lanes is that each of the SIMT cores may have a completely different stack pointer, right? And thus perform computations on completely different data sets, whereas SIMD lanes are simply part of an ALU that knows nothing about the memory per se. Right, that makes sense to me. Neural nets don't really do extrapolation. They just fit your data set and don't go past that. Right. And most of the times when you're looking for a method, you're looking for a new algorithm, you're looking for, an analytical expression for something. In my mind, you're probably also looking for something that can extrapolate, right? You're looking for a new theory or something. Anyway, it's kind of weird because stack pointer is just more data. It doesn't make sense to me. I got to be honest, and this is where I might draw the line. I actually don't know a clear difference between SIMT and SIMD, you can't trust it to extrapolate into higher dimensions. Just get data from higher dimensions and train it again. Well, that's the thing. You can't get data from higher dimensions, right? Like clearly you can't, right? Maybe you should just give it a try and see whether you could come up with a novel approach or optimize the current approach. Right. See, that's why I don't like machine learning, right? Exactly that. Because like what ends up happening is that you run into these situations where it's like, oh, here's a cool novel photomosaic algorithm. Here's a cool way to do this. Here's a cool way to do that, right? All this kind of stuff. And like, you're missing out on that when you just use machine learning for this, right? I guess my problem with machine learning is that it's overused. I think that's the truth. And again, that means it's incredibly successful, right? It's like, that means it's incredibly successful and it's incredibly useful. It is an incredibly useful tool. I agree with that. It's just that it's the same thing with like, I don't know. And you could argue maybe I don't like it because it's competing directly with the type of things that I like to do. I get that as well. I don't know. Anyway, the point is, I don't like it because it ends up just being like, it ends up just like taking these interesting problems that have, been very difficult to solve. And then it's just like, here's machine learning. We're using a big black box for it in the end. And I'm like, come on. Like you could have tried to solve the problem at least. There's all these other ways you could have solved the problem. And then you're just like, machine learning is the be all and end all. That's what we're going to do. And it's just, I don't know, it just bugs me. I can ramble about this all day. And the truth is I'm rambling from a place of ignorance because I genuinely, as I've said before, don't actually know much about machine learning, except that when I see it, it frustrates me. I didn't read about the IBM quantum computer. Did someone learn? And can TLDR me? As far as quantum computing is concerned, I mean, I know a lot of people are super into quantum computing, but I also, it's one of those areas that I need to learn more about. The really cool ML stuff is unsupervised learning. Yeah, right. I understand this as well. Human understanding of mathematical models of the universe seem to be reaching a limit. People can't even figure out what should be the basic stuff, like the Collette's conjecture. This stuff I don't really care about. Time to give ML its chance. Well, I mean, ML is what do you think ML is? It's still math. Like literally, deep learning is just taking an n by n matrix and learning the weights. It's just Hebbian learning. That's all it is. It's not like anything more complicated than that. Like, sure, you can add a lot of stuff to that, and reinforcement learning sometimes works differently than that. But like, a neural network is literally just learning weights to an array. I mean, that's all it is at its purest sense. ML is the panacea. That's like a cure-all, right? Well, that's the problem, right? Like that's how it's kind of treated. If you branch, you do both sides, the branch of every time, filling the branch, you not taken with OPs. Actually, I have no idea what you're saying. I'm so sorry. If you branch each thread, branches separately. Well, the Collette's conjecture is non-trivial. We should dedicate all of our resources to finding all the digits of pi. Funny story about that. So we opened up a new cluster at Auburn University at some point just for basic computation. And apparently, one of my professors was doing a pi calculation just to check to see how it did with computation, benchmarking and stuff like that. Accidentally left it running all night and used up all the data on the cluster just calculating pi. Let's see, what do we have here? We should, okay, as was Fermat-Wiles theorem, ML is math, but it doesn't depend on human understanding. ML is just leveraging CPU power on a huge data set, and that's great. Most ML is not Hebbian, it's gradient descent. Fair. But it's not applicable to all problems. No operation. Oh, I see. Anyway, I see people are pretty mad at me, and that's fine. I'm sorry. Look, the truth is I just don't care about machine learning. That's what it is. Like, that is the truth. At the end of the day, I don't like it. It takes all the interesting problems that I like solving and makes them not interesting to me. That's what happens with machine learning. I mean, like, it's my opinion. Probably down the road in like probably a few months, I'm going to look at machine learning in a completely different way. I mean, I did the reinforcement learning classes, I did the all that kind of stuff in graduate school. As you know, it is what it is. It doesn't sound like people are mad at me. Sounds like a good discussion. Yeah, that's fair as well. It's just that, I don't know. The truth is, I'm going to say this again, and this is just the end of the discussion for me. I just get disappointed with machine learning. I just get disappointed by it. That's why. Like, it's just like every time I'm reading a paper, when I see machine learning, it's like, man, that was a waste of my time. Because like, of course you could use machine learning for this application. Like, everyone knows you could use machine learning for this application, but it's like, why would you? Like, I mean, it's like, fine, you just ruined the fun of the paper. You're doing GPU. It's only a matter of time before you sucked into the ML world. There are a lot of people who do GPU that are not doing machine learning. In fact, the entirety of GPU, I would say if you're doing GPU, you're probably not doing machine learning. So anyway, see you in 5 minutes. Because if you're doing GPU, like if you're actually coding in CUDA and you're doing all of this stuff, you're probably not using the machine learning tools. Maybe I'm spoiled because the only ML papers I've read like that are the self-examination. So they have cool ML application and they look at the internals. Well, yeah, okay, to be fair, right? Like, this is the problem. Machine learning is a hammer, right? And when you have a hammer, everything's a nail, right? That's the phrase, right? So people are just constantly using it and feel that it just doesn't belong is a problem. But you said it's the end of conversation, so I'll stop. Yep. I mean, we can keep going. It's fine. I'm just saying that, like, you're talking to someone who just doesn't really know what they're talking about, right? Like, I don't know what I'm talking about, and I'm biased. So I'm the worst person to talk to about this type of stuff, I love GPU computing because I love the parallel tasks. I love doing parallel summation. I love doing, the histogramming stuff is super cool. All this kind of stuff where you're trying to take a naive operation that's incredibly easy to do on the CPU and make it faster on the GPU. I love doing that. It's just super fun. I really enjoy it. And yeah, I don't know. I mean, the truth is machine learning is such a huge umbrella. Like, it's just so many different, like, various topics are covered with machine learning, right? And like, you've got also different hardware as well, like the IBM True North chip, for example. Whatever came of that? Like, people were really into it for a while, and then all of a sudden cognitive computing just kind of died. It is called cognitive computing, isn't it? Is it even so CC refers to technology platform that, broadly speaking, are based on scientific disciplines of artificial intelligence and signal processing. At present, there are no widely agreed upon definition for cognitive computing either in academia or industry. In general, the term cognitive computing has been used to refer to new hardware and or software that mimics the functioning of the human brain. Yeah, so this was interesting. I was really interested in the in cognitive computing hardware was something I was super interested in a while. Machine learning saying, screw optimization, let's just throw a ton of matrix multiplications at it until it sticks. Yeah, well, to be fair, that's some machine learning. Again, that's not for everything, but that's kind of the vibe that you get, Anyway, this is one of those things that, people have a lot of opinions on, the only reason people have a lot of opinions on it is because it is a big thing. It is this thing that is changing how we perceive the world around us, in a sense. And that means it has been massively successful in what it's trying to do, right? That means it is a good thing to have. It is a wonderful tool that's really changing the world, and that's good. The fact that we have so many people talking about it and hyped up either on one side or the other side of the spectrum means that it's doing good things. So that's kind of where I feel. Machine learning is different than human learning. So far as I know, it's not. But I mean, you can argue maybe. But it's essentially just doing human learning in hardware is essentially what it is. Really interested in studying sparsity in machine learning, so you can use way less flops than RAM. That's an interesting thing as well, right? Like, and that's the thing. Like, I think the primary reason why I get upset with machine learning is that I only see machine learning in fields that I don't want to see machine learning in. So, like in physics, or some areas of computer graphics, or like biology or chemistry, these areas where the point of the model is to extrapolate further. You know, like the point of a physical model is so that you can use a physical model in places where you can't do an experiment, or in places where you cannot do an analytical calculation, right? So it's in like the mean field regime and stuff like this. And in that case, you really don't want machine learning there, because if you put machine learning there, again, it can't really go that much further than what you've given it, you know, what systems you've trained it on, this type of thing. And so you don't want to see it there. And so what you end up seeing are all of these papers of machine learning badly optimized to a problem that it's not really suited to solve. That's what ends up happening. So it leaves a bad taste in my mouth, specifically because it's like, all I see are applications, and I see bad applications, not applications where it's actually, you know, properly utilized, right? But I feel that if I actually dug into machine learning and I was trying to optimize, you know, machine learning methods themselves, then I think things would be entirely different. The stuff you're talking about right now, 2Curbs, I think that actually sounds really cool. And a lot of these kind of like lower level applications, I think are quite nice. It's just, you know, when I see it randomly in a paper that I didn't want to see it in, it's all of a sudden like, come on, man, like, why'd you do that? I don't want to have to touch machine learning in the middle of this paper on, you know, like a completely different topic. You know, AlphaFold seems to be in the state of the art, very clever techniques. Anyway, I'm gonna be right back. Give me about 2 minutes, and then we will get started on the just kind of poking around with the parallel summations and doing some GPU engineering and stuff like that. I'm sorry, I know CropEb is gone, but I wasn't really able to finish the SIMD versus SIMT discussion. Clever technique, but what is the result? Right. I mean, that's the thing. The results for the papers that I look at are usually less than stellar anyway. Like, they're basically trying to find a way to use machine learning in a new field. And that's why I tend to feel like it's kind of not useful, right? But I mean, look, you got people who are like, you got really intelligent people saying that like AI is going to take over the world. It's like, fine. I mean, that's probably true, but I just don't see how the machine learning models that we currently have can get us there. I feel like we need something else, specifically new hardware that like better caters to the machine learning methods, because we have GPUs, but like right now, like GPUs are, I mean, they're fundamentally limited in what they can do, and machine learning, it's only a matter of time until like we get dedicated hardware to do the machine learning for us that is better, which is why cognitive computing is actually a really interesting area of research that I really want to go into, or I was really interested in going into, and I wanted to do for my PhD, actually. During the first year of my PhD, I did a rotation in the neurobiology research lab at OIST, and we actually built ourselves basically a single core to what could become an analog electronic brain is what we were trying to build. It was quite cool. I really enjoyed it. And I would have done that for the PhD if I was, you know, more sure that it was going to go somewhere, that was actually going to be useful. But in the end of the day, I chose to do the project that gave me GPU computation capabilities, because frankly, that looked more promising at the time, and gives me more options and all this kind of stuff. Okay, guys, I'm gonna be right back. Give me about 2 minutes, and then we're gonna hop into the GPU engineering in just a bit. Give me a second. Sorry about that. Okay, I'm back. Sorry about that. I'm hoping for no training ML models in the future. But wouldn't a no training ML model just be a model? Like the training is core to the ML, isn't it? Link the texture synthesis paper I linked above. I don't think I got that link. One second. Could you link it again? Because I think I completely missed that. I'd be happy to read it. Also, guys, I'm happy to have a discussion. Maybe instead of talking about GPU stuff, I want to do the GPU stuff, but we could just have a discussion about machine learning. This could be a day where I just catch up on some machine learning stuff. If you guys send me papers, I'm happy to go through them, and we can just kind of do some intro to ML, like learning machine learning for the first time type of thing. I'm happy to do that. So, AlphaFold is currently the best at predicting how proteins will fold, as I understand. That's what I meant by state of the art. Oh, interesting. How is it help in the context of diseases? It's not really a paper. It's like a link of a bunch of other papers. Oh, okay, I see. I don't really understand. Let's go here. Are we talking about protein folding? Protein folding is a very interesting, like biological application. Like it's one of those things that like, it's one of those things that like a huge number of people would love to have, like a good protein folding algorithm. It's useful for, I gotta be honest, I don't know why it's used. I just know that a lot of cluster space is used for protein folding. Zernal PP, let's go to downloads and texture .pdf. Oh, I see, it's a series of slides. Texture synthesis. Let's see, what do we have? Markov chains, Markov chain example, text synthesis, modeling texture, Markov random field, texture synthesis, synthesizing 1 pixel, reading synthesizing 1 pixel, really synthesizing 1 pixel. Interesting. Combining 2 images, yeah, that's fair. Oh, it's using, yeah, GraphCut, that's fair as well. I see. That looks like homework, kind of in a way, right? They can use protein folding to figure out which proteins might perform a particular function in a cell before actually synthesizing them in a lab. Yeah, that's fair. I mean, this is the thing. Like, I know of the methods that, like, for example, for a lot of bioinformatics, they use a lot of like string matching or string, what is it? String distance, edit distance algorithms and stuff like that, which is quite useful. But I don't really know. So it makes drug discovery process faster. Yeah, it could be. I really don't know. Okay, so let's go here. Let's go ahead and remove these. Delete here. Okay, so here's what I'm going to do. We are going to look up specifically the sum function. So I'm going to cd into project Simuleos GPU. ls here. Let's go into vi test .jl. There we go, JL. And I'm just going to create a new test, and we're going to mess around with the sum function in Julia and see if we can get this to work. So what I'm interested in doing is seeing if a parallel summation is already implemented in Julia. That's number one. And so to do this, I think we're just going to try to see what happens. So we're going to do Julia here. I'm going to create using CUDA, and we're going to see where this brings us in source code. Kind of mess around a bit. It's just showing how stuff done via neural nets can be done directly from source data. I see. Interesting. Okay, so let's go ahead and say A is going to be equal to Q array of, let's do ones of 100 or something. 1,000, sure, that'll work. It can also help guess what existing proteins shape is and what they do, even when they haven't been studied with crystallography yet. Yeah, so let's go ahead and go here and let me do at edit sum of A. Okay, so this brings us to Julia-based reducedim.jl, which is not great. And this brings us to an abstract array. So this says to me that we don't have a sum directly on a Q array. Let me see what happens if we run sum on A. What does that do? It's certainly taking its time, isn't it? Let me try doing this with allow scalar equals false, or whatever that is, which would basically inhibit us from ever transferring data to the CPU. So I suspect what's happening here is it's transferring data from the CPU, from the GPU to CPU, doing the sum, then transferring back. I'm not entirely sure, but I want to see, just check to see what's going on here. So this is one thing that, like, one of the big differences between the Julia and C code. In the C code, I'd know immediately what's happening, but in the Julia code, I have to dig a bit. Protein folding will always continue to be useful as long as we want to discover or study new proteins. Okay, so this one took no time at all, but that's because the compilation was done. So let me go ahead and do CUDA.allow, what is it? Isn't allow scalar? I thought it was like allow scalar, what is it? Oh gosh, I don't remember what it is. Let me go back over here and let's just go to CD projects, kernel abstractions, L is here. Let's do grep -rl scalar. Control C, scalar, see what we got. So we're going to go into VI examples and then matmul, sure. And let's look for, it's CUDA.allow scalar false. I thought I was just looking at that. Okay, let's take this over here, paste it here. Okay, so now we have that. Now let's just try doing sum of A. Seems to still work. So here's my question. Where is the sum of A defined? That's what we need to figure out next. So let me go into @edit sum of A. A is a coup array. This is going to call inline function name of abstract array with dimensions and keyword arguments. Where is that doing anything? Let me go into the CUDA Julia, maybe Julia GPU is what I'm looking for. And let's see what we got. Wait, what's going on? They get data from historical genome. Wait. If the president, wait, I missed a lot of stuff. Protein folding, if the president has diseases and they don't have his data, then which drug discovery is it for? Wait, what? I don't know if I understand the question. They get data from historical genomes and data about crystallography, studies on proteins, but who gives them? You didn't answer my question. Scientists publish the data. They are, let's see, it provides private, isn't it private data of patients? No, this is for specific proteins, not for person's genome. Right, so I don't know how it's actually useful for drug synthesis is the thing. I don't know if it is useful for drug synthesis, but I feel it is like particularly useful for a lot of like basic biology applications and stuff like that. But obviously 2Curbs knows way more than I do. I'm sorry, I'm rambling about stuff I don't really know about. Again, as has been the history of this stream, I'm just rambling about a bunch of stuff I don't know. So let's go ahead and go to learn here. Let me go to the CUDA.jl documentation, and let me just go ahead and look for sum. CUDA.memory allocate, CUDA.advise, conditional use. I feel like someone really needs a good parallel summation. So let me see if I can edit this on GitHub. Here we are. And let's go to CUDA.jl, and let's see what we have here. Examples, pairwise, peak flops, vector addition, hello world.jl. Okay, let's go back. That's not going to help us very much. Source wrap, source test. I'm looking, maybe it's under source, and then maybe it's going to be under array.jl, maybe? Maybe I just bring this locally and I just grep it, see if there's a sum function defined. Let's just do that. CUDA.jl, let's go ahead and grab it. Where are we? Code here, why am I stupid? Grab this, and let's go over here. So this is the basic Julia code. Let's go ahead and quit here. Control D, CD back a directory, back one more directory, git clone this guy, and let's go. It's useful. Let's see. I missed a lot of stuff. But for each person, their protein's different. Their protein is different. So how is it even useful? It's good for coming up with better candidates for drug synthesis, making the process cheaper and faster. 98% of everybody's proteins are the same, right? If they are the same, then how some people have diseases and others don't. And maybe protein folding isn't what we need. Different expressions, rare errors, maybe some other things, right? I mean, to be fair, like these are, I guess, pretty good questions. But I don't really know much about this. Most diseases are not genetic in nature. Okay, let's go here and let's go ahead and cd into CUDA.jl. CUDA. L is here, and let's do grep-rl sum. Right. Yeah, I don't know why I expected anything different than that. But it looks like we're calling cuBLAS. So is there a cuBLAS implementation for sum? Let me see. So cuBLAS is here in test. So cd test ls vi cuBLAS.jl. Let's go for sum here. Oh, okay, that's not. Let's see. Sum. Okay, let's try something else then. Let me do, what can I look for? Let's go to source. And let's do grep-rl sum. Okay, so we've got MapReduce. That's what I'm looking for. Vi MapReduce.jl. This is exactly what I'm looking for. Reduce warp. Good. So there is a good implementation for this function in CUDA. Now the question is, how do I call it? Do I need to call specifically MapReduce? Let's do CUDA.map. It's not available. Okay, so how do we call MapReduce then? So let's do grep-rl MapReduce. Okay, so this is going to be test array.jl, vi test array.jl MapReduce. Here we have MapReduce, two-step MapReduce. So we have at test vector array is going to be the sum view of CUDA zeros, CUDA.zeros of 1, 1, 1, 1, CUDA.ones equals, what is this test doing? But it looks like some exclamation mark might be different than just some. That's interesting. Huh. What do we have here? Different questions, rare errors, maybe some other, I missed a lot of stuff. If they aren't genetic, then what are they? Local disease. How is protein folding trying to fix diseases? Virus, bacteria, did you take high school bio? So protein folding is to solve bacteria problems, it can, or viruses or COVID. Discovering new proteins can cure diseases that are not from a person's genetic defect. Simply feed them or inject them the right proteins, and they do a job in the body. I took high school bio, but it wasn't I took high school bio, but it wasn't existing back then. Interesting. Okay, so this is a test that is basically creating a vector. Oh gosh, let me see what's happening here. So they're creating a vector, okay, which is an array, okay, which is a sum, okay, of a view. It's a sum of a view of CUDA zeros 1, 1, 1, so it's just a 0, and 4,096 ones, and you want to make sure it's equal to 4,096. That's fine. So that means we have a sum function. So let's take a look at Julia, and let's do using CUDA. And now we're going to do CUDA.sum. There's not a CUDA.sum available. Let me do A is going to be equal to this guy, and let's try doing some exclamation mark on that, see what we can find. Some at edit, some exclamation mark of A. No unique match found. Okay, so I can't do some exclamation mark of A. That's not a thing. Okay, that's not a thing apparently. Crap. We're on a journey to figure out how we can call a sum function from Julia's CUDA internals. Well, CUDA internals, I don't know if that's the appropriate word or not, and we'll see where we go. I mean, this is going to be interesting. Protein folding can be used, for example, to study the shape of COVID-19 spike protein, cheaper than crystallography, and then you can use that to figure out defenses. Wait, is it actually cheaper than crystallography, including compute time? I thought compute time was like incredibly long for these studies. I'm sorry, but what makes it doesn't make sense? I thought it makes a lot of sense. Could you explain what the problem is? Let's see. Eating proteins doesn't sound like it would work. Doesn't the stomach destroy it? Wait. We're talking about like, I'm so sorry, two curbs. It sounds like you're like arguing with a bunch of people. And like, just for the record, I realize it's a productive discussion, but also like, I'm sorry that like, there's so many questions about like crystallography and like protein folding and stuff like that. I feel like, I mean, I appreciate that you're here and like lending the advice, but also I feel like there's a lot of people asking a lot of questions to you. So if you don't feel like answering, that's totally fair. But I appreciate that you're lending all of the expertise here. Okay, so let's keep going then. This obviously doesn't exist. I don't fully understand what happened with this error message exactly. Yeah, I don't know what's going on here. So it looks like we have to sum two abstract arrays. What is MapReduce? What is MapReduce even? Julia, let's do MapReduce. We have MapReduce. So how does this work? Let's do methods of MapReduce. Or maybe question mark MapReduce. All right, let's see, what does this do? Scroll up a bit. Here. So MapReduce of f is applying function f to each of the elements in ITRS and then reduce the result using a binary function OP. Cool. So this is essentially like you can take all the elements of A, multiply them by 2, and then add them all together or something like that. If provided, init must be a neutral element for OP. Okay, so MapReduce is exactly what we're looking for the parallel sum. There's a separate MapReduce created for CUDA, and if you call MapReduce, it should call the CUDA MapReduce is what it should do. So let me see if that actually does what we expect it to do. So we're going to define, using CUDA here, we're going to define A, and then we're going to edit the code for specifically MapReduce. Now that means we have to have a MapReduce call, and we might do this one. Okay, x2 plus, sure, that'll do. So let's try calling that first, just to make sure it works. Perfect. And now we're going to do this of A, see if that works. A is not defined. That's because I didn't define A. Let's try it again. And then we'll try it one more time. We're going to do this. Hopefully it works. And then we're going to try to call the edit it and see if this pulls up the Julia, the CUDA code. Sorry, the MapReduce thing, I was just trying to look at the actual source code here. Sorry. Depends if you consider the per microstate. Much cheaper than crystallography. That's interesting. I thought the compute time, I guess I don't know how expensive crystallography is then. I thought it was just like, and maybe this is what I don't know. I don't know crystallography at all, but I thought it was just like, you look at it under a microscope type of thing. Some it destroys some protein. If you consider the cost per microstate in an ensemble structure, computational is cheaper usually. Yeah, if you don't feel answering, that's fair. Just dumb asking lots of questions. Yeah, I mean, I actually really appreciate all the questions being asked and all the answers and everything, but I just feel like, you know, there were a lot of questions towards two curves and he's the only one that could answer, or they're the only one that could answer it. MapReduce is programming paradigm. Okay, so let's edit this guy. Edit, let's see what we got. Hopefully this brings up CUDA MapReduce. This brings up base.MapReduce, which is A of any GPU array, which is an abstract array. So where does this call? Is equal to underscore MapReduce. So let's look for underscore MapReduce. A function underscore MapReduce is here, which is going to say, this is a problem. Whenever I look at this code, it just gets super messy. Okay, so we do BC. So MapReduce should apply F like map does, consuming elements like iterators. So how is this linked to the CUDA stuff? I guess here's my question. If I want to do a parallel summation, right, I guess I can just call a MapReduce on a GPU array, and then I can read that reduced thing into a kernel or something. So in principle, what we found here is that the sum function is optimized appropriately. So I think what I should have done is I should have just done a performance benchmark, and I should have just checked, hey, is this actually running on the GPU or is it doing something else? That's what I should do. That's exactly what I should do. Perfect. And this will just let me know if we have a performance sum function written in Julia that we can use. At the very least, we see an implementation that we can work off of. So that's a good step forward. Let's see. Yeah, I guess I don't know what crystallize means. Oh, I'm so tired. I'm so sorry. There might be a sense for someone, yet protein folding isn't here to give the solution but an answer. So we're still far from solving any disease. Yeah, you also usually write a lot of protein samples, waste a lot of protein samples to get a good structure in crystallography, which is often a hit and miss process. Oh, okay, right. So I guess I see now. I guess let me Google crystallography, because I could just ask, I think this is what it is, but let me just Google it. Like, I have the internet. A lot of my friends did crystallography, and I just never actually asked what it was. It's the experimental science of determining the arrangement of atoms in a crystalline solid. The word crystallizing is derived from the Greek word kristallon, a cold drop, frozen drop, with its meaning extended to all solids in some degree of transparency, and graphene to write. In July 2012, the United Nations recognized the importance of the science of crystallography by proclaiming that 2014 was the International Year of Crystallography. Cool. So this is essentially the act of creating some sort of structure, like figuring out the arrangement of atoms for like a protein or something like that. Sure. good. That's fair. Which would make sense why you have to do a bunch of different, it would make sense why it's a finicky thing, right? Because you've got to make sure that they're, you probably have to like measure it multiple times to get the right answers, all this kind of stuff. Okay, cool. That's enough for me. See, this is stuff I should know more about. Like, I know that protein folding is a big deal, right? I know it's a big deal because I see it all the time. I don't know any of the experimental techniques. Right, and they don't crystallize well. That's probably fair. Okay, so now what I'm going to do is do some very quick benchmarks here. So we're going to do nsys launch. Sure. nsys launch Julia. That'll do. Let's do using CUDA. And let's just do an app profile. Let's see what we got. Ringo Mar, hey, how are you? I can't even crystallize cooking salt. What does that mean? Okay, let me do, what am I going to do next? Let me just do a quick, A is going to be equal to Q array of, and let's do 1,000. I think I can do 1,000, 1,000, 1,000. Maybe that's too many? I bet that's too many. How much? Let's do 2,000, 2,000. Something like this. There we go. Error. Oh, I'm an idiot. We try that again. Should be like ones or something. Of this and that. Perfect. Okay. It's a giant array. Let me check my GPU memory really quick. NVIDIA SMI. Okay, so it looks like we're actually not even using that much. Let's make it even bigger. 4096 by 4096. Sure. This is now using, really? I would have thought by now we're using a lot more data than that. 1 second. So this is 693 megabytes. How much more can we use? Can I do 1,000 by 1,000 by 1,000? The answer is no. Yeah, no. Memory, I'm trying to allocate 7.45 gigabytes. I cannot do that. I should have known. So let's do 200. Okay, so I was able to generate that. We should be using most of my GPU memory now. Oh, I'm not watching it. That's why. Okay, that's what I wanted to see. Perfect. So now what I want to do is just sum of A. This should work just fine, and then we'll go on it from there. In life, you need to learn one thing and focus on it to later work on it. I found myself interested in some subjects, some I can't understand, but I wish to work on. And also, I think most people can just get tired after working on something some years. That's fair. Never saw cooking salt crystals. Maybe I did. It might have been a long time. They look pretty on Wikipedia. Sodium chloride. 1 second. I'm checking to make sure that I'm not like lagging or anything. I think I might have done this before. It's been a long time. I used to do the thing where you'd put like, I think you just put like salt in a closet or something, and you can make, I mean, I've seen this before, right? Let's see what we have here. Open this, paste there. That would be salt. Oh, sodium chloride. Yeah. So to be fair, like I always thought it was a bit mean, the whole sodium chloride thing. All right, let's go here and let's do CUDA.appProfile sum of A, and let's take a look at the profile results. And hopefully we have an optimized sum, and then this is going to be our, this will show me at the very least that we have some sort of sum that's working on the GPU, and we can go from there. So let me get a little bit more water. Hey Cropeb, how are you? I hope you're doing okay. So we got this. Let's go and do a Control D, and now let's do nsite sys. 1 second, and then report 1.qdrep. And let's see what we got. So we're going to, yes, so we have this big parallel sum in here. So if we go to show an events viewer, we see partial map reduce grid here. Perfect. That's what I wanted to see. Just wanted to make sure that it was, if we do a sum on a Q-array, it's actually working appropriately. Now, what this could mean is that we probably want to launch multiple kernels when we actually have to use the sum. So let me think. Do we actually need to implement the map reduce? Can we actually put that into a kernel? The answer is probably no, right? Probably we can't just use sum in the middle of a kernel abstractions kernel. So let me try that. I'm pretty sure this one's not going to work, but I'm going to give it a go. Yeah, I'm pretty sure this one's not going to work, but I'm going to give it a go and see what happens. So we're now going to create a quick test where we put sum on the inside of a kernel abstractions kernel and just see what happens. I know it's going to break, but I just want to see if it will work, because if it does, that solves some of our issues, and it means that I don't have to do some computation, which would be nice. So let's go ahead and do remove report 1.qdrep, cd back into GP, where am I? Simuleos and then GPU. Okay, ls here. And then what I want to do next is just create a new test. So we're going to cp test2 into test3.jl. I'm going to vi test3.jl. We have +1 +2. This is just testing function pointers and stuff. Okay, so here what I'm going to do is the following. Just tid is equal to this. I'm going to see if we can do sum of input. Probably can't, but I'm just going to check. You know, what's the worst that happens? This fails? Fine. I just want to see what happens. So then I can just do write and quit here. By the way, Jesus farted. Hey, thank you so much for following. Really appreciate it. Okay, so let's go into one second, end site sys. Well, let's just launch it. It's probably not even going to work. Julia, include test 3.jl, and then we're just going to see what happens. So again, I'm pretty sure this is going to fail, but I want to test it. So we have ftest here. So I think it just runs on A, right? Vi test 3.jl. Oh, reads an F2. Nah. Just needs to read an input. Let's remove this as well. And then go down here, remove this. And let's go. Perfect, write and quit. Let me do control D. I'm dumb. That's okay. We'll just use this terminal. I accidentally deleted the terminal. All right, we're going to cd into projects, Simuleos, GPU. Ella's here, Julia. Now we're going to do include test3.jl, and we're just going to run it. See what happens. I don't know. I have no idea what's going to happen. So now we're going to create an input, and we're going to say A is going to be equal to this guy. It's a giant coup array, and we're just going to read it in. So we're going to do wait on test exclamation mark of A. See what happens. No way this is working, right? No way. I mean, how would this even work? They would have to... Anyway, let's see what happens. We're going to wait on this. An error. Perfect. Illegal memory access was encountered. That was not what I was expecting. Let me try making a smaller A, and it just be like 1,000 elements. Okay, my GPU is dead. Perfect. Let's try it again. So we're going to do include this guy. We're going to create A. It seems like there's something wrong with the encodings. What encodings? Are you talking about... Wait. With the stream? I thought about adding a GUI with some sliders for my Rust Galaxy simulator. Needs a lot of iterations. I find it interesting looking... to find interesting looking parameters. Yeah, to be fair, that's definitely true. There's a lot of like the twiddling of the different parameters to make it look pretty and all that kind of stuff. The character encoding in your terminal? Is there... Wait, is there something wrong with it? Seems like there's something wrong with the encodings. This stuff up... Wait. You can still read it okay, right? Or is there something... Let me check. I should have quality options as well. Yeah, you have multiple quality options. Let me go here. Let me do A is going to be equal to just 1,000 ones. And then let's just run it from there. Okay, so we're going to do this guy and see if that goes. I think it's still going to fail. When you made the Julia array. Oh, right. Yeah, there's... Okay, I need to look back at that error. The error here is that... Oh, just for Pete's sake. Okay, so this actually works. That actually worked, which is surprising. Oh, hello. Oh, this guy. Yeah, I see. Yeah, I'm using Unicode. Fine. Let me do this again. Let me make this big. I'm using the wrong terminal. I sometimes open terminals without Unicode support just because I don't like Unicode, and it bothers me that when It bothers me when we have Unicode. I just don't like it. CD Projekt, Simuleos, GPU. Okay, let me do some... I don't understand the illegal memory access exactly. But let me try running this again and see if it breaks. So Julia, and we're going to do include here. And now we're going to say A, and we're just going to make it 1,000 by 1,000, see what happens. First, I tried to use real numbers for averaging star mass and distance from Milky Way, but I guess to work out, it needs more than 1,000 stars as well. Yeah, it needs like a couple billion stars. Let me see, I have the actual number here. It has to do with, oh, how many is it? It's in this paper. I'm looking at it right now. Oh gosh, I don't know. With 100 billion stars. So 100 billion stars is how many it needs. So using real units here might not be exactly useful, unfortunately. Let's create A and let's make it a 2-dimensional array. Okay, and now let's try calling our kernel again. See if this works. Because there was an illegal memory access before, and I'm not sure exactly why that was the case. So we might have to look into that. This would need some time to calculate. Yeah, definitely. Definitely some time. Also, according to this paper, it takes 18,000 GPUs. Illegal memory access was encountered. Interesting. Query is done. Throw API error, CUDA error enum. CUDA error, illegal memory access was encountered. On a synchronize. Really? Okay, let me mess around with this a little bit more. I wonder if it can work on a 2D array. If I create a new array now, I think it'll break. Yep, in a similar way as before because of the illegal address, which I don't know how to fix right now. So let's just do Control D. Do it one more time. Julia, we're going to include test3.jl. We're going to create a new array. This time I'm going to make it exclusively one-dimensional because a one-dimensional array did work last time. But I'm just going to make it 1,000,000 elements in one dimension. So A is now going to be 1,000,000 elements in one dimension. And we're going to try it again and see if we get the same illegal memory access. In principle, we should, but I'm just double checking. Here, so we should get an illegal memory access here. I'm not entirely sure why we're getting an illegal memory access or at what state we get the illegal memory access. I could just create like a quick for loop that just goes through all the values until eventually we have too many. I don't know. We'll figure it out. Okay, so this also broke, which is good. Encoded code 700. Initialization.jl, stream.jl. I could look at a different GPU layer of debugging. You're getting this illegal memory access when creating a new array after the first one. Yeah, so the first one here, and now if I create a new array here, it's going to break. So this is going to give us the weird, this thing, which I just, honestly, I'm not going to, I don't know what's going on here. Error running finalizer, CUDA.Q error, all this kind of stuff. So let's go ahead and Control D. Okay, and then we have all this. So we essentially segfaulted out. CUDA error, run finalizers. There's something wrong with like finalizing the array or something. Maybe I'm out of GPU memory somehow. I'm not entirely sure. So what we might want to do is like look at a different debugging layer for CUDA or for kernel abstractions, also CUDA, and see if that helps us figure out what the problem is. I don't know. It's going to be kind of crazy. So what this says to me, let me think about this. What this says to me is that the summation actually works as long as we're not doing it in a kernel. And it works in a kernel sometimes, and I'm not entirely sure how that works. So what I might do is I might call this one more time and see what we get. Maybe the GPU disconnects from the program and CUDA is still trying to talk to it, resulting in illegal memory or something. That could happen, but why would CUDA disconnect? So again, so what it works when I try to run it as just, so I'm doing a bad job of describing this. If we do this and I do just a sum on A, it will work. So if I create A here and I do sum on this, we will create a GPU kernel that this will actually do the sum appropriately. It creates an appropriate GPU kernel. But when I'm running the kernel abstractions kernel, it doesn't work. And this is fair. Totally fair. Is there a way to see events on Linux? I have no idea what that means. So I don't know. What is an event exactly? Let me get some water. Like processes? Okay. Let's see, what do we have? Also, guys, it's 5 o'clock p.m. my time. I'll be streaming for maybe another 3 hours or so. But what I might have to do, again, I am kind of tired. I might end up doing something that's not programming for a bit, just to, kind of do the longer streams, but also like, we'll see. We'll see how this goes. I'm just getting a bit tired, and I'm just letting everyone know that beforehand, so that if I end up ending soon, or if I end up like, I don't know, like doing something else, that's why. I'm just getting a bit tired. I was tired before starting stream for some reason, so that's how it is. It's a way to get information from the driver GPU on why it might have quit. I don't know. I don't know how to do that at all, if I'm honest. So here's what I'm going to do, Control D. I actually want to run this one more time, Julia. We're going to do, nsys launch, Julia, dm, is that it? dmesg, sudo. Do I have to watch this? One second. Should I just watch this as it's going? So we have, I don't know what all this is. Fail query, graphics exception, audit, user bin sudo. So should I just watch that and see what happens? I could just do that. What happens if I watch sudo dm, what is it? Let's just do watch this. Okay, so this is not the same, is it? So if I go here, do Control D, and we do Julia, and then we do include this guy, and then we do A is equal to some giant thing. See if there's something with GPU NVIDIA. Okay, so if I do this then, Control C, and we do grep NVIDIA, we have graphics exception. So if we do grep NVIDIA, see if this does anything. I mean, there is graphics here. Probably somewhere in var log as well, like current.log. Right. W to watch. Oh, I didn't realize there was a W to watch. That's nice. That way you don't have to grep it. Well, I guess I still need to grep it. But also, there's nothing happening here. Control C. Let me happens if I don't watch it. Let me see what happens if I don't watch it here. Okay, so there's nothing with NVIDIA. But if I look for graphics, there is stuff. So all this stuff is all graphics. Graphics exception. Does it give me a timestamp? So if I watch this, can I do W? Oh, is this watching it? Okay, so let's see what happens if I do something now. So I'm going to say A is equal to this, and we're going to try the F test. So now we're going to do F test here on input. What was it? It's watch here. So this is going to break, and I'm just going to see if anything happens on the left here. I genuinely don't know. Yeah, let's see what happens. All right, give it a second. It's going to break in like 3, 2, it already broke. I didn't even have to count down. So then if I do Control D. Okay, I didn't see anything new. I didn't see anything happening there. But this might not be the right command, right? So maybe we're missing something. But let me run something really quick. I just want to go ahead and take a look at the what's it called? The performance tools here. So nsys launch Julia. Here we go. And now we're going to do include here. It moved, but the error is the same. Oh well. You're right. It's graphics exception offset. Yeah. Let me just take a look at this and see if we can take a look at the kernel. So what I want to do is run, A is going to be equal to this guy. We're going to drop a few orders of magnitude. Let's do this, see if that works. You did something bad with the arrays, right? And so now what I want to do is wait here, make sure it runs, then we're going to do it again. Right, so there isn't really much I could have done with the arrays because, like, again, I'm just running sum. I mean, the code was literally just putting sum into a kernel. I was just seeing if we could run it in a kernel. I don't know if we can. I mean, obviously we can for small arrays, but I don't know if we can for larger arrays. So that worked. So now what I would do is cuda.appprofile, this guy. And we're just going to take a look at that and see what the kernel looks like. That's what I want to do. And then once we do that, I'm just going to see if there's like an extra call to like some kernel, some kernel, and see where that goes. Oh man, am I tired. Today is a day. All right, so we got this. We have QDR, we have report 5.qdrap, control D. Let's go into nsite sys and report 5.qdrap. And see what we got here. So we have this whole kernel. I think it's just going to be shown events viewer. So this kernel is going to be just a test kernel. So it doesn't show us more than that. It just says that there's a lot of computation going on. Let me see if we go back into kernel abstractions, cd into kernel abstractions, grep-rl sum. Looks like we have matmul, and we have test matmul, and we have a.out. We have, okay, we have something in a.out for examples. So it looks like it's just examples. So if we go into vi examples, and then, matmul. There we go. And then we go to sum. Yeah, I didn't expect it to be anything big. So let's go into lib, kernel gradients, test, and matmul is also in a test. Yeah, it's also in a test, isn't it? Okay, so this means that we're not specifically grabbing the sum. Okay, so why would sum in a kernel break? Why would it work is, I guess, the initial question. Yeah, okay. I think I see what happened. I know exactly what happened now. Okay, I understand. Here's what happened. So what I did was when you do a sum on an array, it obviously uses all the parallel threads available, right, to do that sum. When you do it on when you do it within a kernel, like for example, cd back a directory, cd into tests, ls here, right, that's exactly it. Each thread was calculating the same sum. So that's why it broke. That's why I just wanted to make sure, like I was almost positive it wouldn't work. And I was almost positive it would do something like that. I was just double checking to see if that was actually happening. What this means is not much, because I think if we're going to have to do the sum anyway, I'm just trying to think. So the thing I was trying to avoid, the thing I was trying to fix, was the fact that if we have like a whole bunch of forces all being added together for our n-body simulator, I was trying to speed up that parallel summation. So what we need to do is we just need to calculate all of the accelerations. Ooh, that's going to be messy, isn't it? Yeah, we need to find a way. Doing that parallelization is non-trivial, is what I'm trying to say. What I am doing right now is I'm making it so every single thread goes through every single particle. But what I probably should have is like some sort of array that adds all the accelerations together and then that finds all the accelerations. And then after that sorry, what's jumping? Sorry about that. It's now jumping. Oh, this is jumping. Over here? Wait, what's jumping? Anyway, so what we need to do is then, I think, create an array that adds all the accelerations together and then does the parallel sum. So I'm not sure the best way to do that. The green video? Oh, up here. Yeah, that's fine. No, you're good. I just want to make sure it wasn't like I wasn't clipping or anything like that. Okay, so fine. This kind of solves my issue. I know it doesn't sound like much, but this actually clarifies a lot in my mind. Also, because I'm so tired, I'm not doing a very good job of explaining what's happening. But essentially what's going on here is we are now able to, I know how sum works. I know we have an efficient implementation of the parallel summation. However, for the implementation we need for our force integrator, we might still have to do that from scratch. Because otherwise we're going to have to do a whole bunch of unnecessary kernel launches. Yeah, the parallelization is still non-trivial. Fine, good. That solves that issue. Okay, so that issue, I think we figured out what I need to do there. I know, to be clear, it wasn't like exactly obvious what was happening on stream. What I had just done is I just checked how sum works. So if I sum over A, it's fine. If I sum within a kernel, it's not fine because it makes every thread do all of the processing. Pretty sure that's what's happening. I can double check really quick by doing the same operation we just did, except this time just doing the where am I? PWD. Just doing the sum instead of the sum within the kernel. So let's try that as well. So we're going to go backer directory into GPU. What? See, backer directory into Nuleos and then GPU. L is here. And now let's just do the same thing again and just check the timings of the two different kernels and check the like thread occupancy and stuff like that. Okay, let's see what we can do. So I'm going to do one more thing, and I need to think about that. 1 second. So we're going to do Julia and this one. And sys launch Julia, perfect, using CUDA. And now we're going to create an array, and we're going to sum over that array, and we're going to write that out. Good. So A is going to be equal to 10,000. We're going to sum on A, and then we're going to profile that and check the difference in timings. And I think you'll see that like one should be like 10 times as long as the other or something like this. Anyway, if we see that, then, you know, I'm fairly confident in saying our, you know, analysis here is fine. That, you know, the sum is like per thread or something. We can look at the profiling a bit better, but that would also explain why the GPU is just like flat out failing. At some point, it's just either doing too much compute or like allocating too much memory or something. It's doing an illegal action, and that makes sense. If every thread has to do the sum, that makes sense as to why that would happen. Specifically, if every thread has to do the sum and Julia's garbage collector is really bad. Okay, let me get some more water. Super thirsty here. Let me do CUDA.app profile. 1 second. And then sum of A. Perfect. All right, give this a second to go, and then we'll take a look and see what we got. JDiamond978, thank you so much for following. Really appreciate it. Okay. Then the next thing we need to do is start talking about histograms again. Oh boy, histograms. This is going to be exciting. All right, let's go here. Let's go back to nsite sys, and we're going to do nsite sys report 6.qdrap. See what we've got here. And looks like we have this guy, shown events viewer, and we have the map reduce here takes 3 milliseconds, 3.8 milliseconds, whereas report 5, this guy, 1 second, shown events viewer, the whole kernel takes 2.87 milliseconds. That was not what I was expecting. Not what I was expecting at all. Okay. What? Why is this faster? What? Is it actually working correctly? Okay, let me try one more thing then, because that's kind of surprising to me. Each thread doing its own sum is faster than the MapReduce? We have two MapReduces here. One's 14 microseconds, the other's 3.867 milliseconds. And this guy over here is just a single kernel launch, which is, why is it faster? Okay, wait, this is actually something really good to look into. Let's go here. Let me redo the test really quick. vi test3.jl, some input, and let's just say, dd, we're going to say a is going to equal to this, and then we're going to say input of tid is going to be equal to a, right? Quit. Now we're going to do Julia, sorry, nsys launch Julia, and now we're going to do using, 1 second, using CUDA, and yeah, we can go from there. Okay, so using CUDA, what's the next thing I want to do? I want to create A here. I'm going to do a quick test and make sure that it works as expected. So we're going to do wait here, ftest not defined. Did I not include? Oh, I didn't include. 1 second. So let's go ahead and include the test 3, and then we're going to run the kernel and see what happens. Yeah, so we can run the kernel now, and then hopefully it all works out. Whew, my back is killing me. How do people sit in chairs all day? This is crazy. I know I used to have a standing desk, so that's kind of why I'm saying that. Okay, so we waited on that. So now let's take a look at A. Well, that is weird. Definitely weird. What's happening here? Okay. So we have 10,000, and then we have this guy. Can it mutate the array? Yeah, so it is mutating the array. How do people stand all day? That's also fair. Yeah, so that's really the only way to run GPU kernels is by mutating them, the data. Those are intermediary values. I think what's happening is we're running per thread, and I think what happens is you do like one block, and then you do, once that block is done, so I think the first 256 values are going to be 10,000, and the next 256,000, yeah, so let's go there. So let's do A of 256. This is going to be not what I was expecting. 255. Okay, let me do A is going to be equal to array of A. Sorry, HA is going to be equal to array of A. And now let's just do plot HA. Can I do that? Plot not defined using plots. Can I do that while I'm also in the debugging mode or something like that? We're doing sum in the kernel. Yeah, the sum is in the kernel right now. For some reason, the sum in the kernel was faster than the sum outside of the kernel. I don't understand that. So let's do plot HA. And let's see what, so it should go, I'm running with 256 threads. So depending on how that was blocked up. Oh, well, this is different than I was anticipating. Huh. Okay, let me just output this to file. So using delimited files. And let's output that to file. Log plot would be better. Yeah, I'm just gonna put this in new plot so I can more easily manage it. So let's do write DLM check.dat then HA. All right, Control D. Then we're gonna do 1 second. GNU plot, and we're gonna plot out.dat check.dat with lines. Okay, so here's that guy. Let me make it bigger, and then let me just zoom in here. Okay, so this is interesting. Okay, so what's going on here? We're 0, 10,000. Huh. Okay. How are you, Swarden? I hope you're having a great day. Thanks for the chats there. I can see you even if you didn't have to. You don't have to highlight messages. I can see them. You think it's undefined memory? But how do we get undefined memory? Like, we set A to be all ones, and then we updated. What is happening? All right, I know this is stupid. I'm trying to figure this out. I know this is stupid. Give me a second. We'll figure it out. What is going on here? You're reading and writing to the same location? Right, you're reading, writing to the same location, definitely. Right, I mean, I can throw an @synchronize in there, which would solve that issue. Control D, test 3. So if I put an @synchronize in here, I mean, this should basically, without using anything, yeah, so let me add the @synchronize, see if this does anything. Julia. Okay, include, and let's see what happens. I think my mind is kind of fried right now. I'm clearly not thinking. So let's create A here, and then let's try running it one more time and see what happens. So we're gonna do wait here, and then hopefully we get what we expect. Well, I don't even know what we expect, but hopefully we get something else, you know? Let me get some water. Man, I'm thirsty. Okay, let's take a look at A. So we're going to say array, HA is going to be equal to array of A. It's not going as high anymore. Let's do using plots. Let's see if we get the same behavior. Okay, so now we're going to do plot HA and see what we get. Now there are 10,000 elements, so maybe it takes a second, but yeah, let's see what we got. Right. Right, of course. I don't know why I was expecting anything different. I don't know why I'm analyzing this kernel. It doesn't really matter. Like, it really genuinely doesn't matter, but I'm interested. It's like, why is this happening? I have no idea. Right. So, I mean, I can output it to file again. It's going to be the same, though. Delimited files. Right, DLM. All right, Control D. GNU plot. Plot check.dat with lines. Make it bigger. Scroll in here. Yeah, there aren't as many spikes. I don't know what that means. And also, it's like, it's not very clear like where the spikes are coming from. Oh, this is so stupid. Why do I even care? It doesn't matter. This kernel is like completely useless, but now I'm interested. Like, why is it doing this? Like, what is kernel distractions doing under the hood such that it is... Like, what's this doing? Okay, here's a question. Do you guys... Swordhands, by the way, Senior Wordhands, actually. Thank you so much for following. Really appreciate it. Okay, question. Is this actually... Should we keep looking into this? So, the two things that we can do from here is we can keep looking into this, try to figure out why the kernel abstractions kernel is so weird, and figure that out. Or we could look at histograms, or we could do something a bit different. It does look a bit better, I think you're right, but I don't know why. Giab, thank you so much for following, really appreciate it. But yeah, just let me know what you guys think. I mean, I'm happy to, oh, that's slow, isn't it? I'm happy to keep looking at this if you guys are. But also, like, to be fair, this kernel isn't particularly useful. And so because of that, it's not particularly useful to keep going here, you know? So yeah, let me know what you guys are thinking. I'm happy to keep looking at it, but also I feel like maybe we should move on to something else as well. In the meantime, while you guys are thinking, I'm gonna run upstairs and grab some water, because I'm basically out. So I'll be right back. Right. So is it correct though? If not, it might be worthwhile to know what the issue is to avoid it while implementing the other kernels. Yeah, let's talk about that. Will we actually run into this problem later? That's the question. Knowing the basics, one building on top is always worthwhile. GPU calculations are not very accurate. Single precision on the GPU means 32-bit, while the CPU calculations more accurately, even when using 32-bit floats. A CPU usually has 80-bit internally. This is true, right? I mean, like for GPU computing, you are losing precision, right? And the question is, do you actually need all of the precision? And I don't know. I don't know the answer to that, right? By the way, Gia, but also No Test 4, thanks for following. Really appreciate it. So let's go ahead and catch everybody up on what's happening and see where we want to go with this. So here's the thing. Let me go back over here. Journal, new page before. So we were talking about our N-body simulator, but also a bunch of other things. And in particular, we have this problem with the N-body simulator. We have all these particles, right? And now look, there's a bunch of ways to fix this, but essentially every single particle has to talk to every other particle in the simulation, right? There are ways to fix this, like for example, using like octrees and stuff like that. But for the most part, you have to do an n-squared operation with some performance differences depending on your implementation. So in particular, the hard part here means that as this guy is talking to all these other guys, you have to add all the accelerations together, right? So this means that, this person is influenced by every other particle's gravity, right? And what you're trying to do is see if, see exactly where this guy will move, in what direction this guy will move in, based on every other particle in the simulation, right? So you have to add together all accelerations due to gravity. Okay, so that's the big difficulty here. That's the challenge here. Ordinarily, this isn't very difficult, right? Like you just sum, like all of the accelerations together. Sum A1, A2, A3, all of these guys together, right? But doing this type of iterative process is kind of, it's not great on the GPU. Like if you can, you want to optimize that in some way, shape, or form. So we're actually taking a look specifically at the sum function. So one needs to sum n by the dimensions. Yes, one needs to sum, it depends on what you mean. You need to do a sum over n values. Yes, a sum over n, it's n by the dimensions, I believe is what you need. Miyabdi, hey, how are you? I hope you're having a great day. So it's sum over, the number of particles in one dimension and then the dimensions in the other dimension. So it's like if you're running a 3-dimensional simulation, it's going to be 3 by n. I think that's what we have to sum. Then you have to do n of these sums. So the operations you wrote down is correct, but it's n of 3 by n summations. That's what you have to do. Okay, so we were looking at the sum function, right? And we found that there's a couple different ways to do this. So one way you could do this is you could literally just do an operation. So you go to this particle, you find all the accelerations. So find accelerations. Step 1, find accelerations. Accelerations, plural. And 2, sum those accelerations. In code, what this would be is probably a kernel to be find acceleration, which outputs some acceleration array is equal to this, and then sum on the acceleration array. And then you go from there. This could work. That'd be fine. But the big issue here is that we have this auxiliary data structure, which is for the accelerating component, which isn't particularly good. It's fine. We can just use the same data structure. But the other thing too is you have to find the acceleration and you have to loop through all the particles. So there's going to be an over loop here. So for n, n equals 1 to big N or something like that. You have to basically go through all of these guys, right? So this means you're going to have a bunch of different kernel launches and all this kind of stuff. And depending on how this sum is implemented, I'm not sure. There might be an auxiliary array in there. Pretty sure there isn't, but we can go from there. n minus 1 over 2 sums for pairwise interactions. You make a great physics professor. He doesn't like physics. He was kind of a physics lecturer. Yeah, I was a physics. I did a physics PhD. I definitely did a physics PhD, which is why I'm super burnt out of physics. The problem is a lot of times when people talk to me on stream, I'm quite tired. And so the issue is that like I'll sometimes say things that aren't exactly accurate, and I just end up saying different things every other day. But the fact is that I used to teach physics classes, right? I did a physics PhD. I went through all of that, and I'm so tired of doing physics research. I just want to focus on something else. That's kind of where I'm at right now. As far as being a physics professor, I would love to be like a computer science professor. I think that'd be nice. But I have no intention of doing a physics course unless it's a computational physics course, in which case I think I'd be relatively happy to do that. Okay. So what I was trying to then find is a way to do the summation of all the accelerations within a kernel. So that way we don't have multiple kernel launches. Now, we're really micro-optimizing this, if I'm being honest. Because in the end, we're going to have a loop. There's going to have to be a synchronized statement. It's going to be fine. I think actually the ideal way to do this is this way, where we output some acceleration and we sum the acceleration second and we do all the kernel launches. Otherwise, the kernel is going to look like this. Kernel, and then inside the kernel, you're going to say for I equals 1 to n or whatever. Sorry, my loop notation is different here. And then you're going to have to do acceleration of, what are you going to have to do here? You're going to have to do acceleration of like I is going to be equal to or plus equal. How would you do this in a kernel? Actually, I think the two separate kernels is actually the way to do it. I don't think having a sum inside of a kernel is worth doing. No, I'm trying to think of this again, but I don't think that's how we want to do it. Let me think. Okay, so we can do for you don't want this for loop in the kernel. If you can, you want to avoid that, right? We're looking at the acceleration for all particles, right? But we need to, the summation bit is for each individual particle. We have to do a separate sum. That's the problem. Kernels should be faster, right? The kernels will be faster because you don't have the kernel launch. The two kernels, I think, might be faster. You might be right. The two kernels might be faster because I mean, the only thing you have to take into account is the extra kernel launch. But here, if you're going to write the kernel, what would that look like? And it would be, oh, no. Let me think about this again. So you do acceleration of TID. This is all you do. One kernel is just acceleration, acceleration out of TID is going to be equal to whatever you're doing here. So it's just going to be calculated acceleration with the particle positions at TID or whatever. And I, or something like this, some sort of calculation like this. So you're gonna have some calculation like this, and that's gonna be the end of the kernel. And then you can @synchronize, right? And then all you have to do is, that's gonna be the calculation of the find. So this is a find acceleration kernel. And then, no, you need the for loop. So the question is it better to have the for loop inside the kernel or outside the kernel? And I think the answer is probably outside the kernel. I don't want to sidetrack you. Say you know how the FFT is done. Isn't that they're also kind of like the n-squared algorithm? Could you have a peek at it? Are you talking about the Cooley-Tukey method? The Cooley-Tukey method has a fundamentally different structure for how it does like the divide and conquer method and stuff. So we need the for loop because you're talking about why we need the for loop in the kernel. And the reason we need the for loop in the kernel is because we have to look at every other particle for every other particle, right? And so if we were to write this differently, 1 second, it might look like, let me just do this in text mode. I don't know why I'm doing this in, let's try this again. So the kernel would look like something like for I is equal to 1 to n. 1 second, I'm failing. By the way, Atrutha, thank you so much for following, really appreciate it. So we have the kernel where the TID is going to be equal to the particle we are looking for the acceleration of, and then the I would be the particles we are comparing against. So in this example up here, the TID would be this one, And these guys would all be your I iterations. I. Okay, so then you'd have to do, so then literally the kernel method that I have right now, I think, yeah, so you do for 1 I to n, and then what do you do from that point? So this is why I think, you know, like, what do you do? So what I'm currently doing right now is I'm saying temp acceleration of TID is going to be plus equals to the, you know, new acceleration, find acceleration, whatever it is, the function in which you find the acceleration between the 2 points. So like gravity or whatever, you're running between position 1 and position 2 or something. You know what I'm saying? So it's like position of TID and then position of, the position of TID versus the position of I or something like this. And that's how I'm currently doing it. And actually, that might be the fastest kernel if you want to keep it within a single kernel, because otherwise we're going to have like a separate acceleration. I'm interested. Actually, let's go back to the n-body simulator and let's implement this method right now. Let's get this done and see what the difference is in performance between this method and the current kernel that we have. Okay, that's what I'm going to do, because I'm actually interested to see which one's faster. Let's do it. I mean, we have another, 2 hours of stream or something like that. This is plenty of time to do a quick performance test and see what it looks like, you know? Like, why not? Let's go for it. Okay, so we're going to CD into projects, Galilee. Here we are, Alice here. Let me do git status really quick just to make sure we're up to date. Perfect. Over here, we're going to CD projects, CD projects. And then we're going to run Galilee here. Okay, so let's go here. Let's go into the iForces. Source and forces. Okay, so here's how it's currently done. So we have the find accelerations kernel, which launches with a particular sim type. And the sim type I'm running is the n-body sim, which is unfortunately down here. What this does is it says our temp accelerations are going to be equal to 0. It just sets them all equal to 0 at the start. Then it says we do for j is equal to 1 to size of positions of 1. Oh yeah, thanks for being here. Quits fake. I appreciate it. Thanks for the follow, by the way. And we say if j is not equal to TID, we run the force law, which then updates the temp accelerations here. And then we do @synchronize, and we just say size of accelerations. So I think this might work. What do you think about the advent of code? It's not really scientific computing. Do you think it's worth doing? So the advent of code is something that a lot of people in the community have liked a lot. It's something that, you know, you're the type of person that will know whether this is something that would be useful for you or not, I think. So maybe, like, it's a bunch of coding problems, right? But I think a lot of them are quite useful. I think a lot of them take a lot of thought. The reason I haven't done it before is just because I haven't had the time to do it. Why do we use a temp array? So the reason we use a temp array here is because... One second. I'm thinking. The reason we use a temp array is because, wait, I'm going to join competitively maybe? That'd be quite cool if you did. I think a lot of people really like it. You're right though. Chaotic One, thank you so much for following. We might not need a temp array. We could write directly to the accelerations. I think you're right. I think we can avoid having that temp accelerations array. We probably could. I've done so for the last 2 years. Last year kind of burned me out. Yeah, so the reason I haven't done Advent of Code is not because it's not a good project. It's actually a really good project. The reason I haven't done it is exclusively because I just haven't found the time to do the bit of code every day. It's just been a little bit... You know, I'm a wimp is the actual reason. I just haven't had the time to do it. And every time the Advent season comes up, I'm always like, I want to work on this and that. I have so many other things I want to do. And so when the Advent of Code comes on, similar like Project Euler and stuff like that, like I don't want to work on problems outside of the problems that I've already given myself, because I have so many problems to give myself, you know? 6 a.m. is a hard time to be ready for code. That's probably fair as well. Anyway, the reason I had the temp accelerations here is because the reason I have the temp accelerations, let me think, I need to think about this. We have the accelerations of TIDJ is equal to temp accelerations of TIDJ. We've @synchronized for this guy. The accelerations, is this even going along the correct dimension? Size of position is 1. Size of positions 2. So the temp accelerations is going to be of size 4, I think. The temp acceleration should be of size n, where n is of size... Wait a minute, what is going on here? I think I did things all wrong. I think what I actually want to do is create a local mem copy for temp accelerations, which is all going to be equal to 0. Because I think temp accelerations is only going to be for like elements of dimensions in size, where dimensions can be like up to 32. So maybe what I want to do is I want to rewrite this so it's using a shared memory tile, so we can write to the shared memory tile, and then we can output it afterwards. And then, but why do we have thread ID? What is going on? I need to relook at this code. I don't know what I did, but holy crap, that is stupid. Okay, temp accelerations should only be 4 elements long, and then we output it here. That's what it should be. There's no reason for it to be bigger than 4 elements. Let me take a look at the force law here. So when we're doing the force law calculation, it reads in the temp acceleration, TID and J, and every single time we write to the temp acceleration, it's always of element TID. Yeah, okay, this is me just writing bad code. Let's make this faster. At the very least, let's just do that. So let's increase or make this particular calculation faster using some shared memory, and then we can go from there. Because in principle, what we can do is we can just say temp acceleration is going to be equal to like at local mem float 64. I guess 64 is what we're using here, I guess. And then we want a particular size. Now we have to define the size beforehand. So as long as we don't go above 32 dimensions, we're going to be fine, I think. Oh no, I can't believe I wrote that. That's so bad. Somebody asked earlier whether Advent of Code is worth it. 100% for learning. The times you're going to swear your code is right, but turns out it isn't, will be TDH. Look, I gotta be honest. Like I said before, if you're one of the people that gets something out of having a problem to do every day, and you see that as motivational, then yeah, it's gonna be useful for you. Some tasks look pretty easy. To be fair, I think that's what everyone always says about the advent of code. It's always like it looks easy and then it ends up not being easy. Okay, so then what I'm gonna do is I'm gonna rewrite this. Oh, how do we want to rewrite this? So I wanted to test the 2 different versions. One where we do a bunch of different launches, and one where we do like only one big kernel. So let's see what the difference is. So right here we have find accelerations. So all we have to do is modify the find accelerations kernel. Let's speed up the current code, and then after that we're going to write a new version, which is using a different method, and we're just going to compare the 2 and see which one's faster. That's what we're going to do. Screw it. Not going to worry about it. Plus, some of the easiness depends on how much experience you have with the area. In general, they increase in difficulty. I missed some stuff. I'm sorry. Crop up there. One thing I love about competitive Advent of Code is that you have to trade. You have the trade of the speed of your implementation for the speed of you're implementing it. Yeah, that's totally fair. Some tasks look pretty easy. Good. Okay, let's just fix this up. I cannot believe I wrote such crappy code. I mean, have you seen me? I write crappy code all the time. But okay, so here, we don't need the temp accelerations anymore. I'm going to make it so the temp acceleration here, for all of these different force laws, is now going to be read in as a singular. This is a singular temp acceleration. Now, positions as well, I think we can just read in a single array. And so what I might do is I might create a temp acceleration and a position. Positions here, we're going to have TID. It's TID and K. How is this going? So we have 4K is equal to 1 to size of positions 2. So this is along the dimensions. We do R2 is going to be plus equal to positions of TID K minus positions of JK. So what is J? J is going to be read in from the loop. So in principle, what we can do is we can just read in, we can create 2 different shared vectors, one for positions and one for accelerations, and we can use those to write quickly to think, oh God, I can't believe this. I've written such crappy code. Like, I've written crappy code before. Okay, so temp acceleration. Okay, temp acceleration is going to be equal to, I think I can just do at local mem. Should I just change this back to the 4D galaxy simulation? Let's go back to the 4D galaxy simulation. I'm just gonna put that in the title. It looks like that's what we're gonna do for the next hour or two. So I'm gonna change that again really quick. 4D galaxy sim. Let's go. Done. Let's go. All right, we're gonna get this done. All right. So what do we have here? Gotta go see a crop. Have a wonderful afternoon or evening, or morning or whatever time. You see some programmer and veteran. It would be worrying if you weren't easy for you. What are you working on right now? Generally, they increase in difficulty. Okay, right. So what am I working on right now? So right now, if you look in the upper left-hand corner, you see a simple n-body interaction with gravity. So here's the 2D simulation. We have a 1-dimension, a 2-dimension, a 3-dimension, and a 4-dimensional simulation. We're fairly convinced that the 4-dimensional simulation is going to be boring, but at the same time, we're looking at different techniques in order to speed up this computation. So we've been looking today at the GPU code, or at the GPU summation function, which is deceptively difficult, and we are trying to get that to to work in our code. That's kind of what we're doing right now. So we're implementing 2 different versions of the code. One is a sped up version of the code that I've already written, and the other one will be an implementation where we do 2 different functions, one for summation and one for the calculation of the accelerations between all the positions, and that's what we're working on. So if you're absolutely new to this, here's what's happening. We have a single particle in space, and we have n other particles, or n-1 other particles. So at any given point, we have to ask ourselves, where is this particle moving, right? And the answer is, well, it looks at every other particle in the simulation, and it asks, okay, well, where is the force? How are each of these forces acting on all these other particles, right? And so once you've determined that, you've looked at every other particle, you can find the acceleration of this particle and then move it forward with time. And that's how that's working right now. Let me go catch up on chat. And so we're trying to speed up the finding of that acceleration. That's the part that we're trying to speed up. Let's see. Gotta go. Tennis program says something. Some looks pretty easy. Gotta go. See you later. They do require serious algorithm knowledge at times. I wouldn't call them easy. They do take time and energy to get them done. Right. I think most people say the advent of code is deceptively challenging. It looks simple, but it's oftentimes a little bit more complicated. So advent of code is not educational. Okay, I had the impression it was more educational. No, wait. It is educational. Like, it's definitely educational. I'm sorry. Like, I hope you didn't get that idea. It's 100% educational, but many experienced software engineer programmers haven't dealt with those types of problems. Right. That is true. Is it real time in the top right or pre-recorded? It's pre-recorded. We generated this yesterday. Okay, so we're going to go ahead and speed this up and go from there. So we have the n-body calculation here. I think this is how you do it. I might have forgotten, but I think it's like local mem of the floating type that you want. So float 64, and we're gonna make it so the maximum size is 32. That's not ideal, but it is what it is. Okay, so in here what we're gonna do is we have temp acceleration equals 0. We do actually want that now. So what we might do is we might say, just to speed this up a little bit, we might remove these lines in here, and we might also create a local ID for local ID, and we're going to do @index_local. I mean, we could do up to 256 dimensional, but the problem here is it has to be static or constant, so we can work on it from there. Okay, so we have this. So now what I'm going to do is if LID is less than 32, again, it just has to be constant, which isn't great, but we're going to say temp acceleration of LID is going to be equal to 0. Perfect. So now we've decided that. Here, we're just going to read in the temporary acceleration. And then we're going to do acceleration of TIDJ is going to be temp acceleration of, should just be J, I believe. Here. So what we actually want to do is the following. We're going to do if LID is less than 32, less than accelerations, size of accelerations. This is a stupid way to do it. Size of accelerations 2. Let me go over here really quick. For Pete's sake. This, change the song. I don't like this song. Then we're going to do this. DD, accelerations of TID, LID. It's going to be LID. Oh, that's so dumb. I mean, like, I would love to make it so this is all, like... Anyway, we can check again. So if we can make it so, like, if this is not const, then we could do this a lot faster. But I think this has to be a constant value, so I don't think we can do anything about that. So now for the positions. I think we also want to create a temporary set for positions, 1 and 2. So I think we want to do that as well. So we're going to do temp position 1, temp position 2. So yang paste and paste. So we're going to temp position 1 and temp position 2. Position 2. Okay, and the reason I want to do this is so that we can define so we can define all the positions here. So if LID is going to be less than size of accelerations 2, we're going to do this as well. Now we should just be able to do temp position 1. Temp position 1 is going to be equal to, and it should just be positions of TID and then LID, I believe. Okay, so now we have the temp position. And all we have to do now is change the force law so it reads in 2 different positions, position 1, position 2, and the acceleration that we're writing to. And so for this guy, all we're going to do is say temp position 2. 2 is going to be equal to, I think we can just do, wait, I need to think about this again. I might need another if statement in here. Hey, Nick, how are you? And also, we're really, like, making the first 4 threads do a lot of work. Or the first n threads, where n is less than... Like, why are we optimizing the n body problem anyway? You know? It's kind of like, why would you ever do... Anyway, let's just keep going. The problem with this force law is that we have to read in the entire array of positions, and I don't really like that. I would love it if we could just read in temp position 1 and temp position 2. The problem with that is to do that, we need like a separate loop that is resetting the temp position every time. And that's kind of ugly. I don't like doing that at all. So let me go up here and see what we can do. So the force law here is going to read in the temp acceleration, and we want temp position 1 and position 2. And then we should just be able to run position 1, position 2, and then we don't have to read in the thread ID or J anymore. Okay. Okay, let's rewrite all of these forces so they only read position 1 and position 2. That's what we're going to do. It's going to be faster. Let's do it that way. So these guys are all going to read in position 1 and position 2, and then acceleration. Temp acceleration. Let's go here and just do that for all of these guys and just rewrite the code so they do that. And then we're going to modify that later. Here. Okay, so $, do that a couple times down here. And here as well. Okay. So R2 is equal to 0. So this is going to be position, this said position, but it should be position 1, position 2. I'm stupid. Let's fix that. See you, Nick. Have a wonderful birthday for your fiance. I hope you're gonna have a good day. And yeah, have a good rest of the day. Thanks for the wishes for the good stream. Sorry, I'm kind of tired today. 1, and then we do 2 over here, and then we keep going. So we have 2 over here, and then we should have gravity 4D as well. 2 there. Okay. Position 1. And 1 up here. So what we're doing right now is we're changing all the force laws so they read in 2 positions in a temp acceleration outside of what they did before. So this is position 1 minus position 2, isn't it? I guess it's 1 minus 2. So position 1 of K. It's weird that that's, it's repulsive. No, I don't understand that. Why is this? Wait a minute, why is this position 1 minus position 2? Shouldn't it be the other way around? I'll check that later, but I'm just going to write what the code says. Here, and then position 2. There, okay. So keep going. So it should be positions. So this is going to be dt there, 1 of k. And then this is going to be positions 2. Okay, perfect. And then temp acceleration, we'll no longer need the TID. So that should just work, I believe. Yeah, that makes it way like nicer too. The code just looks nicer. I mean, it's not that much nicer, but it's a little bit nicer. And sometimes when you're writing code, you just need a little bit nicer to make your day just a little bit happier. Okay, size of position. This will be position 1. And this will also be position 1. And this time we can just do length. So let's do length instead. All right, we're gonna have to do this for all of those, but it should be relatively quick. So here we're gonna just go through one at a time and just kind of do it in bulk. So dt there, here and there, and modify all those to be length. All right, keep going. Kitty Mouse, thank you so much for following. Really appreciate it. What'd I do? Okay, this should be length. I was looking at the notification and then I messed myself up. Let's keep going up here. And here as well. It's good. I'm happy to see that we're going somewhere. So let's go here and change all of the positions. So first we want to remove these guys. Oh, sorry. Down here as well. And up here. Change this positions array to just to be positions 1. I'm just like changing things one at a time. I could have done this way faster, but just how I'm doing it. You guys are gonna have to deal with it. Okay, so down here, again, it's weird that it's position 1 minus position 2. I don't understand that one, but it's fine. DT here, there, here, there. All right, keep going. And here as well. I'm just deleting all these and I'm going to add the 1s and 2s in a second. And this one as well. Okay, so now we got to delete some indices and stuff, but we're slowly getting there. So let's do 2. Yes. 2, 2, 2, 2, 2, 2. And we're going to modify this so it's position 1 and 1. 1 as well. And then we have a couple down here. And this one down here. Okay, so now we just have to erase some of these indices. There. Temp accelerations, we have to erase that index. Perfect. Again, guys, if you have any comments, questions, concerns, anything like that, feel free to let me know. We're doing a bit of just kind of, you know how it is. Sometimes you just have to kind of go through a bit of grunt programming, and that's kind of what we're doing right now. I say grunt programming, but it's not exactly. I mean, you kind of have to think about what you're doing while you're doing it. I say while talking and not paying any attention to what I'm doing. But yeah, let me just check this. So these should be our new force laws. So if we go down here, we should be able to read in temp position 1, temp position 2, and then temp acceleration. So temp position 1, temp position 2, and then temp acceleration. Okay, perfect. And then what we want to do is for this guy, I think I'm just going to make every single thread is going to go through. So I think what I have to do is an @synchronize in here as well. So we're going to do @synchronize, which isn't great, but it's before. Unless I just make every single one of them. Should I make every single? The temp acceleration here should all be set to 0. So maybe I don't do the setting to 0 in parallel. I just make every thread do it. This means that there isn't a synchronize. Yeah, let's just make every thread do it. Then we just don't have the synchronize. It's fine. So we're going to say for k is equal to 1 to length. Size of accelerations 2. And then we're just going to do temp acceleration of k is equal to 0. And temp position of k is going to be equal to TID k. So what we're doing here is we're basically creating a shared memory array for the accelerations and 2 sets of positions. One set of positions is going to be the position of the particle that we're looking at, and the other position is going to be every other particle in the simulation. Now, I don't like the fact that we have these nasty for loops in there, but we're going to fix that. I'm a complete newbie, have done some very basic coding, not that I can remember it right now. That's okay. If you have any specific questions, feel free to let me know. I'm doing my best to kind of describe what we're doing as we're doing it. And again, for those who may have just come in and you don't really remember what we're doing, here's the idea. We have this n-body gravity simulation, right? So the idea is that all of these particles are being influenced by each other's gravity. So the idea is that this particle in here feels the force from gravity from every other particle in this simulation, right? So what we're doing is we're writing a GPU, a very fast parallel kernel, that allows us to basically do this summation of all of these accelerations onto a single particle. So this particle is going to be our thread ID particle. That's our individual thread on our GPU. And then our I values, or J values here, are going to be every other value in this guy. So every single thread on the GPU will start by initializing our position and our accelerations. Then it will look at every other particle, and it will check to see it will check to see what the acceleration is supposed to be. Sorry, I just hit my table. And then it just goes from there. So that's kind of what we're looking at. Again, I'm kind of going quickly because I'm in the middle of like a coding binge moment, where I'm just kind of getting all the code in. So I do apologize if that was quite quick, but overall, that's what we're looking at here. Now we're using a shared memory array because I'll fix that in a second. I'm using a shared memory array because the shared memory array will just be faster on average. It looks like you renamed accelerations, plural, to temp acceleration in a few places, but you also referenced temp acceleration without the S. There should not be any more temp accelerations, plural. Oh, up here. I see. Thank you. That was what it was before, because we were reading the entire acceleration array into these. Hey, Gawabunga, how are you? Hip hip array? Okay. Man, you're on fire with the jokes today, man. There was, didn't you also say there was like another joke that came up earlier that was something like, and what was it? It was, there's a few more places. I'll take a look in just a second. Let me go and fix this up. Equals 1 to size of accelerations 2. And then we're going to remove the local ID with K and change this to be K. And I believe that's right. So now we can remove the local ID. Now let me look for accelerations. All right. So size of accelerations, that's fine. Accelerations, temp accelerations, correct. Okay. Anything else? No, I think that should be fine for now. So let's go back up to the n-body simulator because that's running for lay, which is a different thing entirely. Okay, so we have this running. We have the force law. We have temp position 1, temp position 2. So the next thing I have to do is just go in here and say for K equals 1 to length, size of, I should probably read N in as well. So size of positions 2. 2, then we're going to read that in here and here, and then we're just going to say temp positions, position, 1 second, 2, this isn't a really good name, but it is what it is. Temp position 2 of K is going to be equal to positions of J, K. And then we do the force law, and in here I'm actually going to read in N, which actually means up here I'm going to define what N is. N is going to be equal to, let's do little n, is going to be equal to size of accelerations. Let's do 2, and let's go ahead and modify all these size of accelerations to just to be N. Now, I am defining these to be 32, even though in principle they only need to be 4. Or up to N, which is the size of the dimension, just because, I don't know, I just feel like they have to be constants, right? And I know we're not going to go over 32 dimensions, so I think it's fine to do that. Okay, this should be fine. Right input there. So I think then this will technically work. We're asking each thread to do a lot of work, but this is the trade-off, right? Like we were going to try to do two different types of code. One where we ask the threads to do a lot of work, and the other where we ask the threads not to do as much work, but has a few more kernel launches. And I wanted to see which one was faster. I believe we can run this, and we can remove the temp accelerations entirely. So we can remove that from this. And that means we can remove the temp accelerations here, and we can go to end body here, and we can remove the accelerations. No, wait, let me think. Oh, it's already removed, perfect. Okay, so we go up here, right and quit, go into VI source simulate. Oh, we're so close to getting this done. So where's our temp acceleration? So we have this temp vector that we're passing around, and we don't need to read that in anymore, so we can remove the temp vector here. Hey, Marco Dev, how are you? I'm having a great day. DTX. Perfect. Let's see what happens. Oh, there's no way this is going to run. Using Galilee, it's going to break. I'd be surprised if this ran. Oh, man, my back is killing me. 4D Galaxy of what, actually? Stars and dark matter and stuff. It's 4D Galaxy. It is what it says it is. Okay, so it pre-compiled, which is nice. We'll try Galilee.run, 256 particles, CUDA not defined, using CUDA. Try it again, see what we get. No way this is going to run. If this runs, I'm going to be amazed. Like, honestly amazed. Interesting. So let me get some water. So what we found actually was because when you go to 4D, the force law probably changes to 1 over r cubed. We found that it's actually probably not that interesting because 1 over r cubed force law means that the amount of force, did that run? The amount of force that every particle feels is just way lower, like the further away you go. So it's like, I don't know, trying to do the simplified galaxy rendering simulation, space-time. We're not talking about space-time, not at all. We're talking about 4 spatial dimensions. And then if you want to consider space-time, then it's 5-dimensional. But honestly, we're not dealing with that. It's literally 4 spatial dimensions, as in when you get a tesseract or something like that. Let me get some water. In principle, we got another 2 hours of today's stream. We got actually these visualizations. We have the visualizations that you see in the upper left-hand corner 2 days ago, and we spent 2 days just optimizing the code, which is about right, Okay, so let me go ahead and remove some files, and let me see if this is actually working. That wasn't what I meant to remove. Remove accelerations.dat. Sure. And let's try running it again. This will be a 4-dimensional code, Gravity 4D. Let's just run a 2D sim. Let's just do 2D. So 2 dimensions. And let's go. 4D algebra. I'm sorry. I'm talking fast because I'm trying to get the code done. Okay, so we're going to do Control D. We're going to CD into aux, ls here. And now let me just run the last GNU plot and see what happens. Plot 2D. And this should create a 2-dimensional plot. And then we should be able to take that 2-dimensional plot and go from there. String theory requires 2 more microdimensions and strings. Gotta be honest, I know nothing about string theory. Genuinely nothing about string theory. The more people talk about string theory, the less I know about string theory, and the less I want to know about string theory. Mirage. Crap. Back into check. Oh, I'm an idiot. Mirage out. This guy? Okay, so here's our set of particles as they started. Whoa, what's happening now? Oh no. We were expecting to see what we see in the upper left. And instead, they all just kind of run away. Oh no. Oh, there they go. Okay, well, let me, I'm going to save that one. That one's pretty good. Oh, that's pretty funny. I'm gonna only save the first 100 frames. So let me just go ahead and remove everything after 100, and I'm just gonna output this to file. All right, we're just gonna create a visual. All right, delete that. Yeah. Okay. Go here and let's just mogrify that. Oh no. Runaway theory. All right, so now we're gonna do / create video, and we should get a new video. So let's do mpv test.mp4. There go our particles. It's just so wonderful. There's our 4D galaxy simulator. I know exactly what's happening. All of the accelerations are writing the same point. That's the issue, which is fine. I know how to fix this. Is Zeus finally turning into an evil physicist? Or has he lost his mind? I just find it so funny. We were expecting a visualization like you see up here in the upper left-hand corner, and you just get the whole plot just leaving. Oh well, it is what it is. All right. Of course that's not going to work, right? Of course it's not going to work because the shared memory is obviously shared between threads. You want to use a local memory resource. Can you create a local memory resource is a question. Maybe I could just create the array, which is like a tuple or something, and we can update the tuple. Oh no, I can't believe that. All right, I'm going to save that though. Move temp. Test.mp4 into runaway.mp4. Oh, that was beautiful. Let's go back a directory. Oh, that's pretty good. Okay, so now we're going to do vi source forces. Okay, so I know what happened here. So what happened was all of the accelerations we created a shared memory resource to put the accelerations and to put the positions and all that kind of stuff. However, because it's a shared memory resource, it's pretty clear. It's pretty clear that we're writing, like, we want like a thread local memory. Like we want every thread to have a single bit of data. But I was putting it all in shared memory because I'm an idiot. So what I actually want to do then is I want to create multiple shared memory arrays. I want to create multiple shared memory arrays where we have a local... How big can we make the shared memory arrays? How much shared memory can we actually like create? Is my question. Because I don't... Oh no, this is so unfortunate. I thought we had this. I thought it was going to work. And then we get that. And now we're like stuck at the beginning again. So let me explain what's happening because I'm not doing a very good job of that. So I created a temporary acceleration, a temporary position, and a second temporary position. All of these are local memory arrays, which essentially means that they are shared between a bunch of different threads plural. So each thread has a local ID, and has a local ID. Come on, just think. So each thread has a local ID, but they're all sharing the same memory resource, which basically means that every time we updated the acceleration for any particle, it updated the acceleration for all particles. So what you were seeing there was an n-body simulation where every single particle has the same acceleration and is moving in the same direction. So that's why that happened. So how am I going to do this then? I can create a two-dimensional array, which is going to be of size... I can create 3 two-dimensional arrays, and I can try to do this slightly differently. So what I can do then is I can do, I think at group size is what I want. How do I do that again? I've done this before. Let's go into vi back a directory into histograms, Simuleos, and then histograms. Then we want to go into, what's it called? Probably just histograms.jl. Let's go into GS, which is group size here. So at uniform group size here. Ooh. Oh, but we don't have any synchronizes, so we should be fine. Good. Okay, so we're going to go into forces.jl. Let's rewrite this. So we can do this in a number of different ways. What might be best is if we just create a bunch of uniforms. I know that's not ideal, but maybe that's what we do. So we do a bunch of uniforms. So we're going to do uniform, and we specify that code is of size 4D. We are not going to be able to generate we're not going to be able to generate an array, but we should be able to generate a tuple, I think. So let's try that. So right now we're going to try a couple n tuple ideas. So we're going to need this syntax. So let's go here, comment this out, and that out. And let's define them again. So we're going to do @uniform temp acceleration. All right, and we're only going to go up to 4D. So I think, let me go ahead and check out the Julia syntax here. Julia, and let's do n tuple 4, 3, this. Okay, so can we just do the following? Can I just do the following? Let me just say this is going to be equal to, hear me out here, 0, 0, 0, 0. Okay, I know it's dumb, but this is what I'm going to do. Temp positions. Temp position 1, and then temp position 2. Okay, so in principle, this is the same code we just had with a bunch of @uniforms. If this doesn't work, so for this we have temp position 1, temp position 2, temp acceleration. If we're allowed to allocate this tuple on each individual thread, in principle this should work. So let's go ahead and run Julia --project using, where is it? CUDA Galilee. There we go. And then hopefully we can just run it again and it just works. I don't know. I'm a bit sketched out with the tuples in there. I feel like we're asking each thread to hold a lot of stuff in its head. But I have a backup when this fails. I definitely have a backup when this fails, which is create a very large shared memory array and use that instead. Oh boy, that's been a crazy stream, hasn't it? I mean, look, we've gotten stuff done. I'm relatively happy with where we've gone. See, I figured that was going to break. And this is going to break because it's going to say, the very top here, dynamic function invocation call. That's different than I thought. Unsupported dynamic function invocation call. Let me just mess around with tuples really quick. See what we can do with them. Control D. CP test 3 into test 4.jl. All right, vi test 4.jl, and let's just see what we can do. I'm going to do TOD is equal to this, and then we're going to say A is going to be equal to just some random tuple, so 0, 0. Let's see what that does. Write this over here. CD projects, Simuleos GPU, and let's give it a go. So all we're going to do here is allocate a single tuple. That's it. That's all this function does. So we're going to run Julia include test4.jl and just run the function test on some random input. And make sure the input is a GPU array. So A is going to be equal to this, just 100 ones. And then we're just going to do f wait on f test and see if this breaks. If it doesn't break, then I'm going to try a couple of other things, like accessing individual elements of the tuple and stuff like that. So that didn't break. So what I want to try to do next is create set A. Oh, this might be the problem. A of 1 is equal to 2 is probably an issue. Probably if I create a tuple, A is going to be equal to this, 0, 0. I probably can't update the tuple. So A of 1 is equal to 2 is not going to work. That's the issue. The set index issue is the issue. Okay, so that means we probably need to write this to, we need some sort of shared memory array or something like this. So that's obviously going to fail. Now, okay, let me try doing the following. Let me try, instead of this, I create it as an array. I've got a feeling this is not going to work, but I'm going to try it. Okay, Control D, Julia, include test. We're going to create the Q array, and then we're going to go from there. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. I'll totally address it as soon as I see it in chat. So we're going to define we're going to define A is going to be equal to this guy, and we're going to run with our random F test. So wait here. I don't know, guys. I don't think it's going to run. But if it does, that solves our problem. That's what we need to do. I don't think it's going to run because I don't think the allocation of an array on a GPU thread is a good idea, first of all. Yeah, so I thought it was going to break. So, backup plan. We're going to create a giant shared memory array that is of size group size and then 4. And we limit the number of dimensions that we can run the simulation on to 4. I don't like that, but that's what we can do. So let's go ahead and do it. All right. This means we have to use a local ID a bit, which is fine. Okay, so let's go here, Control D, and then we're going to do vi source forces.jl. Let's go down to the end body code in here. So we have the group size there. In principle, I can just run at localmem32gs. But we don't want 32. We're going to set this to be 4. In fact, I think probably GS wants to be the first element. So group size 4. And 4 again. Again, this is limiting the number of dimensions here to 4, which is not great. But that's okay. So let's grab these guys. Here, temp acceleration. We can DD all of these. And then all this stuff we're going to have to modify a bit. So now we have to use a local ID as well, which is not going to be a problem. And we want to do global local. I think it's local. Okay, so the idea here is we have some big global array with a bunch of threads, and then we have a local, which is a local thread, which is going to be our blocks that we're working on. So this should be LIDK, and unfortunately, because of this, we're going to have to put some synchronizes in. Oof. That's not great, is it? No, we don't need to synchronize. Yeah, we don't need to synchronize. We don't need to synchronize. We'll still be fine, even without the synchronize. There's going to be LIDK, positions of JK is fine. And now this is where things are going to get a bit tricky. I'm going to try LID colon and see if this is actually going to work or not. Let's move this down to the next line. I've got a feeling this line is going to break, but we might as well give it a go. LID colon, and then this is also going to move down to the next line at LID colon. I don't know what I pressed, but it was not the right button. Okay, I don't know if that's going to run. I've got a feeling that's going to break, but that's okay. Temp acceleration of LID colon, and now where's our temp acceleration? Good. Good. The rest of this looks fine to me. Okay. So we can write that out, and then I think we're good to go. I think we just run this and see what happens. So let's see what happens. So let's go ahead and run Julia -- project. Do using CUDA Galilee, and then we're just going to try to run it, see where it breaks. In principle, this should work. In practice, it's probably going to fail. Load error, perfect. It says. Wait, what is the issue here? It says var local mem. Oh, is that not how you call it? Am I dumb? Please don't answer that. I am dumb. How am I dumb? So let's go into VI, back into histograms, and then histograms.jl. Let's look at local mem. At local mem. Oh, right. It's local mem. This is a space. And then this is going to be that. I just got the syntax wrong, and this. Okay, let's try it again using CUDA Galilee and see if it works. If it runs, I'm happy. I've got this, I don't know why I'm mentioning this. I've got this someone mentioned this the other day, but this little black bar looks like I'm sitting in a pew, like for a church. And so I have this little, I can't even show it to you guys. It's like it's like this pillow that I have that I've been kind of rolling on my back recently. And so like if you saw me just kind of like moving around like this, I was just like moving it up for some reason. I don't exactly know why. All right, so that broke. Let me see where it broke. Ooh, that's a message. What a wonderful error message. I've never seen such an amazing error message before. It's got a problem with copy to through a literal pointer is what it says. Let me see if we can fix this up somehow. So what I'm gonna do is Control D over here, and I'm gonna run most of the stuff over here from now on. This is going to VI forces, source forces.jl. We've got gravity, and let's go down here. So I'm not sure exactly what's breaking, so I'm gonna actually comment out some of this and just see what works and what doesn't. So we're gonna comment all this out right now. I've got a feeling we're doing like an out of index access somehow. So let's go here and run Julia -- project. And then we're going to do using CUDA and Galilee, and we're going to try to run the code one more time and just see where it goes. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. I'll totally address it as soon as I see it in chat. And for those of you who may be here for the first time and you don't really know what the point is, so this whole project is called Laos Labs. We're trying to create like an open, engaging research lab that, you know, uses the community, well, not uses, but like encourages the community to help us do research together, and that's kind of the whole shtick. If that sounds interesting to you, I'm glad you're here. Feel free to follow. Otherwise, you know, thanks for stopping by. I really appreciate all the company and everything. So let me get some water. I'm going to be streaming. I really am trying to stream from 2 o'clock to 8 o'clock p.m. Every day. Except for Tuesdays, which will be from 12 to 6 instead. So I'm trying to get about 6 hours of streaming in every day. You know, some days we'll get some really good stuff done. Other days might not be as much stuff. Okay, so that ran. With sandboxing, when do you use it? I don't know. I don't know what sandboxing is. So I have no idea. I'm so sorry. Okay, so let's go here. And now my suspicion is that these lines of code will also work down here. So I suspect it's in the for loop that things are broken. Control D, Julia -- project, and now we're gonna do using CUDA and Galilee and run it again. Is sandboxing like setting up like a toolbox, or setting up a set of tools to try stuff out with? I guess like I don't know how to put it. I'm actually doing a very bad job of describing it, but like a, also I think my camera's kind of like not exactly in frame. Let me see what happens if I do this. Now maybe that, and then I run the code, see where it breaks, and maybe move it down just a little bit. That didn't help at all. That might be okay. Yeah, that's fine. Yeah, okay. Where you can run simulations. Oh, I still don't know what it is then. I'm sorry. So is it like a, 1 second. So let's do DD here. Let's paste here, and DD here. I'm pretty sure it's in the force law then. Yeah, it's probably in the creation of the subarray where things are broken. That's why I had to do it that way before. Let's do Control D. And let's go to Julia -- project. Like, is it where you can just test a bunch of different simulations out to see what it would be like in a real run? Or I guess I can Google it. 1 second. Run this. Okay. What is sandboxing and how does sandboxing work? What is sandboxing? Testing a new computer program for its in an isolated environment. Yeah, I mean, I don't think I've heard the term before, but it's yeah. Anytime you're trying to test to make sure that something is running properly, that's when you sandbox it, I guess. So like it's kind of like an integration test mode. So like if you've written a lot of code and you want to make sure it works for a bunch of different environments, I guess that's when you want to do it. Sorry, I don't really have a great example or a great explanation there. Okay, so I think the big issue here is with these indices in here, the creation of the subarray to pass into the force law. I think that's actually the key problem here. So if we do temp position here, and we actually have this, we have this read in, the LID, and with temp position, LID colon, LID colon, LID colon. So we have this read in the indices themselves as well. So like this would read in, for example, J and TID. Then I think it should be fine. Am I doing this correctly even? I think so. So the temp accelerations is going to be positions of TIDK. Temp position is going to be TIDK and LID. So we're putting that onto a local memory resource. I mean, if I could find a way, I think the creation of this sub array is what the problem is. I think that's where we're running into issues. I'm going to be right back before we fix this issue. So give me just 2 minutes. Sorry about that. And then I will be right back. And then we can keep working on this and then see if we can get the other code to run as well. So we'll see how this goes. Give me a second. I'll be right back. Okay, I'm back. So we have about another, hour and 30 minutes, hour and 20 minutes left in stream today. I think we can get this working in the next maybe 20 minutes or so, and then we can benchmark it against that other thing that we're going to try to benchmark it against earlier in stream. We mentioned it. I'll talk about it more later. If you're just coming in, you haven't been here before, this is Leos Labs. The idea is that we're going to try to do like really exciting, engaging open research. And yeah, if that sounds interesting to you, I'm glad you're here. And hopefully you'll stick around. We'll see how it goes. So what we're doing right now is an n-body simulation. So the idea is that each individual particle here sees n other particles, right? And it updates its acceleration, essentially how fast it's moving every time step, based on what every other particle in the simulation is doing. So this guy right here is looking at every other guy in the simulation and asking itself, hey, how much acceleration, how much closer should I move to this particle at every given point in time? So what we realized earlier today is that our calculation for that acceleration is actually not particularly efficient. There's a lot of things that we're missing and a lot of things that we could do to speed it up. And so we tried to do that and then we ended up failing. So now we're going to try to create like some compromise in between. So we're still trying to speed up the current implementation that I have. And then once we have that current implementation working using some shared memory tiles on the GPU, things should be a bit faster and we should be able to just keep going with the simulations and see where it goes. Again, I have been streaming for about 4 hours now, and I was trying to stream for an hour before that, so it's roughly 5, maybe 4.5 hours of streaming, something like that. Is kind of like how long I've been doing this. So I might be a bit tired, and I'm just letting everyone know. And I've been trying to give everyone this kind of I don't know how to put it, but disclaimer at the last hour of stream every day that, you know, my stream stamina is not particularly high. So even though I'm doing my best to be, you know, exciting and engaged and all that kind of stuff, if I sound a little tired, it's because, again, I've just been streaming for a while and I'm not inherently extroverted. So doing this like very like long discussion with everyone, it takes a lot out of me, right? So if I sound a bit tired, that's why. But I do think we can at least get this working today, and then we can update it and just make it fancy. Like we're gonna really try to see whether this implementation or my next implementation will be faster. That's kind of what I'm trying to do right now. Okay, so let's go here. So this force law thing, this line is broken right here. And the reason it's broken is because we have to create a sub-array here. Now, what I'm wondering is if we can use another resource that Julia has called a view, or if this is already creating a view. Are your limitations because of your computer or the source? Well, so what do you mean? So the limitations here are not, so the reason this is broken is basically due to the software. And fundamentally, you know, the Julia software is still more extensible than other things. Or the universe. Wouldn't it take the power of the whole universe to simulate the universe? It would take it would take more than the power of the known universe probably to simulate the universe. Well, no, that's not true, because the universe itself is a simulation of itself. So in that case, you know, it's fine. You know, like fine. You know, we're all in a simulation in the experimental physicist's definition of a simulation, you know. So fine. It definitely takes the energy of the whole universe to simulate the whole universe. But I would reckon it probably takes more than the energy of the entire universe to simulate the entire universe if you're not using the experimental definition of simulation. Okay, so what am I going to do next? I'm going to check out a very simple test here and see if I can pass a view of an array into a function and see how that goes. So let's go into test4.jl. In fact, let's go into vi test2.jl, which is the one where we're testing a bunch of different functions. And let's create a new function here, which is function, what am I going to call it? We're going to call it function array test. Okay, and it's going to read in A, which is going to be a subarray, and here, and it's just going to say A is going to be dot equals to 0 or something like this. Sure, let's do it. Okay, so in here what we're going to do is we're going to read in input. I don't think we can do it that way. I think we're going to have to do input. Oh, I think I know what's happening here. I think I know what's happening exactly. Is that related to the halting paradox problem? I have no idea. It's a paradox to simulate the whole universe. You can simulate everything but the simulation itself. I mean, I guess. I genuinely don't know. Like, you know, we're talking about a bit of philosophy that I don't really know about here. As far as the halting problem, I don't think this is related to the halting problem. Could be. But I don't think it's fundamentally related. But this could be because I don't know the halting problem well enough. The only place I've seen the... you're talking about the stopping... Let me make sure we're looking at talking about the same problem here. When you say halting problem, I usually think about stopping algorithm... what is it called? 1 second. Usually used for like stock trading, optimal stopping. This is what I'm thinking. Are we thinking different things? If so, I'm so sorry. We could simulate the universe in our universe. If we could simulate the universe in our universe, we could simulate faster than real life than predicting the future. This is pretty close to defining a set that contains all sets. Interesting. Yeah, I mean, you're right. Okay, I know nothing about this, if I'm honest. But I think the halting problem is actually different now that I think about it. All I know is an optimal stopping. Let's go to halting problem. Halting problem, Wikipedia. In computability theory, halting problem is the problem of determining from a description of arbitrary computer program and input whether the program will finish running, continue, or run forever. Ah, interesting. Let's see. One can't define a set which contains all sets. Such a set does not exist. Sure, that's fair. Because obviously, if the set contains itself, but itself is... Sure, that's totally fair. Okay, so I'm going to run a very simple test here. And I think I already know what the problem is. What I'm going to try to do is... I'm new at set theory. I am also new at set theory. I'm really bad at it. So if I just try to run... maybe array test. In fact, let me just do the following. Input. I tried using broadcasting before, didn't I? No, I tried a broadcasting operation before. Let me go there. Vi test.jl. This should be, yeah, we have the input here. We even have the sum in here. So that should work then. It should just be passing values through to a subarray. That must be it. So if we do, oh, sorry, wrong one. So if we go test 4.jl, vi test2.jl, and we try the array test. So let's just try array test of input of colon. And let's just do, let's try that. See if that works. That's probably not going to work, but we can test it. So let's do Control-D, and let's do Julia. So the reason this is not working, it makes a lot of sense. I think. Let me see if this breaks, and then I'm going to reverse logisticize it. Give me a second. So include test4.jl, or is this test2? This is test2.jl. Crap. So Julia, include test2.jl, and let's just try to give it a run. This is pretty close. I'm new at set theory. It's an interesting problem. I love science. Yeah, so this is one of those things, you know? I think the halting problem is a very constructed problem because the proof is that the source code of the halting determining program is fed to itself, which is a very special case. We can look at the halting problem in a second. I don't know much about it, so it's something I have to look into. Okay, so let's just go ahead and run wait on ftest a, and I think we have to read in f, which is going to be +2. This is going to break. Because I haven't defined A. So let's define A, and then let's do it again, and show that it also breaks. No method matching ftest of CuRay float64. What? What happened? No method matching ftest of... Oh, we just read an input. Oh, okay, that's fine as well. Yep, not a problem. This should break. But it's enough. Can the universe produce itself? I guess it's the inverse problem. Is that the inverse problem? I thought the inverse problem was something else. But it might still be possible to determine a program halts for 99% of all programs. Good enough for an engineer. Okay, so this broke. This is what I expected to see. This definitely should have broken. Yeah, that makes sense to me. So how do we fix this? Can we try passing in a view? So let's see what happens if we make it a smaller set. So what if we just do 1-to-1? Or what if we do TID to TID? Let's try it again. I misspelled TID. Let's try it again. Here we go. Write this. And we're going to do Control-D, Julia, and then we're going to do include test2, define A again, and try running it one more time. I'm pretty sure this is also going to fail. I think any type of array generation is going to fail in a kernel. And this is essentially creating a subarray. I was hoping it wouldn't create a subarray, but I think this is the only way to do it right now. Let's see. I disagree. It works because the current programming languages are carefully constructed. So the compilers for them work too. Should I look up the halting problem? If you guys give me, I'm happy to look at the halting problem in just a second. Like once we get this working, which look, there's an easy hack to get this working. But once we get it working, I'm I'm happy to take a look at some of this stuff. Like I said, I'm kind of tired after streaming for about 4 hours today, more like 4.5 hours. So I'm happy to just kind of look at something else and chill for a bit once we finish getting this to work, instead of like hopping into the next thing. So I'm actually not convinced that what we're doing will even speed anything up. Yeah. Okay, so any subarray is going to fail. Let me see if I can do something else then. What if I do view of A, and we do 10 to 11? Is that going to do anything? View 100 element array at index 10, 11. So can I do this? Perfect. So what if I try view of input? TID. This is probably also not going to work, but I'm going to try it anyway. There, and we're going to do TID +1 or something. Okay, so let's do Control D. Julia double dash. I don't have to do double dash project. We're going to do include, redefine A, and then go from there. I'd first look up the definition of Turing machine. I think it's better to show the halting problem through the post-correspondence problem. It's, of course, more complex, but it's less weird, hand-wavy as a demonstration. When the TM is defined, the halting problem is simple. TM is the what? Turing machine. So we're going to do define A here, and then we have to wait on the test and see what happens. So now if we wait, we should get something. I mean, it's going to fail again, is what I'm expecting. This is also going to fail. If this doesn't fail, then we have a way around. Universal Turing machine, right. Right. So, I mean, yeah, this also failed. In fact, I think it failed even more spectacularly than before. Yeah, like, it's just, gosh darn it. Okay. Like the entire GPU just died on that one. So Control D. Okay, that's fine. Let's just do this a dumb way then. That means we have to read in the entirety of the shared memory array to each. Oh, it's so annoying. I hate that we have to do that though. I feel like there should be a way around this. Maybe there's not. Maybe we just have to read in. Okay, let's just do it that way. Yeah, let's do it that way. So now we're going to read in LID and J. Oh, sorry, TID. Oh, no, we need LID this time. LID and J. Do we also need TID? No, everything should just be local now. So it should just be LID and J. Yeah. But what's J for then? Wait. So it should just be LID. Oh, everything's local. So all we need is LID. That's it, just LID. So if we go up here, we can modify these so they take in an LID. So let's do gravity first, just to make sure that one works, and then we'll update the other ones if needed. LID. So in here, we just have to modify all of these, so it's LID and K. U there. 1 second. LID, K, and we just modify all of these guys. And down here as well. It's nice that they're all local. I mean, that's quite nice. So let's try running that. I'm going to go back over here, Control D, Julia double dash project, using, okay, 1 second, using Galilee and CUDA, and then go from there. What do we have? I missed some stuff. This is fascinating stuff. Last I watched this, you were working on the dissertation. Congrats on the PhD. Oh, it's been a while then. Yeah, so for those of you guys who don't know, I got my my PhD from the Okinawa Institute of Science Technology in December of 2019. So it's been 2 years, honestly, since I finished my PhD, since the PhD streams in particular. So yeah, it's been a while. Since then, I worked at MIT for a year, and then after working at MIT, I kind of stopped to do my own thing. So. Oh, that still broke. Really now? Okay. Well, let's take a look at that in a second. This will save you a ton, save you hours of research. If you need USB drive stick, just buy Samsung Bar Plus. Don't get small one from Fit Plus because it's so fast that the controller overheats and shuts the drive down. Other drives don't worth it because they're bad at random writes and reads. Interesting. Okay, I know nothing about that. Also, what controller are you talking about? Like a controller in your computer? Hey, Silent Tree, how are you? Let's see. Those are some awesome cards. Creds. Oh, creds. Yeah, like yeah, PhDs and stuff like that. Yeah. So anyway, so when I say that like this project, the Leos Labs project, is an attempt at an open research lab, like know that I'm not just some random person. Like, you know, I mean, sure, in some sense I am a random person, but like, you know, I went through the PhD. I know what research is like at MIT. I can, you know, I can call upon people at MIT anytime. You know, my wife is a fantastic researcher. I have plenty of things. It's not like I'm just some random person doing research. It's like I'm a random person who knows how to do research, and I'm trying to show other people how to do it as well. Like, that's the whole point of this project. And look, I 100% understand. It's hard. It's hard to, you know, show research in a way that's, you know, engaging and entertaining and also clear and concise and all that kind of stuff. But that's what it is. The one that converts flash chip to protocol USB. Okay. So something is broken, and I'm not sure what's broken, so I don't know what to do. We're reading in the local ID. Crap. Okay, so we're reading the local ID. We have the temp position 1, temp position 2, temp acceleration, and local ID. So, let's see, what do we have here? Trying to shove a square into a round hole. So, okay, one thing about USBs that I've never understood, people always have this weird thing where they're like, for some reason people are like unable to like plug a USB in the correct way. And like they say, you know, you try plugging it in correct like once and it's not going to work. You plug it in again, it still doesn't work. Like they tried this way, and they flipped it around, tried that way, they flip it around, tried it again, it still doesn't work. I'm like, what are you doing? Like, I don't understand. Like, do people literally have trouble like plugging USBs in? Like, I've never had that problem in my life. And yet you see this problem like all the time. People are like, you know, USB, plugging in USBs the right way, it's impossible. Like, I see this meme all the time. I'm like, really? Like, why though? Like, who has trouble with that? I would love to use earthquake data in a meaningful way. To be honest, I don't really know much about earthquake data. I think obviously there are a lot of people who know a lot more than I do. But there was a very interesting paper I found not too long ago, dealing with the determination of local gravity, because obviously gravity does fluctuate a bit depending on how far away you are from the Earth's center, and stuff like this, and like how much mass is under you, and blah blah blah, like little things here and there. Determination of like local gravity with like optical sensors and stuff like that, and they noticed that like the small seismic shifts here, actually they could identify like the small seismic shifts and stuff, and it was quite cool. I was like, oh, that's amazing, actually. Like at some scale, you should be able to like maybe even identify like the movement of magma, maybe. I don't know, like this stuff I don't know anything about, but like at some scale, like if you have a good enough precision, you should be able to like see like stuff like that. That'd be really cool. Again, I know nothing about this topic, but it'd be cool if you could, you know. Okay, so we know these are broken. Not entirely sure what's broken. It could be the passing of a shared memory array to a function that could be broken. So let me go there and let's see what we can do. So we're going to replicate this test. Wait a minute. Let me write this, try it again, because maybe I didn't write it correctly using here. And then I'm going to try to test it, because I think the passing of a shared memory array to a function, I think, is what broke, which sucks, but that's okay. We'll figure it out. Okay, Galilee.run. Give it a second. Let me get a little bit more water. Again, guys, letting you guys know I have about 1 more hour left in stream. I close my stream off right at 8 o'clock p.m., which is about 6 hours of streaming. For today, it'll be about 5.5 hours of streaming, 5 hours and 20 minutes of streaming. But yeah, I do try to get about 6 hours of streaming in every day. That broke spectacularly. We're going to have to try that again. I try to get about 6 hours of streaming in every day. So if you're here now, you like this type of content, you want to see more, please feel free to join me tomorrow, and any other day for that matter. Just want to let everyone know my stream times. Also, feel free to check out Discord. I'm going to show you guys that now. Also, for the record, I use light mode. If you need to put your sunglasses on, put them on right now. Here you go. New mentions in general. Oh, what is this? Oh, okay. Yeah, I'll look at that later. Create invite, copy button. Let's go ahead and paste it here. Paste this there. There you go. Good. Okay, so in the case that you want to hang out on Discord after stream, feel free to do that as well. We try to chat and stuff there. Rip and Dip 444, thank you so much for following. Really appreciate it. Okay, Let's do a test. I'm going to see if I can pass a shared memory array to a function. That's what I'm going to test. I think what I'm going to do is go over here, remove these functions here because we saw that those worked just fine. Okay, array test A. So what I'm going to do, I think, is I'm going to say a dot equals 0. Maybe this is a fine test. Fair enough. Let's just go ahead and create our local memory array and try passing that in. So here we're going to say LRA, LA is what I'm going to call it. Why not? It's going to be equal to at local mem float 64. And let's do float 64 of, let's try to keep it the same size as the other one. So this is going to be a size at group size. Then we're going to do 4 times 3, which is going to be 12. And then we're going to try to pass that in to the array test here. So we know the view is broken, but let's see if we can just pass in LA. Okay, let's see what happens. So we're going to go over here. We're going to do Julia, include. I'm an idiot. 1 second. Let's see. Would it help to just chat for the next hour so you can wind down? So the thing is, I mentioned that I'm tired, but also like, the reason I mentioned that is not so much like, dude, like, please just hang out. Like, this is what I want to do. It's more like I just want everyone to know that if I sound a little bit less enthusiastic, slowly but surely, as the time goes on, I just start to feel a bit more tired. It's like the end of the workday type of thing. Like you start feeling a bit when 4 or 5 o'clock rolls around, you're like, but actually, I genuinely love streaming. I love talking to you guys, the fact that we're like doing this, like. I think part of the appeal of the stream is the fact that we're doing cool stuff, while talking to people, and engaging with people. And, one thing I have thought about recently is maybe changing the category. Cause let me just go to science and tech really quick. Here to twitch.tv, and let me go to science and tech. Should be right there. Perfect. Here. So if you look at science and tech, like you've got, live earthquakes, you've got electronic, here. Which I think is actually quite cool. I don't know this person. 3D Drunk. What is this? Is this English? And then you got PC building, which will also be quite cool. Maybe we should just raid someone else in science and tech, actually. Like, some of this is actually quite good. Actually, yeah, it's not bad. I quite like a lot of this content, really. Anyway, my point is the following. I've been thinking a lot about, like, changing categories or something like that on Twitch. Because in some sense I do more software and game development, in some sense I'm doing more just chatting, and maybe I can switch between those guys, but I've ultimately been settling on science and tech because I feel like we're doing research and I just want to get more people doing research on Twitch. That's what I really want to do. I don't know how to get that started. I don't know how to go from where we are now to getting a whole bunch of people doing groundbreaking research on Twitch, If you need to wind down, there was an update to the Metropolis PR after your review. So I don't know if we can take a look at that as well. I need to look at the source code for the Metropolis algorithm. So let me see if I can at least get this code to run. And then once I can get it to run, then I'm at the state where I want to wind down. But it's going to take another 10 to 20 minutes to get it to run. So at the very least, we need to get to that state. I'm also happy just to chat for a bit, for maybe, a few minutes just at the end of stream, that kind of stuff. My point is the following. I'm a bit scattered today, but I don't feel like I really need to wind down too much. It's just that I'm scattered. And as we go longer, I'm going to be more scattered. That's what I mean to say. So let's go ahead and try this test really quick. So we're going to include, what? Okay, so we're going to include test 2. Am I in the right directory? Yes, okay. Include test2.jl, and let's see what happens. Again, guys, I just need to be very clear. I'm actually incredibly happy that you guys are here, that we can just do cool things together. Like, that's what I'm excited about. Okay, so we have this F test. Let's go ahead and wait on it, see if it runs. A is not defined. Try it again. I'm always on the live earthquake site. They have a great Friday mix party. Oh, I didn't know that. That's actually quite cool. +1 is not defined. Where are we using +1? Oh, I see. Ho, I see. I removed some functions that we actually needed. That was my bad. All right, let's try it one more time. Julia, no, just include first. Then we create A. Then we wait on it. Let's go. But yeah, I guess I'm interested to hear what you guys are interested in. Like, do you guys want to see like more, like, what do you guys want to see? You know, excuse me, what is this? This is, your name is Sundari Tubeworm. It is a 4-dimensional galaxy simulation. That's what we're working on right now. Let's go ahead and wait on this. F not defined. F. Oh, come on. Don't give me that now. I screwed up twice. I'll explain in just a second. Give me 2 minutes. So let's go here, Control D. We're going to run Julia. We're going to run include. Sorry. Let's go ahead and do 1 second. Why is it taking so long? Okay, A is going to be equal to that. And then we're going to run it one more time and see what happens. I'm pretty sure this is going to break, but let's see. And whether it breaks or not, I'll explain what we're doing. Just give me just 1 second. GPU compilation failed. So we are unable, interesting, we are unable to send, weird. It returns a value of type union. Okay, well then let's just make it not do that, shall we? All right, screw you then. Try it again. I'm so sorry. Give me a minute. Let me run this and then I'll explain what's happening. Give me just 1 minute. I'm so sorry. Okay, we're getting this to run. Now we're going to define A again. And now, after that's done, we're going to wait a second. Please. Please run. Dang it. Okay, it didn't run. I'll figure out why it's not running in a second. Okay, so what you see up here in the upper left-hand corner is an n-body simulation. By n-body simulation, I mean that there are n bodies, i.e. particles, being simulated. So each individual particle feels the force of gravity from all of the other particles. So the idea is that this guy up here is feeling all of these different forces from all these other particles and deciding where it wants to move based on how fast it's moving in some direction and what every other particle is doing, right? So it's moving up here, and then you'll slowly see it kind of comes down this way, right? So at every time step, what we have to do is we have to watch to see how these particles are moving, right? And basically this involves 2 steps. The first is, going through every single particle and determining what the acceleration should be for the new particle. So this means that every particle has to look at every other particle. It's an n-squared operation. And then the other thing that it needs to do is it needs to actually move the particles forward. Slibdub, hey, thank you so much for the raid. I hope you're having a great day. Feel free to talk about your stream in chat, but also, I don't mean to force you. Like the way I also don't like it when people call me out when I raid other people's streams. So I feel like, don't mind if you just want to hang out. You don't have to say anything. You can lurk. That's totally fine. But I hope your stream went well. And thank you so much for the raid. Really appreciate it. Okay, so what are we going to do next? So what exactly, how is this related to what we're doing right now? So to do these types of simulations, we have to do them incredibly quickly. To do them incredibly quickly, we have to do them in parallel. And the best thing to do anything in parallel with is the GPU. So we're focusing on GPU engineering, and I'm trying to just figure out why the code that I'm running is breaking. I'm not entirely sure what the deal is, so I'm just messing around a bit. And that's where we're at. So let me go ahead and try to do input here instead of the shared memory array. So what I suspect is happening is that we're unable to pass in a shared memory array. I think that's what's happening. How are you actually generating the video stream of your particles? Right now, we're just outputting them to file and then plotting each individual frame in GNU Plot. I can show that in just a second if you need. So let's go here. Let me try running this code as well. So we're going to run Julia, include test2, running this, and hopefully it works. I got to be honest, it could also be the broadcasting operation that's failing. So we're going to try to unroll that broadcasting operation as well in just a second. Is equal to that. Are you supposed to pass a function to your kernel? No way. If this works, I'm going to be really angry. Not really angry, but I'm really like, oh, come on. It's one of those things, A is equal to this. All right, now we're going to run, wait on this, see if this runs. Just see if it runs. The problem with this particular library is that the error messages are just, they're next to impossible to read. So, I don't know. It's really difficult to work with. Okay, so it's still broke, which is good. It means it's not a stupid error. Unsupported dynamic function invocation call. Call to multiply. Call to multiply? What do you mean by that now? This is an aside, but I want to mention that I love watching your stream while working on my own side projects. I feel like when I'm listening to someone who's working on really complex work, I get motivated to work on my own problems. Currently implementing an interpreter for fun. Oh yeah, actually that's super fun. I love writing my own like abstract syntax tree parser or this type of stuff. And feel like the struggle is shared. Thanks for you streaming. Yeah, thank you so much for coming by. Honestly, I mean that's one of the big reasons I stream. I feel like not only are we doing cool stuff together as a community, but, a lot of people have said that, because of this stream and because of, a bunch of other things, people within the community, people are now making stuff that they wouldn't have made before. I mean, this isn't, to some extent, this isn't YouTube, this is Twitch, right? The idea is that I'm not primarily on your monitor, right? I'm a second screen, and hopefully you're doing stuff on your own. And, if you feel this content is good enough to be on your primary stream, that's also fine. I'm really happy with that. But the nice thing about Twitch is you can either watch me or you can do your own stuff and have me on the side or all that kind of stuff. It's kind of, that's the point. And I'm so happy to say that there've been a huge group of people in the community that have, they've done a bunch of cool things. And it's specifically because, this stream has in some ways inspired them to do that. Sorry, let's do length of A. Oh, I'm just bad at typing. Let's go here and just say A of I is equal to 0. Okay, so I'm just doing this as a way to test whether it's the broadcast that's failing. The broadcast shouldn't fail, but I'm just double checking because, if it's something stupid like that, it's an easy thing to fix. But this is good. I mean, I was mentioning before that I was getting kind of tired, but actually seeing that we have all these errors and stuff, it's kind of nice. It means that we have a single problem to work on, and probably by the time we get this problem finished, it will probably be the end of stream today, which is good. It means that we've finished some very clear projects. Here's the GNU plot scripts. Oh, yeah, thank you, by the way. I appreciate that. Also, should we call you 10x Programmer or Frank? What do you prefer? I feel like 10x Programmer is what I would naturally call you because I usually like to go by people's moniker. But you also have an amazing you've done amazing other projects. I think I've seen your stuff. It's on Twitter or something, but I've seen your stuff on Twitter or Discord or somewhere. It's quite good. It's not like you're. I kind of feel like I should shout you out to some extent, because the content's actually really nice. I don't care what you like. That's fair. Okay, let's go here. Let's include it one more time. And let's see what we can do. Okay, so we're going to include it. We're going to redefine A, and then we're going to see if it runs. I don't think this will run, so what I'm going to try next is reading in the entire input array is what I'm going to try to read. So let's do wait here. This will probably also fail. And 10x Frank. He's 10 times better than the old Frank. Okay, let me get some more water. And let's see. Yep, that failed. All right, let me try reading in the entire input array. Because I know we can read in arrays. Here. But what is it saying? It's saying that there's... What is it saying? It's saying invalid dynamic function invocation call to star. Where are we using star? Overdub, check IR. Bah, it's a pain. Let's try reading in the input. Okay, let's go here, run Julia. Did I write it? Yes, let's go into include. Oh, this is gonna be a bummer, isn't it? Oh, no. After all this is done, we're gonna find out. We're gonna find out that we can't use any of these tricks that I've been trying to pull because we can't pass a shared memory array into a function. That's probably what's gonna happen. Include, oh, no, I need to run wait on ftest. This one will probably run, I imagine. It's not going to create the correct results. We're going to have threads racing against each other and stuff, but it will probably run, which is something. Come on. No, it broke. This also broke. Okay. Sorry, so now I'm even more confused. We're getting unsupported dynamic function invocation call to star. So what is the problem? Let's go ahead and erase everything else except for this guy. And I don't know. Oh, I'm an idiot. Are you kidding me? Oh. Okay, yep, that's probably it. That is almost certainly it. Let's just, yep, there we go. We figured it out. Thanks, Amaras. If it would have looked just one line down and I would have read that line, I would have understood. But no, I didn't. I didn't do that because I don't know, hubris or something. Okay, let's go here. Let's define A again. Try to run this. This should work. And then we're going to try passing the shared memory array in and see if that works. And then we can finally see whether that's our problem with the code or not. Let's wait here. And hopefully we get something that's working. Okay, give it a second. Yep, 1 second. Oh, come on, is it gonna, oh, it still broke. Did I write this? Yes. So how did this one break? Undefined use of none. Should be return nothing. I think that worked. Julia, include, create A, and go from there. It's always hard stepping back on your code. Yeah, I mean, especially when I'm trying to do something quick. And, you know, I hate to blame Stream, but sometimes, like, when you're in the middle of streaming and all this kind of stuff, you kind of just want to do things quick and just not... like, you pay attention to it, but not... It's not like your full attention, you know? Like, sometimes you're kind of chatting, and you're doing this and that, and it's just sometimes you end up just not looking at important things. I mean, you know, I'm not saying... I've mentioned this many times before, but like Stream is both helpful and harmful in that it's helpful because, you know, there's people like MRS, for example, who will say things in chat and be like, oh, you forgot to do this. I'm like, oh, thanks. I completely forgot about that. Or we'll have plenty of like really good discussions like we've had today with various different people. And all of that's super helpful because it kind of helps you reorient yourself, helps you better communicate, helps all these different things, you know? But it's also sometimes a little bit harmful because I end up just chatting. And the just chatting ends up taking over sometimes. Okay, so we're going to do this A here. Okay, now let's go ahead and define our wait function and see what we got. Okay, hopefully this will run. And this would mean that we can pass shared memory arrays into a function, which means that the other one was only failing because of an indexing problem. No, so that failed. Let me try one more time. I'm just going to read the actual input in here. And then if this works, I'm going to take a look at that error message and see if the error messages are the same. Because if the error messages are the same, then we know the problem. We cannot pass a shared memory array into a kernel. That's the problem. Which to some extent, I guess I should have expected. I mean, I guess... I don't know if I should have expected that or not. I don't know if that's a bug with kernel abstractions or if that's a bug with... I don't know. Let's just take a look and see. I feel like as a user, I would imagine being able to pass a shared memory array into a kernel should be fine, or into another function should be fine, right? Like, okay, let me think about this a bit. Okay, so here's what I'm going to do. Let's go ahead and include this guy, run this again, make sure it does pass, and then we're going to just take a look at the error message and see what we get. Ooh, man. Okay, so now we're going to define A. Okay, and now we're going to do wait, and this one should pass. Unless, the only thing that... This is going to fail. Because of this reason. I did not define group size correctly. Okay, well, that's good to know. So let's go ahead and define group size again, and try this whole thing over again. Set uniform group size here. Okay, let's go up here, paste, 1, and then we're going to go in here and say group size. Okay, let's try this again, make sure that passes, Control D, Julia, include. The other problem here is that it only we only see that it fails at runtime, which is kind of another pain, but we'll see. Okay, so let's define A. But yeah, like in general, you know, I really do want to like turn the science and tech channel or science and tech category into a place that researchers can just stream and we can like, you know, it can just be a place where people just do cool things. I mean, there is the other problem that, like, I know Twitch is primarily for gaming and all of that. But okay, so this did pass. Okay, so one more time. We're going to pass in the local array here. Okay, Control D, Julia, include. And I'm going to try also, then after this is done, passing in a slightly smaller local array. And if that also fails, then we know the problem. The problem is definitely in passing a shared memory array to a function and acting on it in that way, which is fine. I think probably the issue here is that the function probably just doesn't have access to the correct like resource, I guess. I don't know, like, you know, the memory hierarchy or whatever that we're talking about here. I don't know what I'm talking about, so let's just go ahead and keep pretending I do. Let me get a little bit more water. And let's go. Okay. And now we're going to do wait here. So this should fail. That's what I'm expecting, this to completely fail. What I'm going to try to do next is run with a very small shared memory array and go from there. Don't be too hard on yourself. If you have fun, we have fun. When you give us regular summaries, regular summaries, it's been really helpful. What? How did that pass? No. The only thing worse than code breaking is code passing when it should break. Like, that's the only thing worse. There's nothing worse in the world. Okay, there's a lot of things worse in the world, but like, it's just, okay, so we know we can pass a shared memory array into a function. So then, what's wrong with my life? Okay, so let me comment out the for loop and let's just start debugging this one step at a time. All right, let's go. Julia Double Dash project using Galilee and CUDA, and let's get this going. Because that means the shared memory accesses should work. The nice thing about shared memory is that you can, anyway, there's a lot of nice things about it in that it's a lot easier to access the data in shared memory. It's a lot faster. So in principle, this should speed up the code a bit. Let me take a look at the Twitter, see what we got. Here, paste this there, enter there. What do we have? Game developers, doesn't work, why? It works, why? That's like every programmer, it's not just game developers, right? Okay, so that ran, perfect. So then let me go ahead and comment this out here, comment it out here as well. DD there, and paste there. So now we know it's gonna be the Force law that breaks, Julia Double Dash project using Galilee and CUDA, and then we go from there. Yeah, so I think we've got, what, another 30 minutes left in stream, 40 minutes left in stream. So yeah, I think we might finish this up. Yeah, we'll finish this up. I don't know how much longer it's going to take, maybe 10, 20 minutes, and then wrap it all up together. And I think maybe that's a good place to close stream. We might chat for a bit. I think, yeah, let's just chat for like 20 minutes or so after that's done, and just hang out, I think. Okay, so temp position 2 of LIDK. I don't see how that would break, but I'm cautiously pessimistic. I'm so sorry. I don't know what happened to my throat there. It just kind of got a bit dry. Dims to gravity is still gravity. Do subatomic particles, primarily electrons, have any angular momentum? Yeah, so this is something I don't really have a good description of either, but technically there is something called quantum spin, which is a type of angular momentum. Now, I gotta be honest, I don't know much about it. I should know. Spin states is something that I even dealt with a lot during the PhD, but I've completely forgotten everything about them. So if you want to talk to someone about them, like talk to someone who knows more about quantum. But definitely, like, spin states are super important for this type of thing. Okay, so let's go over here. Let's DD here, DD there. So we're reading in temp position 1, temp position 2, and then we have temp acceleration, which are all local memory arrays, and then we're reading in an LID. So we go to gravity here, and let me comment out most of gravity and see if it's broken. Okay, let's go here, write that, go over here. Now we're gonna do Control D, Julia Double Dash project, using CUDA and Galilee, and try it one more time. See what's happening. Yeah, let's see how this goes. I don't know. I'm super pessimistic now. So that ran. This should run as well. And then we'll just see what's actually broken here. So we have position 1 of local ID k, position 2 of local ID k, times position 1 of local ID k, position 2 of local ID k. Are we indexing incorrectly, maybe? Oh, we'll see. They have spin, either half or negative 1/2, but they don't really spin. Yeah, so this is me just not... I really don't know. I mean, yeah, I don't know. You hear angular momentum all the time at that scale. Let's do this, but it might mean something different if I'm honest. Again, I don't know. I really don't. It's been such a long time since I did anything with quantum. I say such a long time, but it's been only like 2 years. My hunch is that spins influence how they emit their electromagnetic radiation. That makes sense. Yeah, to some extent, I guess. I mean, we can talk about what spin is in just a second. I'd be happy to take a second and look into that. Again, I'm not convinced. Okay, so that broke. So that means that this guy here is not good. Okay, so this is an illegal instruction encountered. And let me see if it's the indexing or if it's the adding to R2. The indexing here is going to be LID and K. So this broke, which means down here should also break, I believe. So let me just output like at print size. We'll do size of position 1, for example. Well, let's do size of position 1, and then we're going to do new tab. Oh, sorry about that. New tab, and then size of position 2, and then we're going to do new tab, and then size of, well, that should be fine. But let's also print out LID. And then we're going to print out a new line. Wait a minute, maybe... No, it should be fine. Let's print this, go over here, and we're going to do Control D, Julia _ project, using CUDA Galilee, and let's see what we get. Again, we've probably got another 20 minutes of debugging here to get this to run. And then at the end of the day, we're not even going to really get this to, we didn't even do what we wanted to do. I thought this was going to be quick, like taking 20 minutes, and I've taken 2 hours on it, which is, I guess, like what you would expect. I mean, it's not too atypical. Let me, while we're working on this, just go ahead and put a to-do statement at the top of the code here. To-do, that broke, but it was expected to break, but because the error message is so long, I can't do anything about it. So let's add the to-do statements and say, try a two-kernel approach with a loop over particles. Okay, let me just try this. I'm just going to put it down. For I equals 1 to n. I think I want more space. No, that's fine. Why not? That's okay. So for I equals 1 to n, find acceleration of like particle p1. Sure. And then end. And then here we're going to say sum x. So here we're going to say, oh, sorry. I'm just kind of writing some code down so I remember what I want to try. Is equal to this, sum acceleration. Final acceleration is equal to sum of the acceleration. And then we end the for loop. So this should be acceleration of I colon or something. This will be temp acceleration. Okay, I'm just writing that down so I remember to try it later. Okay, so let's go through and get this to work. So let's go down to the gravity here, and let's dd there, paste up here, write this, go over here, Control C, Control D. Try it again. So now we're going to do Galilee.run using CUDA Galilee and see what we got. Okay, give it a second. And then let's see how it goes. Galilee.run. We should get a bunch of print statements is what we're looking for. And I just want to take a look at what those print statements are. Because what I want to make sure is that, first of all, position 1 is a two-dimensional structure. And then the second thing I want to make sure is that LID is on position 1. So what do we have here? Control C. Okay. So it looks like it's 256.4, 256.4. Length of position, that's what's happening. I got it. DD here. DD here. I got it now. I figured it out. Perfect. Size of position 1, 2 is what we want. Position 1, 2, and then 2 as well here. And then we put a size here. And this should, in principle, do it. Using CUDA Galilee, Galilee.run. I'm an idiot. There's still a print line statement. Print. What? How did that? Why is that being printed at all? Write this, go over here, Julia Double Project, using CUDA Galilee, try it one more time, and then hopefully we get something that's working. And then we get some sort of gravity simulation, then we fix the other functions up, and then we're done. We're done, we got it. We did half of what we wanted to do today. We did a quarter of what we wanted to do today. Okay, we did at best a quarter of what we wanted to do today, but we did something. And that's sometimes enough, you know? All right, this seems to be running, I think. Please. Come on. And then we're going to go to the aux. Oh, beautiful. Beautiful. You ran. That's all I need. All right, let's plot it. Let's plot it. It's running now. After 2 hours to fix a bug that I implemented. Oh, if I wasn't so tired. Was there progress? Answer is yes. I don't know. So I know a lot of people probably do this, but like during my PhD, my advisor would come by pretty much every day. I'd always be there in the morning. And my advisor would come by at like 8 o'clock a.m. or something like that, which is when I'd be there. And, you know, he'd always ask how things were going and like what was going on and all this kind of stuff. And I'd always like phrase what happened, like what was going on during the day in a positive way. It's like, oh yeah, we made progress here, or we made progress here. And like, frankly, like the actual day-to-day experience was definitely not making any progress. But, you know, you kind of sell it in a way, you know? Okay, is this going to work? Almost. Oh, geez, what happened? Why did it go that way? It's so close to working, but why is it up there? Oh, no. It's wrong, but it's wrong in a weird way that makes it very difficult to debug. Like, why do we have 2 clusters? Ah, crap. Am I just not looking at all the particles correctly? They're going this way. I mean, yeah, it looks cool, but like, it's not correct. Oh no. All right, I'll save it as another blooper. All right, let's do Mogrify. I'll save it just so I have it. Special neural network CPUs, which do big matrix multiplications, might be useful for n-body calculations as well. That's probably true, but also like, what is a special neural network CPU that does big matrix multiplications? Like that's kind of what a GPU is, isn't it? Let's do create video. Yes. Let's just save it. So let's go ahead and move. Move test.mp4 into blooper2.mp4. Okay, perfect. This happens naturally. I got 2 clusters as well with my simulations. Interesting. I do find it weird that you got 2 clusters though, because I mean, maybe with another random distribution of points, but I think there's a y at the end that I missed. At least sometimes. Yeah. Yeah. Okay, let me, but I have no initial velocity to create those. Let me go into the forces file and see if I do feel something's wrong. Sources, oh, I'm in the wrong VI back into source, and then forces.jl, and gravity is in here. Okay, so let's think about it really quick. So we have the kernel n body, we have the kernel m body, and it is, oh, I'm so sorry, I'm tired. So we're creating the force law here. We had to, yeah, so we had to do it this way. Yeah, okay, fair enough. We had to do it this way. We have the temp acceleration is equal to this. We have temp position 1 and 2, that's fine. Then we do temp position 2 is equal to that. and then we do the force law. Could be an issue with the force law. We do size of position 2, which is going to be... Let's do here. So we have 1 to n. N is the size of accelerations. I see the problem. We should have... This should be 1 through size of positions 1. That's the problem. Okay, let's go back over here. Remove this guy. Control D. Julia double dash project using CUDA Galilee. And then I think this is actually going to work. I think it's actually going to work. I'm 25% sure, which is more sure of anything than I've ever been in my life. 25% sure is relatively high for me. Okay, let's go here. Let's run it. Let's go here, quit. And let's just let it go. This is going to be perfect. You're going to see the most beautiful galaxy simulation you've ever seen in your life right here on this Twitch stream. You'll be able to tell your grandchildren. You'll be like, I was there. I saw it. The most beautiful galaxy simulation on the planet right then and there. It all happened here, you know, right here on Leos Labs. So I'm sorry. Let's go to GNU plot. Okay, let's see what happens. Give it a second. We're going to plot it. And then you're going to see it. The absolute most beautiful n-body gravitational simulation imaginable. It's impossible to beat this visualization that you're going to see right here, right now. It's going to be perfect. Are you ready? All right, 3, 2, 1, and... Oh, no! Oh, no! What happened? Oh, jeez. Oh man, it just blew up. How did that happen? Is it because... How did that happen? It's like the acceleration was multiplied by some vector. The Big Bang. I mean, we only got to 15 frames. We literally only got to like 20 frames. That was it. And then all the particles are gone for the rest of the simulation. Oh gosh, I can't believe that happened. Okay, let's go ahead and go into PCman FM, and let's save that one as well as another blooper. We got to what, 25 frames? So let's just delete every other frame and save that as a quick visualization. Oh, I cannot believe that one. Okay, so now we're gonna do Mogrify. Oh, jeez. They're moving forever when they reach escape velocity. I mean, there's no escape velocity in this. Create video. Yes. Move test into blooper 3.mp4. Okay. So what could possibly be happening? That's a good question. Source forces.jl. All right, what do we have here? So in the gravity force, we're adding to R2. We have the temp acceleration is going to be plus equal to that. Could it be that we're not clearing the temp acceleration appropriately? Movie tests to RAM. RAM FS. What is RAM? Wait, RAM file system, you mean? Let's see. What do we have here? Position 1 of LIDK. Positions LIDK. Let me get some water. I just can't. It's awful. What is RAM? What is that? The big issue here is that everything is obviously in RAM, right? But like the generation of the images is not. So there's always an escape velocity even for stars and galaxies. That's true, but okay, maybe everything did pass escape velocity. Maybe that happened, but like, oh well. I don't think that's what's going on here. So we have the temp accelerations. So we have the temp accelerations. We set them all to be 0. We go through all of the particles. We set all the temp accelerations to be 0. Perfect. We then have the positions. We set the position 1 to be what it's supposed to be. Then we change the position 2. We add all the accelerations up in our local array. And we go back here. So the thread ID K. So the positions of thread ID K. All right, I can take a look at that later. I mean, yeah, we can look at the RAM file system in a second. Okay, so what do we have here? Temp acceleration is at local. It's going to be the group size, which is going to be up to 256. And then what we're doing here is we're saying temp acceleration of LID 0, which is going to be 0 to 256. So all those are going to be set to 0. Sure. Then we do this is going to be equal to the positions of TIDK, also fine. The force law is going to be temp position 1, temp position 2, and temp acceleration, and then LID. Most time is probably spent. Wait a minute. Wait just a brief second, like, you know, just one microsecond, 1 micro nano millisecond. By the way, I don't know if you guys are familiar, but there's a type of optical fiber. You know, optical fibers, like things that send light through, like your internet through a fiber or something like this. What you can do is you can take the optical fiber and you can heat it and you can stretch it. So the center of the optical fiber is like within the nanometer range, like nanometers or micrometers in size. And when you do this and you send light through the optical fiber, a little bit of light will leak out of the fiber. Now here's the thing, the nanofiber is of the range of 100 nanometers or 700 nanometers or a micrometer or something like this. The notation for the nanofiber is of course nanofiber, because even though it is roughly the size of a micrometer, people call it the nanofiber because it's cooler if it's in nanometers, right? So fine, nanometers, right? But some people didn't like the fact that it was called a nanofiber because it's roughly in the micro fiber size. So they instead started calling them microfibers. So we had these two different camps. One called it microfiber, the other called it nanofiber, right? And then all of a sudden, people were like, okay, let's combine the two camps. Let's sit down and let's try to reach a conclusion where we can both call this object that is either a microfiber or a nanofiber the same thing. So they settled on the micro nanofiber, which is the dumbest name. The absolute dumbest name you could have called it. It's like, it's now like, what, is it a micro nanofiber? Like, what is this? What does that mean? It's just like, they decided they would like just combine both names into one. It's like, okay, that's what we're going to do. It was so dumb. Let me do Mirage here. I'm sure this is going to be it. This is it. There we go. Perfect. Beautiful. Amazing. My time step was really high in the last simulation. And because my time step was so high, it ended up being that we did a very unphysical, like, simulation where the particles just zoomed way past where they were supposed to go. Oh, thank goodness. All right, we have something that's working. Wonderful. Let me take a look at the XKCD. Let's go here. There. And let's take a look. There we go. Enter. Standards. Situation 1, there are 14 competing standards. 14, ridiculous. We need to develop one universal standard that covers everyone's use cases. Yeah. Situation, there are now 5 competing standards. It's exactly correct. There's an XKCD for everything, right? Okay, so we got that working. Beautiful. Now we just have to update the other functions so that they also work. And then we are golden. That is it. That's what we need to do today. So let's go ahead and run that. Make sure the other forces work as well. And let's do it. Let's go into vi.source.forces.jl, and we have to update the repulsive force, so it reads in an LID. And these are now 2. This is also going to be a 2. This needs to change the size, so DT there, and here as well. There we go. And this guy as well. And then we need to change this, so there's an LID, comma. Something like that should work. Oh man, my throat is kind of, it's kind of, you know, like that moment where you're like about to cough, but you don't want to cough. And like you're trying to keep yourself from doing that. That's exactly where I'm at right now. It is a very difficult position to be in. Okay, let's get this done as well. So we have to read in LID. All right, perfect. And now we just do 2 here. I messed up. 2 there. Over here, we're going to do 2 here as well. And we're going to do Man, some of those bloopers were pretty good today. Size here, size here. I want to take a look at those bloopers before we're done today. LID there, 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 here, there, and there. So I think we're going to get this running, take a look at the bloopers, and then I think we're going to be done for today's stream. I think that's it, isn't it? Okay, so let's try this again. We're going to do Control D. Julia double dash project. We're going to remove the previous files. We're going to do using CUDA and Galilee, and we're going to try the different force laws out. See what happens. They're all going to be in 2D, but that's fine. What is that? Miramasa Jam. Interesting. So let's go into this one. So we want to run force law repulsive first. Just make sure it runs. And then everything's good to go. And then I'm going to do some very quick performance tests. I mean, look, it's going to be the same speed as it was before, but now that we're using shared memory, maybe it's a little bit faster. Not sure. Let's just go ahead and check it out. I'm excited. I think this is going to be great. So this one, all the particles should blow away. They should literally just, every particle should just run away from each other. That's, no, I was excited and now I'm not. Okay, LID, what did I do wrong? Position 1, 2, position IC, that's what I did wrong. I had a typo. Let's try it one more time. Okay, everything, there doesn't seem to be a typo anywhere else. Control D. One more time. Let's do it. Using CUDA Galilee. Let's go. Get it done. I think we're almost there. Like, genuinely speaking, we're almost there. So 2 streams ago, we ended stream with the simulations you see in the upper left-hand corner. And I was pretty happy with that. I was like, oh yeah, it's pretty good. Then last stream, we started with those simulations and then we broke them. Immediately broke them. And then at the end of stream, we got the same simulations out. I was like, yeah, that's pretty good. So today, we did the exact same thing. 3 days in a row, we've had the same visualizations, and we slowly but surely just optimized it a little bit by a little bit. And to some extent, I think that's exactly right. I think that's fine. I mean, I was talking about maybe doing color quantization or something like that for today's stream, but I think ending up on the Galaxy simulation is just as good. I mean, we're going to be doing the same stuff no matter. So I think in the future, probably we'll stick with the N-Body Galaxy Simulator. Like, I think that's what we'll be focusing on. But know that the optimizations that we're doing for the Galaxy Simulator will also work for like color quantization and other things as well. So we'll see how that goes. Okay, so after this is done, I also want to run, I think, Gravity 4D. Perfect. So let's take a look at this. Again, for this, all the particles should just fly away. 3, 2, 1. Perfect. Wonderful. Okay, so now the 4D simulation. This one's going to be a bit weird. We need to remove some stuff. And now let's run Gravity 4D. It's weird because we're going to do a 4D force law in 2D, so it's going to look a bit different. So let's go ahead and do GNU plot. It ran. Come on. Come on. And then once this is done, yeah, let's just see what happens. So right, the 4D force law is a 1 over r cubed force law. The reason this is so different is because a 1 over r cubed force law falls off really quickly. So the particles just can't see each other when they're very far away. So what should happen here is we should see the particles immediately come together quite quickly. And then, oh, they kind of spread out, actually. Yeah, something like this is what I expected. Yeah. Yeah, okay, that makes sense. So what you'll see here, let me just explain what's happening a bit better. It's not that they come in really quickly. What's actually happening is, let me make it a bit bigger here. Like this particle over here has no idea any particles over here even exist. So they're only moving based on their own local, like, so these particles that are in a cluster can see each other, but anything outside of that cluster, they can't see each other at all. So it just, basically they're only moving according to their local clusters, not according to any global forces, which can be interesting in its own way. Maybe if we add dark matter or something, it'll become more interesting. Why is that guy? What? Oh, what's going on over there? Every once in a while, you just see a particle zooming by. Do we see another one? Is that it? Oh, there's one. Hello. Oh, look at them. They're all kind of coming back. Okay, anyway, this guy's just meandering along. Okay, good to go. Good, so everything's working now. Let's just go back a directory, and let's do git status. Okay, git add dot git commit dash m moving acceleration calculation to shared mem. All right, let's do git push origin development and all that. 5 hours of work. for, what is that, 80 lines changed? Wonderful. Okay, let me do some quick timings while we're here. So I'm going to go up here and just do an at time on this guy for, I believe we're doing 1,000 particles. And I want to make sure we're using the regular gravity force law, so let's just do this. And let's do output type. Put method equals none. And then I'm going to make it bigger so you guys can see. Let's do huge here. Just move it over here. Ooh, hello there. Might be lagging a little bit. Okay, so let's run this and just see what happens. I believe this is right. Let's go. I'm just checking the time for all of these guys just to see if it's any faster. It might not be. Oh, 1024. Okay, so that's, I want to do 1024, not 1,000, sorry. So actually, let's just try 4,096 since we're here. Okay. Give it a second. This should take 16 seconds. What's the time? It's actually taking some time, actually. And my computer's lagging a bit. A lot of it. Which isn't great. I'm sorry. I don't think I'm dropping any frames. It's just my FPS is not... Alright, let's see how long this takes. Come on. And then I'm going to pull the previous code and see what that one looks like. It's taken a while, though. I feel like it's actually taking longer now with the shared memory than it did with the global memory. 4 times more would be 16. Yeah, right. But I was going off the old benchmarks. This is going to take a while. Yeah, this is going to take a lot longer than I thought it was going to take. Let me check. I thought these were what we were running before for the benchmarks. I forgot to add time it. Here's 4,096. So this is what we were running before. Output method is equal to none. 2,048. Let's run that one. And then I'll try 4,096 as well. I think it's actually slower after using the shared memory. Gosh darn it. Are you kidding me? All of that work, and we're slower. We're slower for it. Dang it. Oh, that's super unfortunate. Why? Why are we slower? Is it because of the allocation of the shared memory? I mean, we can look at the performance. Oh, man, no way. Let me pull up the branch before this, and... Ah, oh, no. That's just really... It's unfortunate. It's embarrassing is what it is. All of this work. I'm like, oh, yeah, it's definitely going to be faster. No way it's going to be... Ah. And it's slower. Give it a second to run. We'll just see how long this takes. I don't remember any of the runs taking this long last time. So, yeah, let's just see what it... And then I'm going to check out the previous branch before this one, and or the previous commit. So that took 62 seconds. No way. This is way slower. How is it so slow? What am I doing? Let's do git log, control D, git log. So let's see, adding R3 for slot. That's what I want. So let's do Q, git checkout. Can thread acceleration shared mem? Can thread acceleration shared mem in same time? Yeah, let me go ahead and check here. And there. Okay, now we're going to do Julia. Double dash project. Okay, so now we're going to do using these guys, and we're going to at time. Well, we're going to run it once, and then we're going to at time it one more time. So we're going to do just like a Galilee run. Let's see, can threads access? Yeah, they should be able to. I mean, that's the whole point in shared memory, I thought. Galilee.run for 256. Let this do its thing. And then we're going to try it again and just benchmark the 2000... What was it? 2048 run was what we just did, and it took 60 seconds. No way. Oh my gosh, it's way slower. Like we're talking about a factor of 6 slower. I think it might even be more. It might be like a factor of like 10 slower. Okay, so now we're gonna do at time here. Okay, give it a second. Okay. Maybe I was wrong. Maybe it's actually fine. Why am I running one dimension? Okay. At time here, give it a second. It doesn't really matter. Like what matters is the, that took 22 seconds. We are 3 times slower. Oh, why though? I thought that using the shared memory resource would be a good idea. Turns out it's not. Okay, let's do Control D. I'm going to write down some notes for things to try tomorrow. We'll still do some more GPU engineering stuff tomorrow. So I'm just going to put another to-do statement in here. Okay. So let's change this back to default size. Move this down here. Perfect. Okay. Okay. So what I'm going to do next is I'm just going to open up BI source forces, and let's just add a quick to-do statement down here. Gravity 4D. And basically, I want to try nbody again. Where's nbody? So here, I'm going to put another to-do statement. And we're going to say try again without shmem. And what I want to do is... Wait a minute, where's our shmem? Oh, it's not in nbody. It's in... Where is it? Oh, I'm in the wrong... Git checkout master. That explains it. Okay, let's try it again. And now let's do the to-do statement for the nbody. Oh, I can't believe that. Super unfortunate. No way you can do writes in parallel. Let's see. Well, right, so writes to a single location in memory you can't do, but I created the shared memory tile such that they're never writing to the same location in memory. They're using the same array, but they're not using the same like location in that array. And that could have been fundamentally the problem. It could be in the passing. I don't know. It could be somehow in the launching of the function. It could be so many things. I don't really know. Let's go here and let's do to do. Let's see. Write without shmem, but also without temp acceleration. Okay, can two atoms occupy the same space? It depends on your definition. I mean, like, you can have like if you use like a waveform, then actually, yeah, technically, you could have like an n particle system where they occupy like a mini body Hamiltonian, where in which case, you know, they are based on their probability densities in the same place at the same time. You could technically say it that way. Yeah, so like a Bose-Einstein condensate, for example, is literally just a whole bunch of atoms moving incredibly slowly and all occupying kind of the same space. So it's one big like liquid type of thing. Okay, well, that was a disappointing end. We spent a while optimizing, working on different things. We learned a lot. I learned a lot, especially about how to do this kind of stuff in kernel abstractions. That's great. I'm going to try, so there's 2 things I want to try tomorrow. So the first thing is I'm going to try basically redoing that code that we just wrote to not use shared memory, but also not have an extra acceleration array being passed around. The other thing is I'm going to try this, and we're going to see what's fastest. You know, doing multiple kernel launches or one kernel launch. I kind of want to run this on different hardware as well. I've got a feeling that it could just be that like my GTX 970 here is just slow, and then if you run this on some other device, in fact, if anybody has a CUDA device and you're willing to try this out, please feel free to do so. If you got an NVIDIA device, and just see like if one is faster than the other. I don't know. I'm running into a weird case. I really thought this would be faster with the shared memory accesses. I'm really surprised it's not. However, what might be the problem, actually, I think I might know the problem. The problem might be in this line right here. Okay, I think I know exactly what the problem is. The problem is in the line where we keep rewriting to shared memory. That's the problem. Let's see, where is that guy? Here's nbody. So we created three arrays here, temp position 1 and 2. Let me try writing it again without temp position 2. Because I think that might be the problem. Because here we continually rewrite to temp position 2 instead of just using the global memory axis, which means we first of all have to write to temp position 2. That's a problem. But we're also having to access the global memory, which is also another problem. So because of that, I think that might be what's causing it to slow down. So let's go ahead and remove write without temp position 2. The $, temp position 2, just use global mem. Yeah, so that makes sense because now temp position 2 is reading from global memory every time step and then writing to shared memory and then reading again from shared memory. So that would make sense why it's slower. Okay, that makes sense. DDD Decade, thank you so much for following. Really appreciate it. Okay, this is where I'm at for the end of the day, guys. Let me see who's live and who do we want to raid at the end of stream. There's Lana Lux. There is Gamozo. There's Freckled Science. What are they talking about? I feel like it's been a while since we raided her. 24-hour Science birthday subathon. Let's see, what do we have? Oh, Bother, we rated them yesterday. Dr. WD40. Tim, if there's anybody live that you want to raid, feel free to let me know. Otherwise, I might just do, who do I want to do? Let's raid Tim. Actually, no, we raid Tim a lot. Oh, yeah, no, let's raid Tim. Yeah. Or, you know what? How about this? How about I actually won't raid anybody today? Dutchin's Official. I don't know them. Let's go here. Let's see. What do they do? Oh, this is live earthquake. We can raid the live earthquake. Sure, why not? Let's go ahead and do it. Yeah, let's do the raid there. That's fine. Seems fine. If you want to, no problem. So let's go here. We'll start the raid. Raid on Dutchinson Official. There you go. Okay, so we'll do that raid there. It is 24/7, so I might stop hosting after a few minutes. But anyway, thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. I'll see you guys around next time for the next episode of Simuleos, where we'll be working on optimizing this end body simulator to heck and back. Like we're going to try optimizing it a lot. I really enjoy doing this kind of stuff. Thanks again for coming in. Have a wonderful time, and I'll see you next time. Bye, guys.